Hey, how's it going? My name's Dave Eddy. You might know me from a channel online called You Suck at Programming, and this is my Bash guide. My guide to Bash and Bash scripting. We're going to start from absolute beginner to some very advanced Bash scripting techniques, okay? Now, before I jump into that, I want to say if you're familiar with my content online, this will be slightly different, okay? This is not going to be like my normal YouTube videos. Yes, it'll be very similar, but the key difference here is I'm not going to just rapid fire information at you. I know that I can move fast, I can speak quickly. I am going to purposefully slow it down for this course. Now, I want this course to be useful to as many people as possible. That's difficult because everyone's going to be at a different place when it comes to how much Bash knowledge they have, computer science, engineering, stuff like that. So I'm trying to make it as approachable as possible, but I do want to dive into some very advanced topics. So we're going to start slow and we're going to work our way up to really advanced topics. Because of that, I'm going to assume you know some things. So the prereqs for this are that you have a computer, you're comfortable on a computer, clicking, double clicking, the hard drive, you know basic stuff about a computer, and that you have opened a terminal before. This is Bash, so a lot of people associate that with Linux. You don't necessarily need to have Linux. In fact, for this course, I'm recording it on my Mac. I will log into some Linux systems to explain some of the differences between the operating systems. I'll let you know when I do that during the course. But the point is, Bash just needs to run on any sort of Unix or Unix-like operating system. So if you have FreeBSD, if you have Mac OS, if you have Linux, then hey, you're good to go. You might be able to do this on Windows. I know some people talk about Git Bash. I don't have any experience with that. Your mileage may vary if you choose to do that. But the prereqs here is that you need to have some sort of terminal. You need to be able to open a terminal and type some commands in, and it needs to be running the Bash shell. That's about it. So if you don't know what I'm talking about there, pause this video, go learn that stuff real quick, and then come back here and you'll probably be able to learn something. So I expect you to at least know how to open a terminal. You don't need to be comfortable with the terminal at all. You can know like 2 commands and that's fine. We're gonna start slow and work our way there. Just letting you know, those are the prereqs to the course. And like I said, it's not a normal YouTube video. I'm not gonna try and hook you right away. I'm not gonna be like, all right, so today we're gonna learn. No. We're gonna calm down. We're doing bookkeeping first for this course because look at the length of this video. This is a long video. So important thing to note, this course is mainly a long video. That is what it is. You can watch it on YouTube. If you're watching on YouTube, hey, that's awesome. It's completely free. You do not need to pay for it. If you want to pay for it, you are more than welcome to. I will have a digital sale up and it will be on the course's website, which I will put right here. The course has a permalink website, course.ysap.sh. If you lose track of this video or you want to share this with someone, share this link to this website, okay? Because this will have all the information you need. It will have a link to this video on it, and it will have a way to download this video DRM free. So you can pay for this course. I'm going to price it, I think, $10 USD. If you want to, you will get a DRM free MP4 download of the course, and you can do whatever you want with it on your own personal machines. You can copy it to as many machines as you want. You can play it back on whatever you want. You don't have to worry about any sort of ads and stuff. You can pay for it if you want to. You don't have to. The only thing I ask is that if you pay for it, I'll outline this all on the website, but I want to go over here. Don't share it with your friends. If your friends want it, just send them a link to the video, send them a link to the website. They can buy it if they want, and don't re-upload it wholesale. I don't want that. If you are a content creator or you're like a professor or a teacher, you want to show this to your students or you want to react to it on your stream or you want to follow along on your stream and then upload those VODs to YouTube, hey, cool, awesome. You want to transform the content? I love it. I think that's great. Please just don't re-upload that. That's the only thing I ask. So yes, if you want to pay for it with a one-time fee, you can go to the website. I also do have a Patreon, which is a recurring monthly subscription. That sucks. I know recurring subscriptions are not great and they're not the best thing in the world and everyone hates them. I'm not going to ask you to do that. I'm just going to let you know that if you are one of my Patreon subscribers, you will get access to the DRM free download for free. You don't have to worry about it. It'll be part of your subscription. So yeah, if you want to pay money for it, that's awesome. If you don't want to, the best thing you can do, subscribe. Just hit that subscribe button on YouTube. Let's get that number really big. It's really fun watching that go up. It's a very nice vanity metric for me. Like the video, share it with your friends, share it wherever. Let people know. If you got some value out of it, go ahead and let other people know so I can grow this channel as much as possible. And finally, if you want support during this course, I have a Discord server. You can go ahead and sign up. I'll put the link up here. There's a lot of people in the Discord server, a lot of really cool people, a lot of nerdy people, and it's awesome. I hang out in there myself. And I'm going to create a dedicated channel specifically for this. I'm going to call it the Bash course, and it'll be up by the time this video goes up. So you can go there, you can ask questions, you can get support, you can talk to other people that are hopefully going through this course. So yeah, I think that's it. I think that's it for the housekeeping stuff. Like I said, with the prereqs, you got to be comfortable with the computer and at least know how to open a terminal, and we'll go from there. You do not need to be running Linux. I will talk about the OS specific things. We will do some examples on Linux. We will mostly be working on my Mac, but the cool thing is Bash is Bash. And when it's not, when it's OS specific, I will let you know. So yeah, I think with that, we don't need to waste any more time. Let's go ahead and jump in. Okay, so here we are. As you can see, I have a terminal open. It has Dave at YSAP, and it has this little $sign there, and it is waiting for input. I can type here, I can backspace it, I can type a command. I'm not gonna get into what that is yet, but I could type something here, hit enter, and then it would actually run it. So this is the terminal. Before I can even talk about scripting, we gotta get some of this stuff out of the way. So the terminal works as a REPL. REPL is what I'm saying. It stands for read, eval, print, loop. That is what the bash shell does inside your terminal. So just to be a little overly pedantic here, the terminal is the program. In this case, I am running a program, an application on my Mac called iTerm2, and that terminal is running an instance of bash. Bash is a program, and it's the shell. The shell is the thing that waits for my commands, and it's running right now as a REPL. Other programs can be REPLs. It's just a simple term for read, eval, print, loop. That is what bash is doing right now. It's waiting for me to give it input, so it's reading input. Once I give it input, let's say echo hi, we're gonna run our first command, and it's gonna print hi to the screen. That's awesome. It evaluated what I gave it, it printed any sort of output that was there, and then it looped, meaning it went back to the top, and now we're reading again. So read, eval, print, loop, REPL, you've probably heard this term before. That's what's going on here. The terminal will basically sit there. Bash, I'm going to try to be consistent with this terminology, but I do kind of conflate terminal and shell a lot. You'll see a lot of people do that. Bash, in this case, is waiting for my input. Bash is reading right now, and it is doing nothing else. It's waiting for me to say whatever I want. And then when I hit enter, it evaluates what I said. It looks at what I gave it. It says, oh, you gave me the echo command. Echo is a command that's on my system, and it will print whatever I give echo to the screen. That's what happens there. Super duper simple. Now there are some other commands, and you've probably seen some of these. Let's get started by talking about where we are on the system. And what I mean by that is bash doesn't exist in a vacuum. It's always in a directory, or put differently, it's always in a folder. Now this is very confusing if you've only used graphical user interfaces before and you're not comfortable with the shell. So I'm gonna pop open one to show you what I mean. So here I have Finder on my Mac. I popped it open. Let's make sure this is completely visible. Cool. So I have Finder on my Mac. If you were on Windows, you would have like Windows Explorer. If you were on Linux, you would have all sorts of other programs to show you basically what's going on in your system. But here we go. This is my File Explorer. I can see I'm in my home directory and I have all of these folders here. So here's the thing. Finder always exists in a folder. It's always inside a folder. Right now it's in this folder here, users Dave, that's my home directory, but it's always in a folder. And why am I stressing this point? Because your terminal is also in a folder, and we can run pwd print working directory to see what that is. Take a look. My terminal is in users Dave. Bash is in users Dave. So is Finder. Isn't that interesting? If we listed the files on our terminal, do you think we'd see what Finder shows us? Let's go ahead and do that. I'm going to shrink this down a little bit to kind of... There we go. We don't have to deal with any word wrapping here. Let's go ahead and run ls. Here's the next command we're going to learn. You run this, and this will list all the files that it sees. Look at this. You know something interesting? The files it sees here are the same files we have in Finder here. This is something I wish I had learned. I'm showing you guys something that I wish I had when I was first learning this stuff. To combine these two things together in your head is super valuable. If you already know this stuff and you're like, Dave, this is super obvious. It wasn't obvious to me when I was learning this stuff, so I'm trying to give you what I didn't have. So my terminal exists, my bash process exists in users Dave, and if I ls it, here is all the stuff we see in here, the same stuff we see in Finder. So I'll show you another command. I won't get too crazy with it. I'm just going to show you a quick little command. Let's go ahead and touch a file. I can touch file.txt and watch this. I'm going to create the file. It instantly shows up here. There's no lag time. How cool is that? So you can get a graphical sense of what you're doing. When I ls it again, you can see file.txt is there. That's awesome. It also shows up here. Now we've created that file. Let's go ahead and delete that file. This is a dangerous command. Be very careful with this command because you can delete things. There's no trash. There's no recycle bin. It'll just trash your file. Sorry, I should state that better. It'll delete your file. It'll zap it from existence. So be very careful with this command, okay? rm, remove. Let's rm space file.txt and let's hit enter. Gone. Immediately gone. Just completely zapped from existence. And of course, this works both ways. I could go here, hit new folder and call this, let's call this foo. And I did all that through the graphical user interface. When I go here, I'm going to clear the screen with the clear command. All it does is just clear what was visible there. And I'm going to run ls. And you can see that we now have a foo directory here. Here's the interesting part. We can go into the foo directory in Finder. If I double click it, we're inside the foo folder. There's nothing there. But if we go over to our terminal, we can cd change directory into foo, hit enter. And now if we run pwd, we are inside the same directory. Pause right here. I am going to use the terms directory and folder interchangeably. They are the same thing. I will tell you on a personal note, I associate the word directory more with the terminal, more with the command line interface, and I associate the word folder more with the GUI interface, the graphical user interface, but I will use them interchangeably. So typically if I'm over here, I'll say folder. If I'm over in the terminal, I'll say directory. But they're the same thing. I won't be consistent. I'll mess them up sometimes. Just letting you know that when I say directory and when I say folder, it's the same thing. So now that we're in foo, I can clear the terminal again. I can ls. There is nothing in there. That's awesome. So we could touch new file.txt and look, it shows up immediately there. I'm pointing to my screen like you guys can see it. Yeah, as you can see, it shows up right here. And of course, if we were to delete this, let's say I were to right click or you know what, actually command delete. I'm going to do it right from my keyboard. Gone. It's gone now. If I ls, nothing's there. So there's no like having to synchronize between the two. They are both in sync because they're both showing you the same underlying data structure. This part's very important. The file system is the file system. Whether I'm looking at it through Finder or I'm looking at it through the terminal, I'm looking at a source of truth, which is the underlying file system. So Finder doesn't need to sync with the terminal or anything like that. No, they're both asking the file system what files are there. So they can both touch the same files. They can both modify the same files. You can get into some weird situations with that. But yeah, so hopefully that kind of demystifies this a little bit. All right, so now let's talk about some basic file manipulation, okay? So what I mean by that is we are still in the same directory as we were before. We are in the foo directory in my home directory. We can touch, let's say, lesson1.txt. We're just making new files. They're blank, but we're creating brand new files. Touch lesson2.txt and touch lesson3.txt. Hopefully this is obvious what I'm doing. I'm just creating 3 blank files and we can see them right here. That's all well and good. But let's say we want to make a fourth one, right? Touch lesson4.txt. Uh-oh, I made a typo. I meant to say lesson4.txt. I put lesson44. Now, obviously, we could go over here. We could just rename it, and that's all well and good. But can we rename it from the terminal? Absolutely, we can. Very easily. There's no rename command, though. And I'm going to put a bunch of asterisks around this because when you get to the underlying system, it does kind of rename it. Blah, 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 blah. Forget all that. We're going to move this file. Now, this might be kind of weird. What do you mean we're going to move the file? We're going to move the file from lesson44.txt. This is the source. And the second argument we're going to give the move command is the new name that we want it, lesson4.txt. We'll hit enter. We'll get immediate feedback over here that the name has changed. And when we ls it, we can see that we have the 4 files that we expect. That's awesome. Here's the scary thing, okay? Legitimately scary, all right? Be careful with this. Imagine we had taken lesson4.txt and we were like, oh, let's call it lesson34.txt, okay? So we type 3, and then we accidentally type this. Now, do you see a possible problem here? What do you think is going to happen? Because we use the move command to rename something. What if we rename lesson 4 to lesson 3? Well, lesson 3 already exists. You ever try to do this in Finder? If I were to go here to lesson 4 and I were to say, let's call this lesson 3, and then it gives you an error message saying that that file already exists, please choose a different name. That's a very nice error message. It stopped me from overwriting a file. Does the terminal do that? Nope. It just overwrote the file. Lesson 3, the original lesson 3, is gone. Okay? I really want this point to sink in. Like, I really want this to sink in. We've learned the rm command, and now we're learning the mv command. These are dangerous. These are dangerous. Or More specifically, they're powerful. These are incredibly powerful tools. You have to think of it this way. They are powerful tools and there are no guardrails here, okay? You are able to modify your system. You paid for it. It's your system. You can modify it. You can also shoot yourself in the foot. So be very careful with this, all right? Like I said, there's no trash. I can't go and get lesson3.txt, the original one, back. It's gone. Now, if I were in like a Git directory, if I had checked out something on GitHub, yes, I'd be able to restore it, make sure you have backups, all that stuff. But I'm just trying to say, what I'm trying to stress here is be careful. It is surprisingly easy to overwrite files in the terminal, okay? I think the next thing is, let's show how easy it is to delete files in the terminal, okay? If I run the rm command and I don't give it any arguments, don't worry, it gives me a problem. That's an error message. I have to tell it to remove something. But here's the cool thing. Let's say I wanted to get rid of all these lessons, right? We have lesson 1, lesson 2, and lesson 3. I can just say remove lesson star.txt, and they're all gone. All 3 of them, gone. They're just completely gone. This is called a glob. This is a wildcard. I will talk about this more in the future. I'm just letting you know and showing you how powerful this can actually be, okay? It's kind of wild. Here's the fun thing. RM, depending on your version of RM, though I think most versions of RM support this, RM has an optional flag called -i, and I will show you what that does. So let's go ahead and recreate those files. I'm going to clear the screen. I'm going to spell clear correctly, and we're going to touch lesson1.txt, touch lesson2.txt, and touch lesson3.txt. Now let's go ahead and use rm-i lesson star. I don't have to say .text, I can just say lesson star and it will match anything that starts with lesson. Let's go ahead and run this. Look at this. -i means interactive. -i will prompt you to confirm that you actually want to do this. So I could say N here for no, I could say Y for yes, and I could say N for no, and we are left with, as you can already see on the Finder, we're left with 1 and 3 because we specified no for both of them, but we did specify yes for 2, so that's why 2 is gone. We could do this again. Actually, I should show you what I just showed you right now. Up and down, pressing up and down your keyboard, super useful. I should have touched on this earlier. When you press up on your keyboard, you go backwards through the history of commands you've ran. When you press down, you go forwards to the history of commands you've ran. So if I want to rerun the last command, I can hit up and I can hit enter. I can hit up, and I can get to the command above it. Hit up, I'll get touch lesson 3. If I press up again, we'll get lesson 2. If I hit up again, lesson 1. So up and down is a great way of going through your history. So if we ran this again, we can see that want to remove lesson 1? Sure. Want to remove lesson 3? Sure. We could totally do this. And now let's talk about the last thing here. Wouldn't it be nice if this was the default behavior, right? Well, like maybe while you're learning, you don't want to RM files and have them go away like this. Some people might say it's useful. Some people say it's character building to have these files be deleted like that. Hey, I've done it. I've deleted very important files before. But let's go ahead and say maybe I wanted that to be the default. Maybe I wanted RM to always ask. I can't make it the default of RM. I can't change that program, but I can alias it. Now, I will talk more about this in future chapters, but we can alias RM equals rm minus I. Go ahead and look at the syntax, kind of study what's going on here. When I run this, now when I run the rm command, the -i will be there implicitly. So we run rm lesson star, and look, it prompts me to actually do it because it is using the alias. How do I know that it's aliased? Well, I can run alias rm, and it will let me know if it was aliased or not. If I run alias mv, we can see that there is no alias for mv found. We didn't create one. So I'm throwing a lot at you. Don't worry, all this stuff will be explained in later chapters. We're going to go deep into every single topic that we've discussed here. All right, before we wrap up here, I want to show one last command to you that is going to be super useful. We cleared the screen. Actually, I should teach you that one too. Control L. Depending on the terminal you're on, will let you clear the screen. It's like the equivalent of running the clear command. So I unfortunately in the habit of pressing Control L a lot. It's super useful for teaching, but now that I'm trying to teach the basics of the terminal, I have to like remind myself. So hopefully I'm not jumping over too many of the shortcuts I do. I have future chapters dedicated to these shortcuts, so don't worry, I'll try to go over as much of it as I can. But let's say, we can use up and down to look through our history of commands. We also have the history command. If we run history, it prints a lot of stuff at us. And you can see, I have a lot of history here. We have almost like 5,000 some commands. Here are all the commands in my history. You can scroll through, you can see all of them. This is super convenient. This is super useful. If you log into a machine, you run a bunch of stuff, you disconnect, you log in a week later, your history's there. You can remind yourself what you were working on and what you were doing. History is super useful. And this is just a great tool to have. This is just something to keep in your back pocket, something to have in your toolbox. Super useful, super awesome. Okay, so one thing I want to touch on real quick is the concept of hidden files. So if we touch file.txt here, it shows up in Finder just fine. If we ls, it shows up there. But there is this Unix convention. You will see this on Linux, you'll see this on Mac. Windows will handle things slightly differently, but Mac, Linux, FreeBSD, other operating systems like that, they all kind of work the same. To make a file hidden, you have to put a dot in front of the name. Or, stated differently, a file that starts with dot is considered hidden. So we have file.txt. We could also touch a new file, .file.txt. There we go. And now notice, it doesn't show up in Finder. It's there, but it doesn't show up in Finder. Finder's not showing it by default. If we ls here, it doesn't show up in ls either. So is there anything we can do? I think there's a way to show it in Finder. Okay, I actually can't find out how to show it in Finder, so you have to take my word that it's there. But I can show you on the terminal, okay? I'm way more comfortable on the terminal, so don't worry. A lot of the future lessons are just going to be terminal only. But when we're here, we can list hidden files with -a. When you give -a to ls, it tells it to show all files. So we can run -a, and we can see that there's actually a surprisingly large amount of files here. We have dot, and we have dot dot. Talk about those more later. We have .dsstore. This is a Mac specific file that you'll see show up. It's super annoying that it shows up. We have .file.txt and we have file.txt. So real quick, dot and dot dot, these are built in to every directory. Every single directory will have these automatically. You can't create these and you can't actually remove them. They are there. Your file system provides these. Dot is a shortcut that always means your current directory. So when I am in, where am I? Foo. If I cd into dot, I'm still in foo. Dot is always your current directory. Dot dot, by contrast, is the directory one above. It is up one level. If you've ever seen a little up arrow on like the Finder or whatever, that's what it is. So in this case, we are in users Dave foo. If we were to go up one directory, we would be in users Dave. And I can prove that by cding into dot dot, running pwd, and then you can see that we are in users Dave. Hey, that's great. Now I want to cd back into foo. I can run cd foo, right? Well, I can also run cd hyphen. There we go. And this will bring me into the last directory I was in. So that's a cool little shortcut, something that Bash has, super useful. I used it a lot. cd hyphen to go to the last directory you're in, as long as you were in a previous directory. Like if you just fired up Bash, I don't actually know what happens if you run it. So yeah, let's go ahead and trash some of these files. We don't need them. We can run ls-a, and we can rm.dsstore. We don't need that. And we can rm.file.txt. Now hold on, what happened there? I didn't actually type the whole file name. Did you notice that? Watch this, I'm going to backspace this. .ds somehow just magically completed, right? Tab. I'm hitting the tab button. It's called tab complete. Tab complete is super useful. If I type .f for file, I can tab complete it, and it knows how to complete it. That's amazing. So we can rm that, we can rm that, and now we run this, we can see that we only have file.txt. Now be careful, because if I had foo.txt as well, now we have two files here. If I were to rmf and then hit tab, I got a little bell notification. My terminal would have actually made a sound. If I hit it again, you can see that it auto-completed and showed, hey, I can't actually autocomplete this. There are two things that match this pattern, so I have to pick which one it is. So I have to put fi, and then I can hit tab, and then it works because it's not ambiguous. If it's ambiguous, Bash will show you all the possible completions. It'll actually prompt you if there's like a lot of completions too, because sometimes you're in like a directory that has like millions of files or whatever. So yeah, there you go. There's hidden files. All right, so next up is file searching and paging. As you will notice here, we no longer have the Finder window open. We are going to be going all terminal from now on, okay? So we have our foo directory here. When we ls it, there's nothing in here. That is where we are now. I trashed those last two files that were in there, and we're going to jump off from here. So another command I'm going to teach you guys about today is cat. So if we touch file.txt, we've created an empty file. We can cat file.txt. Cat file.txt will open the file and show us what's inside it. It will print the contents of the file to the screen. That's beautiful. There's nothing in the file, it's an empty file, so it's not super useful right now. But there is a file on my system that we can cat that has a lot of useful stuff in it, and I will show you what that is. It is user share dict words. This may or may not be on your system. It's going to be there if you have a Mac. I'm going to run this, and there's going to be a lot of output here. So I'm going to hit Control-L, we're going to clear the screen, and we're going to run this. There we go, a lot of output, but if I scroll, take a look at this. There is a lot of stuff here. There are a lot of words here. So this is basically a word dictionary. It just has a ton of words in it, which are going to be useful for me to kind of show some of these concepts. So let's go ahead and do this. So now that we have cat user share dict words, what can we do with it? Well, the first thing we can do is we can search for it. You know, we have like find, like if I go to this, I can hit Control F and I can start typing something in here. So I could search for like Dave and it will find every instance of Dave in there. That's awesome, but that's my terminal. That's iterm2 doing that. I would like to be able to do that from bash. Is that possible? Of course it's possible. I'm going to introduce you to a lot of concepts here, but let's start slow. Instead of using cat, we can use something else. So I'm going to go all the way here. I'm going to go to the beginning of the line. We're going to swap this out for grep. Grep is a program to search a file or an input stream for some sort of pattern. So grep, the pattern we're looking for is Dave, and the file we're trying to read from is user share dict word. So when I run this, we get the file output, but it's been filtered. It's been filtered for only lines that have Dave somewhere in it. Notice that it doesn't necessarily have to start with Dave. It could be cadaver. That's pretty cool. But it has to have Dave in it somewhere. So what can we do with this? Well, we could anchor it. So we have Dave here. I could put quotes around this. The quotes won't change anything. The quotes will just stop bash from interpreting any special characters. And one of the special characters I'm going to use is this little character, the caret, C-A-R-E-T. I put this, and this means match the beginning of the line. That's what this character means. It's special. It says it has to match the beginning of the line. So if I rerun this, look, it only matched lines that start with Dave. So that's cool. And of course, there are other patterns we can do. Instead of checking that it starts with Dave, we could check that it ends with Dave. You can use a $sign. $sign signifies the end of the line. Nothing matched. That was a failure because nothing ends with Dave like that. But something has to end with, I don't know, ly. I'm sure we'll get a lot of words like that. Hey, here we go. Here's all the words that end in ly. That's kind of cute. That's kind of neat. Cool. So now that we have a little bit of grep under our belt, we don't have all the patterns there yet, but we can work our way up to it. Let's show what we can do with it, okay? Here's some quick little examples. We can make our own file. So we've done this a million times. Touch file.txt, and there we go. Now we have a blank file named file.txt. You know how we can echo? We can say echo hello, and there shows up hello to the screen. That's super nice. We can redirect it. And I'll talk more about this later, but for now, we can do this. So what's going to happen is bash is going to run this command, and instead of printing it to the screen, it's going to go there. So greater than means to overwrite. So it'll overwrite whatever's in file.txt. There's nothing there, so don't worry about it. We're going to overwrite the contents of file.txt with what the echo command printed, which was hello. So now if we cat file.txt, we get hello. Hey, that's awesome. That's how we can write to files very simply with bash. And then using that, we can put more in there. So we echoed hello. What if we echoed, I don't know, let's do like the letter A, and we put it into file.txt. Well, if we cat file.txt, now it just has the letter A. Remember, we overwrote some data. So that's not great. Let's go ahead, let's press up. Let's get back here. Let's write hello into file.txt. So if we cat file.txt, we get this. Let's echo A into file.txt, but let's use this notation. The double greater than notation, this means append. So it will create the file if it doesn't exist, and it will basically put data in the file even if the file doesn't exist. But in the case where the file exists, it will append it to the file. So if I run this and then we cat file.txt, we can see that we have hello, and then we have A underneath it. That's super cool. That's super awesome. So now we could do something like, let's echo B into file.txt. Let's echo C into file.txt. So if we cat file.txt, we have this. That's super awesome. So let's go back and do some of our grep. So we can cat the file, that's great, but we can also grep. So say we wanted to grep B out of file.txt. Well, there it is. There was only one line that matched B, and it was just that one line with B on it. That's super nice, but what if we wanted some context around it? Here are some useful flags for grep. I find these super useful like during my day-to-day with it. Let's say we wanted to find B, but we also wanted to get one line after B. So we want to find every time B shows up, but we also want to get one line after it. We can specify the after to 1. So that means find B and then also print one line after it. The opposite of this, of course, instead of after is before. So we could find B, but then also print the line before it. That's super nice. And the final one, which is nice, I love that they're ABC, that's why I named them this way, we can do a -C of 1. C is for context. So we're getting one line of context both above and below C. This is super useful when you're searching through files because sometimes you might know you're looking for a keyword, but what you actually want is like 3 lines below it. I can specify, hey, I want the after of 3, and then I'm good to go. Super useful, love it, I think it's great. All right, so let's go ahead and put some more data in that file. We can echo Dave into file.txt. Notice the tab complete works for the name of the file, super convenient. We could also echo all caps Dave into file.txt. And now let's search for it. Let's grep for Dave in file.txt. Okay, we only found 1 line. That makes sense, right? Let's grep case insensitively with -i for Dave. And now we found both lines. So -i, super useful to grep, basically says case insensitive, super, super useful. There's another one that's super useful I like is grep-o. Grep-o means only print the parts that have matched the pattern. So I could do something like this. I could say, I want to look for a line that starts with D and then matches any character. So I can put a dot, and a dot means any character. So that's a little bit confusing, but I want the line to start with a D and then have any other character to the right of that D. So when I run it, we get DA because it matched Dave, but it only printed the part that matched. That's what -o does. It means only print the part that matches. You can combine arguments. So I can say -o and -i. So I want to do a case insensitive search of the same thing. Notice that it matches both DA and uppercase DA. You might also see arguments like this when it takes multiple flag arguments. You can specify them together. -oi will give you the same result, and -io will give you the same result. That basically just means multiple flags combined into one, but this is the same thing. That's what's going on here. The order of the flags doesn't matter. I'll refer to them as arguments or flags. Typically flags when they're sort of like a Boolean, yes or no, true or false. So I is case insensitive, true or false. O is only true or false. So that's kind of how I think of it. That's why I'm doing it this way. So now I'm going to tease something very cool that is super powerful with Bash. And if you've heard of Bash, you've probably heard of this. And why is it taking me so long to get there? We're building our way up. Don't worry. We're going to talk about pipelines. Pipelines in Bash are amazing. They are super powerful. It is what makes Unix just so powerful. It's incredible. So I can cat file.txt. We can also pipe this data to another program. Now that might sound kind of confusing. What are we going to do? Well, let's pipe it to grep. And let's look for Dave. And then remember how grep takes the name of a file as this argument? Let's not give it. Let's not give it. We don't want to give it the name of the file. Grep is going to read from this pipeline instead. If we don't give grep the name of the file, it will read from what's called its standard input, and its standard input will be cat in this case. I'll talk more about pipelines later, but if we run this, we get the same result that if we just grep for Dave out of the file. So this is super useful because we can start taking data from the left that's large and distilling it into smaller data. So if you remember, we had user share dict words. This is a very large file. Let's grep for Dave insensitively. There we go. Here are all the ones that match Dave. Okay, that's awesome. I kind of want to care about the ones that maybe have ly in it. Okay, only one matched. What about ones that just have the letter A in it? Well, no, they all have the letter A because of Dave. What about the ones that have the letter I in it? There you go. So as you can see, you can kind of treat these like filters. It's like going through a sieve or something. Like we start with something very large and we pare it down a little bit. We pare it down a little bit. This is super useful. This makes interacting on the terminal just so incredibly powerful. And if you're thinking, Dave, really? This is all the time you're going to dedicate to pipelines? Don't worry. They will show up so much more during the duration of this course. This is like a main point of power with the shell in general. I'll teach you some of the Bash specific stuffs, but just the Bourne shell or POSIX shell having pipes, it's just incredible. What an amazing abstraction. What an amazing concept. All right, so now let's talk about the pager. What exactly is a pager? Well, let's get there. If we cat user share dict words, that's a big file. That's a very large file. I have to scroll. I have to get my mouse to scroll. That's how big of a file this is. So we can do this. Instead of running cat, let's run a different program. Let's run less. Less is a pager. It is a program that pages through input. So I'll show you what that means. Instead of cat, we're going to run less. And look at this. Instead of seeing the bottom of the file, we're seeing the top of the file. And see at the bottom where it says the name of the file in blue? That's a little bit confusing. Check this out. I'm pressing the down arrow. I'm pressing the up arrow. I'm pressing the down arrow. I'm pressing the up arrow. I can paginate through data. This is super stupidly useful. Your terminal may even support it. I can press page down and page up. This is super duper beautiful. So instead of having to print it all to the screen, I can just run it through the pager. And then when I'm done with less, I hit Q. Q for quit. Look, it's gone. It's not on my terminal anymore. It didn't take up any real estate, didn't take up any space. It shows me my file, lets me page through it. I can hit Q, and then I'm done. Less is a really powerful program. I'm not gonna spend too much time talking about it, but man, I really could. I'm just gonna teach you some of the basics. When you're in less, you have up and down to move. You can also use J and K. J and K are moving up and down. So if you've used Vim to program or like VI or anything, you're probably used to up and down being J and K. This is the same thing. Okay, so we can use J and K to move up and down. That's great. Notice at the bottom there's a colon here. That's the command that we're currently typing in. I'm gonna change it. Ready? I'm gonna hit slash, and now it became a slash. Now I can search. I can search for Dave. And there's every instance of Dave. I can still move up and down, but if you wanna jump through the search results, N to go forward, and Shift N or capital N to go backwards. So commit those to memory, super useful. I'm just hitting N to find all of the, and look, I hit the bottom, so now there's no more left to go. So Shift N to go backwards to the results. So super useful being able to search through things like this. Less is a super useful pager. Q to quit out of it. You may also have seen more. More is another pager that you could use on a lot of systems. More is the same as less. People will say it's kind of cute. They'll say less is more. So yeah, more will work, less will work. I pretty much just use less. So yeah, the beautiful thing about less is, you know how we use less and then we gave it the name of a file? You don't have to do it that way. You can actually just cat a file, like user, share, dict words, and pipe it in to less. So it's the same thing. Less, the only difference is, doesn't show the name of the file at the bottom. It doesn't know the name of the file. It just got its data from standard input. But we can still use less all the same here. That's great. That's awesome. Why is this powerful? Because it's in a pipeline. Again, I could grep for Dave and then pipe that to less. So now we are just paginating through the results that have Dave in it. Obviously, there's not enough to fill up a whole screen of content. That's great. But you can kind of see the power. I can pipe things almost infinitely. So I can do all sorts of filtering, all sorts of modification, pipe it to a pager, and then I don't have to fill up my terminal with unnecessary data. I can just kind of see it, hit Q, and then it's gone. Super useful, super awesome. Now, if you want to learn more about less is an external command that lives on your system. We need to talk about man pages, okay? Man is short for manual. These are the manuals. Commands, most of the commands you're going to deal with will come with a man page. I've been seeing some newer commands not ship with man pages. Hey, come on guys, make man pages for your program. But we can use man. So man will give us the documentation. So we can say man ls, and this will give you the documentation for ls. Now, the reason I taught you less is because this opened in some sort of pager, and in this case, it opened in less. So you already know how to use less. You know how to use up and down to move up and down and Q to quit. Now you know how to look at man pages. So if we man ls, we can see, hey, here are all the options to ls. There's a ton of options to ls. I don't expect anyone to memorize all these. But if we go down, we can see there's all sorts of stuff here. If I search, I could search for -a, and look, there's the -a argument. Include directory entries whose name begin with a dot. Hey, we used that earlier in this lesson, or previous lesson. So that's how you would find the options in the man page. The cool thing is less, of course, comes with a man page. So less will tell you it's a program similar to more, but it has many more features. Commands are based on both more and VI, so we have like J and K to move up and down. And there are other letters, and it's all described here in the manual. So I won't go over all the options here. I just want to empower you all watching to be able to go look through the man pages. Go find information about the commands you're using. If you get confused, go look up the man page. Go start reading some documentation. I want you to leave this course knowing Bash, of course, but I want you to basically feel empowered to know how to find out more information. So manual pages are a huge source of knowledge here. And of course, the funny one, man. You can get man page on the man page command, which makes perfect sense. Sounds confusing, but it makes perfect sense when you think about it. So even man takes different arguments and stuff. We're not going to learn too much about it right now, but just know that it will open up in your pager. So as long as you know how to use less or whatever pager you're using, you'll feel comfortable with it. All right, so let's dive into man pages a little bit here. Man will show you more than just commands. Man is great for showing commands. If I man mv, remember the command to move or rename a file, we can see mv, move files. In its first form, the utility renames the file by the source operand to the destination path, blah, 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 blah. You can get all the information you want on the mv command here. That's great. But man also shows a little bit more than that, and I will show you what I mean. If I man, you can see that there are sections. the first section of man is for commands. The second section is for system calls. This would be more kernel level stuff. This is how you actually communicate with your kernel. If you're just learning about computers now, this is probably a little bit scary. You don't have to learn too much about this. 3 is like library function calls, so you can find a lot of C standard library stuff in here. And then as these sections go up, they're a little bit different. I think they change operating system to operating system, but in my experience, sections 1, 2, and 3 are almost universal across the different operating systems. But the beautiful thing here is that knowing that, we can also say man1 CP. We don't have to do this, but we could do this because 1 is the section. You can even see the section it's in right here. So the CP command is 1, meaning it's a command. But there's more than that. It mentioned, what were the 2 sections? System call and library functions. So certain things are not commands, they are just library functions. So if I were to man, I won't go too far into this, but let's man printf as an example. As you can see, there is a printf command. But I didn't want that. I want to know the C standard library printf. So I'll have to run man3 printf. And there we go. Now I have a different man page, and this shows me the C code if I wanted to include standard IO and actually run the printf function. So this is just how you know like what section you're in. If you omit the section, man will go through and try to find it on its own. So it'll check section 1 first. If it's not there, it'll check section 2. If it's not there, it'll check section 3, etc. If you explicitly give it a section number, then it will go look for that specifically. So something to keep in mind, something to be aware of. This is going to be useful down the road. So these commands exist on our system, right? Like CP is an external program, MV is an external program. What do I mean when I say external? Well, let me show you something. Let's go ahead and run a different command. We have history, right? Remember I ran this command and there's the history of commands we've written. So let's go ahead and get the man page for history, right? If I run man history, we get this. This is weird. Built-in one, shell built-in commands. See the built-in command description in the appropriate shell manual page. That's interesting. So what is it telling me? It's telling me that history is not an external command. History is built into bash. So instead of using man, I should use the bash way of getting documentation. And this is key because a lot of people don't know about this. A lot of people will trip themselves up on this. Help is what you want. Help is the man equivalent for bash built-ins. So if we run help and then we run history, we can see, there we go. It doesn't go into a pager by default. I have to scroll it with my mouse, but you can see that it gives me all the options that the history command takes because history is built into my shell, not an external command. So how can we tell this? You may be familiar with the which command. So I can say which ls and it will tell you where on my system ls exists. So I can just run ls and my shell will find it. I could also run bin ls and it will run largely the same thing. That's all well and good. But if I were to run, let's say, which history, there's nothing, doesn't print anything. That's because history is not an external command, it's built into the shell. Another command, please take this command to heart. It is super useful if you're in bash. Type. The type command. If I run type history, we can see that history is a shell built in. Hey, beautiful. That's awesome. Where has this command been my whole life? Type ls. ls is alias to that. Oh, it looks like I set up an alias without even telling you guys. That's a little bit confusing. Is ls built in or is it a program though? Type -a ls. -a will tell you every type from top to bottom, and what that means is bash will execute it in order from top to bottom. So it'll tell you exactly where it found it on the system, but it will also tell you what it has. So bash will run this alias first. This is super useful because there are commands out there that are both. That might be a little bit confusing, but let's echo hello. Okay, what's the man page for echo? Well, here's a nice man page for echo. Look, echo takes a -n argument. It only takes -n. It doesn't take anything else. But if I run echo, I can give it -e, and it seemed to work just fine. Why is that? Because echo is built into my shell, but echo is also bin echo. This confuses people. This trips people up. Really, I mean this. Think about this. Learn the type command, because people will be like, oh, I don't really know how to use echo. I'm using an example here, but echo is one that trips people up. I don't really know how to use it. Let me pull up the man page. Oh, it doesn't seem to have the options they're talking about. That's interesting. Yeah, because the man page is for bin echo, and that's not what you want. You are executing the one that is built into your shell. When it's built into bash, you need to use help echo. And here are the things that echo supports in bash. We have a -n, we have a -e, we have a -E. We have all these sorts of fun little characters when we're giving it a -e. Echo in bash is more feature complete than the echo that's on my system. So just keep that in mind. If you take nothing else from this, please just take away type. Type is so useful. People use the which command, which only finds the external command. Type is useful for telling me everything about it. Remember we set up an alias for RM? If we run it, we can see that rm is aliased and rm is bin rm. So the type command, super useful, amazing. Please commit that to memory. Of course, just like we can run man, we can run help. And we can get all the information on how to use the help command. So yeah, I don't know. That's kind of fun. Help-m, display usage in pseudo man page format. I didn't even know this existed. What do you think that does? Oh, wow, it makes it look like a man page. That's really cute. So if we take this and pipe that into less, hey, it looks like a man page. Wow, I genuinely didn't know this. That's actually really cool. That is super useful. See how knowing how to use these tools and compose them together with pipelines is super useful? You can make the computer do a lot of really cool things. So you might be wondering, okay, Dave, you showed me that echo's built in. You showed me that history is built in. What else is built in? Well, don't worry. We're going to use another built-in command that I'm going to teach you about right now. It's for completion, but we're going to use compgen. This is built into bash. You're not going to have to use it much unless you're writing completions by hand. But compgen -b, this will list all of the built-ins. Super useful. I'll clear the screen and we'll run it. Here is a list of all the things that are built into bash. So you could go through each one of these and learn about them if you want to. They might also be external commands, like kill is built into bash, but kill will also exist on your system. So be mindful of that. The kill on bash might work slightly differently than the kill that's on your system. So, but yeah, compgen -b. The nice thing is, just like all the other commands, we could pipe that to grep for anything that has a K in it. And there are the built-ins that have K in it. I don't know why you'd want this, but you could. You could pipe this to less and you could page through them. So yeah, pipeline, super useful. Any program that just outputs text or data, we can run it through a pipeline. Super useful. Also, like we learned this before, I just want to cement some of these concepts. We could write this out to a file. We could make built-ins.txt. We ran that. Nothing happened. It didn't print anything. That's good. That's the Unix philosophy. Nothing happened there, so we can assume it was successful. Cat built-ins.txt. There we go. There's our list of built-ins stored in that file. Why you'd want to do that, I have no idea. I'm just showing you that data can be translated and written to files. It could be written to pipelines. You can do all sorts of fun stuff. History is the same way. So you could do history, pipe grep to less, and there we go. There's every time we ran less here. There's some weird examples from when I was like working on a previous video, so ignore some of this weird stuff here. This is my actual history file on my machine. But yeah, as you can see, just because like they're pipelines, we can still pipe grep, we can pipe that to less, we can do all sorts of fun stuff. So yeah, neat. All right, so now that we talked about external commands, I want to talk about another command that's super useful. It's not built into your shell. This is an external command. It's called file. File will do its best to tell you what type of file something is. Very confusing. I use the word file a lot. So we have these two files in our directory here, builtins.txt and file.txt. If we run file on builtins.txt, we can see that it's ASCII text. Hey, that's super cool. If we run file on file.txt, hey, it's ASCII text. That's awesome. If we were to run file on star.txt, it will go through each one and run file on it. Super useful. That's awesome. There are some other files here. Remember when we ran, let's say, type-a rm, we can see that rm is bin rm. Well, we could run file on bin rm. And this is a slightly different thing going on here. Look, we have a universal binary. This is an executable program. This is not a text file, it's an executable program. There's all sorts of fun stuff. It'll tell you if it's like a JPEG, if it's an image and stuff. File is super useful. Before you open up a file to like edit it, you can check to make sure like if it's binary or not. Your editor will probably do some of that stuff for you. File is super useful, but of course, there are ways to trick it. But I would talk about this because I want to talk about some of the path resolution that bash does. This is confusing. I'll explain what I mean. So in bash, when I run ls, it finds it on the system for me. It found this. It found bin ls. So it found ls for me in bin. I didn't have to type in bin ls. It knew to look there. How does it know to look there? There's a variable. It's a built-in variable called all capital path. So we can echo all caps path, but because it's a variable, we have to put a $sign in front of it. When we put that $sign, it tells bash to open this variable up and expand it. Don't worry, I have a whole section coming up on variables. This is just a very quick example. So here are all the paths it will check, separated by colons. It will look in each one of these paths for an executable and execute the first one it sees. So first things first. We have to, they're all separated by colons. That's kind of annoying. Can we turn colons into new lines? It'd be a lot easier to read. Of course we can. Get ready for the TR command. Translate. We're going to translate a colon into a new line. Now, because this \n is special, we do have to quote it. but take a look at this. Let's go ahead. Let's run this. And there we go. Same output, but the colon's been turned into a new line. So when it looks for ls, it'll check every single one of these directories. I have a lot. I'm on my Mac. I have all sorts of stuff installed, but it will go through each one until it got down here. It found ls and then it executed. That's how that works. That is something your shell does for you. I can modify path. I could set path equal to bin, colon, sbin, colon, blah, blah, blah. I'm not actually going to do this because then I'll probably forget to unset it and it'll be super annoying. But this will get set probably for you automatically by your shell. But if it doesn't, you can modify it yourself. Super useful to know about. Definitely something to be aware of. This can happen if you go to run a program like ls. Imagine I typed ls properly and see how I get command not found. If you're running a command, you know that should be there. You're trying to ls something that says command not found. Your path is probably messed up. You should start looking there next. All right, so can you believe it? We haven't even talked about scripting yet. We're getting there, I promise. Don't worry, I'm trying to go slow, and hopefully you're able to keep up with this. And again, if you're thinking this is too beginner for you, don't worry, there's gonna be timestamps you can jump ahead. If you're thinking this is too advanced for you, I'll try to slow it down a little bit, but we're going to keep moving forward. So we've talked about variables. We have $path that is built in to bash. It is an environmental variable or an environment variable. It'll be accessible to other programs. I'll demystify what that means later, but we can echo it like this. I put double quotes around it. I'll explain the importance of that later, but for now, I may or may not put double quotes around it. I'll try to explain what it's important. Yeah, just be aware right now, whether I put them there or leave them out isn't going to make too much of a difference. But when you are scripting this, and again, I'll talk about this later, just put the double quotes around it. Be safe. There's some weirdness that can happen if you don't. So we have path, and we can translate things. We can turn the colon into new line. We could also turn every B into an A. I don't know why you'd want to do that, but now instead of bin, we have ain. Super weird, but that's like the power of the translate command. We could technically join those two commands together. We could change colon B to new line A, and it would have the same effect. So you can just join things together. Again, don't know why you want to do this. ABC could become XYZ, and now every A became an X, every B became a Y. So super powerful command, super useful. More variables, I want to talk about this. So we have the pwd command, which can print our working directory. We also have the pwd variable, which does the same thing. It expands, meaning when the variable is turned into what data is inside it, it expands to the same output as the pwd command. There are a couple other ones. We have user. So the user that's logged in is Dave. That's who I am. There's another command in your system called who am I. This will tell you the user you're logged in as. Who am I, of course, is an external command. So it's there, it's on your system, but you can just run this and bash can do it in a built-in way without having to fork an external command. We also have $shell. This will tell you what bash you're running specifically, so what shell has been invoked. So I'm running a bash version that's out of Homebrew, which is running on my Mac. We also have echo hostname. So this is the hostname of your machine. So my machine that I'm running on is called studio.local. There are some other ones. I think you can do like machine type. Yeah, so you can see that I'm running on like an Apple system. So these are built in. This bash will initialize these for you, and you're free to expand them in your own scripts or on your own system, however you want. The other thing here is that we can set our own. So I'm using all caps variables, so those are pretty much set for me and not intended to change, but I can just make anything equal anything. So name equals Dave. I've created a new variable, and its name is equal to Dave, and it will exist so long as this bash session continues to exist. So now I can just echo name, and there you go. I could echo $foo, and there's nothing there because we haven't set foo. Foo equals hello. Notice the quotes, they're optional, you don't technically need them. We could echo foo now, and it prints hello. That's pretty neat. If we echo hello, space, 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 world, and then we echo $foo, notice that I got rid of the multiple spaces. This is why I'm stressing the importance of double quoting your expansions. When you double quote them, it won't get rid of spaces in a weird way. There's technically defined reasons why it gets rid of it, and you can use it to your own benefit, but I stick to always quoting your expansions like this because then it will retain the original data perfectly as is. Most of the time, that's what you want. There may be sometimes you don't want it, but we can talk about that. That's more advanced stuff. We have all sorts of fun stuff here. We can set foo equals to nothing, and it will set foo equal to nothing. You can alternatively unset it. So I can just run unset foo, and then, hey, it's unset. That's super cool. Super easy way of just unsetting a variable when you're done using it. So I'm going to show you a little bit more, and it's going to kind of blow your mind if you've never seen it before, but it's super useful. It's super awesome. Remember I showed you the who am I command? It prints Dave. Well, I also have like the uname command, and it prints Darwin. So this is the name of my system. I can run uname -a, and it prints all sorts of stuff. It prints like, I think the data was booted, the version of the kernel I'm on. It prints all sorts of fun stuff, everything that's in uname. That's super cool. But remember how I was talking about variables here? We could store this in a variable. So we could say thing, name of the variable, equals, and we're going to use backticks or grave marks or the thing all the way to the top left of your QWERTY keyboard. And now we can specify uname equals a, or uname -a right there. And now we have a new variable, echo thing. And there's the output of the uname command. Now here's the thing, that syntax is a little bit older, and for the most part, I would consider it legacy. I don't really see many people using that syntax much anymore. It's been replaced. It was replaced by Bash, and now I believe it is POSIX to use this. What that means is instead of using the backticks, because it can get confusing when you start nesting them, you use this syntax instead. You $ open a parenthesis, and then you close a parenthesis. Anything that goes in here will get executed the same way. So uname a, we go ahead and echo thing, and it works just the same. Prefer this syntax where you can. I would stay away from the grave marks or the backticks or whatever you want to call them. I have a longer form video on my YouTube channel where I talk about the difference between the two, and I kind of go into the specifics. I won't go into the specifics here. I'm just going to say for the sake of the course, we are just going to put that here. If I do mention other YouTube videos that I've made where I talk about some of this stuff more in depth, don't worry, I will put that on the course website. So go to the course permalink and you will have a list of all the references. Any video I talk about, any sort of document I talk about, I'll have a list there, a link with a list with a bunch of links so you can go find all that stuff so you don't have to write down stuff as you're following along with this course. All right, so cool. Now we know some basics about variables and we know how to store command output in the variables. Super useful. We're going to switch gears a little bit and we're going to talk about a text editor. We're actually going to start editing some text so we can start scripting. Can you believe it? We're almost scripting in this course. So first things first, we are going to use Vim to script for this. Don't be scared. If you've never used it before and you've heard scary things, I understand why. I'm going to give you a very quick Vim crash course. That is what I'm going to use for a text editor during this course. If you don't want to use it, if you're more comfortable using Nano or you want to edit it through some sort of GUI editor, that's fine. That's on you. You just have to translate everything I'm saying to match your environment. I am going to be focusing on Vimming this file. So if you've never used Vim before, that's okay. I'm going to teach you. We're going to get going. So hopefully your system has Vim. If not, you might have VI. I would recommend installing Vim. So if you're on like a Mac, I think you have Vim by default on Mac. If you're on a Linux system, you might have to apt install Vim or whatever your Linux system has to pull in Vim. So we're going to start by Vimming file.txt. Okay, so we are in Vim and here is file.txt. A lot like less, we can move up and down with our arrow keys and we can move up and down with J and K. That is because Vim is in normal mode, aka navigation mode. We are in the mode where we can jump around the file. We can't make changes to it by typing in. We can't insert text. We can make changes to it, but we can't type in things, but we can use the arrow keys to bounce around. When you're ready to add something, you can press I, and now we are in insert mode. And you can see in the bottom left, it says insert down here. Your Vim might be slightly different than mine. Now I can move the cursor all around and I can start editing just like a normal text editor, like, hello, how are you? Enter. This is a normal text editor. Enter. So I'm just entering text like that. That's all well and good. And now when it comes time to save this, like let's say, okay, I'm done, LOL, I want to save. We have to go back to normal mode and then we have to issue the command to save the file. So escape, the escape key will bring you back to normal mode. Notice that it switched to normal mode. It lets me know down here. And now we are going to write the file and we're going to quit the file. So colon to send a command, similar to how Les had a colon down there. We have a colon in the bottom left waiting for a command. We're going to give it the command W, which is write, to write the file, and hit enter. Now we have written the file. We have saved the file. And now we can do colon Q to quit. And there you go. You successfully exited Vim. It's not that hard, right? See? It's not that scary. Hopefully you're not too scared about it. If we cat file.txt, hey, look, there's our changes in there. That wasn't too scary at all. Let's go ahead and reopen it. So up and down, I use J and K to bounce around. That's all good. H and L will move left and right. I think they're, yeah, H, J, K, L. H and J? Sorry, I'm translating on the fly here. I'm assuming most of you people watching are using QWERTY. I'm typing in Dvorak, unfortunately, so I have to like do some mental translations with this stuff. I am very sorry about that. The arrow keys are also the same as on your home row, which is H, J, K, L, I believe. I don't remember which one is up, down, left, right, so you're gonna have to do it yourself. I just know where they are on my keyboard, and they are in super weird places, but H, J, K, L is how you do it. You can also just use the arrow keys. That's totally fine. So again, you hit I. Now we're in insert mode. We can go here, and we can start making changes. I'm just hitting enter and typing in text. That's fine. Let's clear some of these changes. I'm throwing in a lot in here. So we are going to get rid of these new lines that I put. So again, you could go into I, which will bring you into insert mode, and then you can just start deleting lines like this. All right, so I don't have time to talk about all the fun shortcuts with Vim. I can just give you a little bit about them. I would recommend if you want to learn this text editor, you're not comfortable with any text editor in general, take the time to learn it, okay? Go find like a course out there or something on Vim because it's super awesome. It's one of my favorite text editors. But if you're comfortable in a different editor, that makes total sense. So for instance, I'm in normal mode here. If I didn't like this line here, I could hit DD and I just delete that line. It's just gone. DD, delete that line, it's gone. Period, delete that line, it's gone. Why? Because period replays the last command I gave, and the last command I gave was DD. So period, period, those lines are gone. I could DD this line here, and I could hit P to paste, and I paste it there. I basically cut and paste. I could YY to yank that line, and P to paste, P to paste, P to paste, P to paste. Oh, I don't want these here. DD, DD. So there are some useful commands. There's a bunch of things you can do. If I go into insert mode, my cursor is on top of the E. That's kind of annoying. What if I went into insert mode, but put my cursor on a brand new line? You can hit O to do that. So what I did is I put my cursor here, I hit O, and now it put a brand new line, basically hitting return for me. And now I can type here, I'm already in insert mode. That's great. Shift O will do the opposite. It'll move your cursor to the top. That's super useful. So I can type here. I hit escape and DD. That's how I got rid of that line so fast. So I might be moving kind of quick here, but the point is you got to have some sort of text editor you're comfortable using. Hopefully I gave you enough here with Vim to kind of get going. It's a little bit scary if you've never seen it before, but when we're done with the file, you can combine the two things together down here, WQ, and that is right quit. And now we've saved the file and we've exited here. So if you do find the mode stuff to be a little bit confusing, I think an analogy that could help is normal mode or navigation mode. You could think of this whole thing like a video game, and think of normal mode like the menu. We're in the menu right now. We can't insert new text. We're not actually in gameplay mode. We can just make some changes. We're like at a debug screen. We can make some very high level changes on this file. I could just trash these lines, or U to undo, hit U, and it just undoes it. I can make very big sweeping changes. But then when I hit I, now I'm in insert mode. I hit the wrong button. Now that I hit I and I'm in insert mode, now it's like a video game. Now I'm just typing, LOL. And then when I hit escape, I bring back up that debug menu, and we can make whatever changes we want to this file. So hopefully that's a good way of thinking about it. Hopefully this isn't too much, this isn't too scary. But yeah, so let's continue. Now that we have this, let's go ahead and make a script. You guys ready to make our first script? It's been a long time coming, but I think we're here now. Let's go ahead and vim script.sh. This file doesn't exist yet. We're going to create it. So there we go. We've created a brand new file down here. So let's go ahead and start putting in some code, because a bash script is just commands. We've been running commands. We could put ls in here and escape :WQ. We're going to right quit the file. We're going to save it. And now we've written our first bash script. Like, I'm not kidding. We've written our first bash script. We could run bash space script.sh and run it, and it ran ls. A bash script is just a series of bash commands that run. That's it. So technically speaking, we've written a bash script. Technically speaking, an empty file is a valid bash script, but we don't need to get existential here. So let's go back into that file. We can do all sorts of stuff here. So we run ls, but we don't want to do that. We want to do something like name equals Dave. Hey, that looks good. Number equals 12. I don't know. Number 12 looks like you. So now we can echo, hello, Dave. There we go. That's awesome. We're not going to use the number, but we're just going to echo hello. No, that's not right. Sorry. Hello name. That was a mistake. Oof. Wow. Almost ran that. So we have name equals Dave, number equals 12, and we're going to print hello name. So let's go ahead, :WQ, run bash script.sh. Hello, Dave. Hey, look at that. We're writing a bash script. That's super awesome. There's all sorts of stuff we can do there. Your number is number. There we go. So we're giving it to the echo command. We're using variable expansion around name and number. Go ahead and :WQ that. I'm pressing up to go back through my history, run bash script. Hello, Dave, your number is 12. Hey, this is super easy. This is super awesome, right? This is incredible. Of course, there's more to it that we can do. We could go back in here and we could say system equals uname. And it's going to yell at me because of this syntax. I'll explain this in the next chapter. Just ignore Vim. Vim's being a little bit corrective here by saying this is invalid syntax. It's going to be fine, but I'll show you why it's yelling at me. Hello, name. Your number is number. Your system is : system. There we go. So let's save that. Let's go ahead and run that. Hello, Dave. Your number is 12 and your system is Darwin. So, you know what? I'm realizing it might be useful if I keep the script up at the same time. So I could cat script.sh and I could run script.sh. I'm going to use another command I have in my system. It's called bat. I have installed this one myself. It is a Rust tool and it's like cat but with syntax highlighting, so it's super nice. So let's go ahead and leave that up while I run this so you can look at both the source code and the output of it. Your number is 12, your system is Darwin, and that's the output of the uname command. Hey, super simple. That's awesome, right? All right, so now we're going to talk about a couple things here, but we're going to focus on file permissions and do we actually need to call bash in front of script.sh? Because you've probably seen people run it differently. You've probably seen people run like script.sh with a /, right? And they don't need bash in front of it. So what's going to happen if we run that? Oh, we're going to get permission denied. That's why we're talking about file permissions. So let's go ahead and show the permissions of the script. So if we ls here, we have built-in.text, file.txt, and script.sh. Let's ls-l. L is long listing, and it will show you a lot of metadata. So we can see the permissions are here. It's owned by user Dave. It's in group staff. Here's the size of the file, and here's the time. Look at that. Here's the time at which I was recording this course. How fun is that? There's some behind the scenes for you guys. So we can see we have 3 files here, script.sh. It does not have the executable bit. It would show up here. It would have an X here if it were executable. We have to make it executable. I won't deep dive too much into permissions. There's a whole bunch of stuff here. This is like Linux or Unix fundamentals. I'll just talk about the stuff that we need to get scripting off the ground, okay? So we need to give it the executable bit. We can use the chmod command to change the permissions of the file. We can use +X to say, give it the executable bit, add the executable bit, and then we can give it script.sh. All right, something got messed up there. When we ls-l again, you can see that script is actually highlighted now. That's pretty cool. And you can see that it has X's here. So it is executable. These permissions equate to 755, if you've ever seen that. Technically speaking, I don't want to confuse you guys too much. You could run chmod 755. This forces the file to be those permissions. So ls-l, you can see it's there. I won't talk too much about permissions. Like I said, +X, script.sh. Now we've added the executable bit. So now it's there, we can run this. And it says, hello, Dave, your number is 12. Your system is Darwin. But there's some magic happening here. And this is the thing about it that's kind of weird, kind of strange. And I don't love it. It works, but it only works because we are currently running in bash. So that program doesn't actually have a shebang at the top of it that tells our system what to execute it with. So we're going to add a shebang up here. You may have seen this. It's a £, and an exclamation mark, or an octothorpe and an exclamation mark. It's a hash and a bang, a shebang. And now we tell it what program to use. So I'm going to say user bin env bash. Commit this to memory if you have to. This tells it that it is a bash script. I have a whole video where I talk about shebangs. Shebangs are weird. They are different on different operating systems. Some people prefer this. I have a whole video on why I don't like that for bash scripts and why I prefer this. I will link it at the end for you. But for now, we're just going to make it this. So let's right quit that file. Let's save it. And if we execute it, this time it'll still work. We expect it to work. That's great. When I open it in Vim, look, the syntax highlighter is happy because it knows it's a bash script. It's very specifically a bash script. So that's super nice. That is super awesome. And one last thing before we move on. This is a stylistic choice, but this is a choice that I choose to make. You will see a lot of scripts out there in the wild that end with the .sh extension. I don't love that because .sh typically to me would mean a POSIX script, which is not as featureful as bash. So there are some bashisms we are going to use that may not be supported there. So I've seen other people use .bash as an extension. I prefer to not use an extension at all because you don't need it. If I run file on this, it already knows that it's a born again shell script, which is what bash stands for. And it knows that because it peeks inside and actually looks at this shebang. So we have the shebang line here. This is how we know it's a bash script. I'm gonna go ahead and get rid of the .sh extension. And here's how we do that. We move script.sh to just script. There we go. So now we just have a program in our directory called script. We run it, and there we go. Super easy to work with. You don't need the extension. The file command still knows what it is without looking at the extension. We can still vim it and get the syntax highlighting without looking at the extension. The extension doesn't really matter. It's what's inside the file that matters. So this is how I'll be doing it going forward. Some people have different stylistic choices. This is my preferred choice. Okay, so let's actually start making some fun scripts. All right, what do we have here? We have built-in.txt, file.txt, and script. Let's go ahead and trash all of this. We could technically run rm star. Be so careful with this, please. Be very careful with this command, okay? Make sure you're in the right directory. Make sure you only have the files you think that you want to delete, okay? Otherwise, you could be deleting some really unknown files and it could be really bad. Let's go ahead and run this, and those files are gone. That's awesome. At some point, I lost the alias I set up for rm. I don't know why that happened, but see how scary RM can be? Oh my god, even I could have gotten messed up there. So be careful with that. But all I did was delete every file in that directory. So now we are in users Dave foo, and there is nothing here. Awesome. So let's get started. Let's make a new script, and we can call it hello. And hello is going to be very simple. We're going to start the script the same way we start all other scripts. User bin env bash. Look at that. The little pound sign, the exclamation mark, user bin env bash. Awesome. And now we can just echo hello. Hey. It's pretty simple, right? So let's chmod plus x that, run it. There we go. We are a bash scripting pro right now. That's the end of the course. No, I'm just kidding. I'm just kidding. There's so much more to go. I'm so sorry. We're going to dive into this. We're going to go crazy here. All right, so we have a hello script. That's super nice. It prints hello. Let's make another script. In fact, we could use this script as a template. The way we're going to do that, instead of using the mv command, which would move it, we don't want to move it, we want to copy it. So we're going to need the cp command to copy hello into a new script, and we will call this greet. So now we should have two scripts, greet and hello. They should both do exactly the same thing because they're carbon copies of each other. That's awesome. Let's go ahead and modify greet now. So we're going to vim greet, and we're going to see what we have here. So we have echo hello. Okay, that's pretty simple, but let's go ahead and make this a little bit more advanced. And the way we could do that is we could say name equals Dave, and very similar to what we had originally, we could print instead hello name. Okay, again, no trickery here, just starting off with some basics so we can build off of it. If we run greet, we get hello Dave. Hey, awesome, super simple. Let's go ahead and make a new one. And we're gonna get a little bit complicated here. We are going to make a loop. So let's cp greet into loop. Now if we ls, we can see that we have a third script loop. Let's go ahead and open that up. And we're gonna trash these dd, period, and they're gone. I'm gonna hit O, now I'm in insert mode and I can actually start typing text. That's super cool. So we can do a loop over things. And the way we do that is a for loop. If you've done like programming before, you're probably familiar with like for loops and things like that. So we're going to do a basic for loop. And the nice thing is the for loops in bash are very much for thing in list or for thing in array. So it's a for in loop. So we can do for thing in, and then anything we put here is the list. Might sound kind of confusing. For thing in foo, bar, baz, bat. Semicolon do. That's important. We have to put the do keyword here to let bash know that we're opening a loop. And now when I put insert on a new line, I'm already indented. As you can see, I'm already indented. My syntax highlighter knows that the next line should be indented. We are inside the loop. We could say echo thing is $thing, and then we can close this loop. Now that we have a do, we have to close it with a done. So we put a done there, and now we have a loop. This is a basic for loop in bash. For thing in foo, bar, baz, bat, thing is $thing. Hopefully this is straightforward. There's no trickery here. Right quit, so :wq, save that. We don't need to chmod, it's already +x. I just totally did that out of habit. Let's run loop. There we go, perfect, look at that. I'll show you the source code real quick. If we bat loop and then we run loop, here's what's going on here. For thing in foo, bar, baz, bat, echo thing is $thing, thing is foo, thing is bar, thing is bat, thing is bat. Very simple, very, very easy to understand. So that's pretty cool, that's pretty awesome. And before I jump on to the next topic, I want to show you something really, really cool you can use. Something cool to keep in your toolbox. This is super useful. Bash -n. bash minus n is a syntax checker. It is just a syntax checker. It does not do anything else, which is super nice. It will syntax check a file for you without executing it. So we can do bash minus n on loop, and we get no error messages printed to the screen. That's how we know it was successful. I haven't talked about this yet, but we can also check to see if the command was successful by looking at its exit code or its return code. I talk more about this in the future, but if we echo $? This is a variable that will be the exit code of the last command that was run. So 0 is success, anything non-zero is failure. So it was successful. Look at that. It was successful. Super easy. Of course it was successful. If we were to have a syntax error in loop, imagine instead of done, I wrote end. End is incorrect. Maybe I'm writing a lot of Ruby lately or something. End is wrong. So if I go ahead and I save that and we run bash minus n, look at that. Syntax error. Unexpected end of line, file 4, blah, 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 command line 3. It gives you a bunch of information about it. Tells you there was an error. That's awesome. Echo $? Non-zero. It was a failure. So bash minus n is something to keep in your tool belt, something super useful for syntax highlighting, not syntax highlighting, syntax checking your bash script. So now if we do this, there should be no error. I spelled it wrong. There should be no error here. We run that and we get a 0. Hey, that's awesome. All right, so now let's talk about taking input. Okay, we have our basic scripts here. We have greet, hello, and loop. We can actually modify them to take input, which is super cool. All right, so let's start with our, what is it, hello script, I think? Just echoes hello. Okay, that's super simple. Wouldn't it be nice if it said hello name, just like the other script does, but name was something that came from the user? Let's go ahead and add that. So we have hello name. We just have to define name. We can use the read command. Read is built into bash. You can do type on read, and you can see it's a shell built in, and there's a whole bunch of arguments that go with it. I'm not going to make you read through all these. I'm just going to tell you how they work. I'm not going to make you read through them, and it's called read. Get it? Yeah, I'm hilarious. So we're going to do read -p. This is a prompt. So let's go ahead and say enter your name, space, and then the name of the variable we want to save it into. We want to save it into name. So there you go. Super simple. Here's what our script looks like. Read, enter your name, saves into name, and then we echo hello name. So let's go ahead and save that, and let's run it. Hello, we'll run this. Enter your name. Dave. Hello, Dave. Hey, that's pretty cool. Enter your name. Johnny. Hello, Johnny. That's pretty cool. What about pipelines? We've talked about pipelines, right? I can echo Dave. Can I pipe that into our program? We can. This is crazy because there's no prompt. Notice this. This is already very complicated. I don't know how many bash courses that would start with this, and probably for good reason. There was a prompt here. We had to actually open up standard input and say, hey, let me get some information, because there was no information waiting for me. In this example, it's a little bit different. The information was already waiting for you, so there was no reason to prompt. You could just go right past this. So this is an old little like Unix trick or like Linux trick. You'll see a lot of people do this. There'll be some sort of software. Just imagine like my fake software or whatever. There'll be some software that has a bunch of questions and it'll ask you multiple times, like, do you want to do this? Do you want to do this? Do you want to do this? And you get sick of it and you're like, yeah, I just want to hit yes. I just want to hit yes for every possible option. That's why the yes command exists. Duh. The yes command just spams your screen nonstop with Y. So you could pipe yes into something like hello. And it will just, in this case, only read it once, but every time it reads new information, it will just get Y and a new line. So, so if you ever have software that prompts you 8,000 times, you can pipe yes into it. You probably shouldn't. You probably shouldn't, but hey, it's your computer. You paid for it. Do whatever you want. All right, so let's look at our hello script, and we can see this here. Let's comment this out just so this code won't run. And let's do something else. Instead of reading it, let's say name equals $1. This is a special variable, and I haven't talked about it yet, but this is an argument. So this will read the first argument to the program. So if I run hello and I give it the argument Dave, it'll say, hello, Dave. If I give it Steve, it'll say, hello, Steve. If I give it nothing, it'll happily just print nothing. So that's cool, but could we make this a little bit better? And the answer is, of course, yes. We can check. We can check if the user actually gave us something as $1, and we can make an informed decision based on that. So let's do that. Let's say if $1 is set, then, and I'm going to pause right here because I just threw a bunch of syntax at you, okay? Bash has if statements. Here are how if conditionals look in bash. It's if something, semicolon, then. That is what an if statement looks like. Oh my God, I can't type. That is what an if statement looks like in Bash, okay? It's if, and then something goes here. The something that we are putting here is double brackets, a -n, and a $1. I will explain these more in greater detail later, but -n says, is this variable set? So we're looking to see if $1 is set. If it is set, then we will use it. I'll move this code up here. If it's set, then we will say name equals $1. If it is not set, we could put an else here. Let's read that from the user. Let's go ahead and uncomment this line. So if it's set, then we will use it. If it's not set, we will read it from the user. Now let's close the if statement. Are you ready for this? The dumbest thing you've ever seen. FI. That's how we close an if statement in Bash. I'm not lying to you. That's really how you do it. Let's trash this line up here. We don't need it. So if the first argument is set, then we'll use that as the name variable. Otherwise, we'll read it from standard input. We'll prompt the user for it. So let's go ahead and run hello, and let's give it John. Hey, it worked. That's great. Let's give hello nothing. Dave. Hey, it worked. That's great. That's one way to read from standard in, and we can also read from arguments. So that's pretty cool. That's pretty awesome. All right, so here's one of the cool things about Bash. As you can see, we have this double square bracket notation. You might be like, okay, I've seen that. I'm not really sure exactly what it does. It's Bash. You can get a help page on it. There you go. There's your help on the double square bracket expression. It talks about all the different types that's going in there. Don't worry, I'll go over all this stuff as part of this course, but you can even do help on a single square bracket notation, which is a synonym for the test built in. So we could do help test, and get ready. There's a lot of things we can do here. We were using -n, which there's a whole bunch of stuff here. String operators. -z, true if the string is empty. -n, true if string is not empty. So you could use -n or -z, whatever one you want. You can negate it if you felt like it. We use -n. We wanted it to be true if the string is not empty. So we'll talk more about that as we go forward, but if you want to look this information up yourself, that's how you do it. You use the help pages, and you can do help on double square bracket or help on test. There you go. All right, so the next thing we can modify is the loop program. So you remember how it takes foo, bar, baz, bat? Let's go ahead and just get rid of all that stuff there. And let's change it to, let's quote our variables because we're being good. $1, $2, $3, etc. I don't feel like writing them all out. So let's go ahead and run this and see what happens. We run loop, and we can see thing is blank, thing is blank, thing is blank. Well, that's not great. I could put like 1, 2, 3 here, and it works. I could put 4 here, and it's lost. That's not fantastic. That's not great. Is there a way to loop all the arguments? Well, of course there is. So let's go ahead and pull that file back up, and let's change this to, instead of $1 or 3 or 2 or whatever, @. The @ will expand, as long as it's quoted, will expand to be an array of all of the arguments. So this is super useful because I can run loop like this, and hey, it works. That's awesome. I can get rid of 4, and now it only runs 3 times. I can get rid of these 2. Now it only runs once. That's awesome. Now it doesn't run at all because there was nothing in the array. Perfect. That's awesome. That's what I want. When you take arguments in your script, you can either name them explicitly, you can use like $1, $2, or you can just use $@ and you can get an array expansion of all the arguments. Even if none are present, it will just expand to an empty array. All right, so let's circle back. Let's see what we have here. I think we have the greet command that just hard codes the name to Dave. That's awesome. We don't need any more. Let's go ahead and get rid of it. So we RM'd it, we ls, and we have hello, and we have loop. So if we look at hello, that's the one that takes the argument as $1, or it reads it over standard in. Hey, that's pretty cool. So let's go ahead and we're going to learn about functions now. So let me show you a simple example of why you might want functions in Bash and how you can use them. And to show you this example, I'm actually not going to use functions, and I'm going to show you why. All right, so now we have this hello script where we can give it a name like Dave, and it prints hello Dave. That's great. Could we say hello to multiple things? Because if we do, Dave, foo, bar, baz, it doesn't care. It just prints hello to Dave. There's actually a couple different ways to do this, and I'm going to show a couple different examples. So let's make a new program. Let's make a program called Greeter. All right, so Greeter is a brand new program. I'm not copying over the other one, so I'm just writing this from scratch. So let's save that, chmod plus exit, because we want it to be executable. Let's go ahead and vim Greeter. So we could do for name in, if you remember this syntax, $@, which are all the arguments, do, done, and then here we put what we actually want to run. So we could, echo hello name, But we already have a program that does that, right? We already have the hello program. We can do ./hello. Remember, dot is our current directory, /hello. So notice that we're using ./hello here. If we just had this, it's going to look into all our paths. Remember that .path variable from earlier? We don't want that. We want to run the hello script that's in our current directory. So dot is our current directory, /hello. Now we can give it a single argument of name. So this is a script calling another script. This is one of the beautiful things about scripts, is scripts can call each other. So we can run greeter. Nothing runs because I didn't give it any arguments. We can do greeter foobar baz, and now it says hello to foobar baz. It executed that script on foobar and baz. How cool is that? Now the reason I use that example is because ./hello is an external program. It doesn't need to be its own program. We're technically relying on another script that we wrote. We could rewrite it, and we could rewrite it in here as a function. And this is the power of Bash when it comes to functions. They are mini programs. This is how you should be thinking of functions. You should be thinking about them as mini programs because that's what they are. So we'll define a function called greet. We'll do that by using greet, open and close parentheses, open the curly brace, close the curly brace, and now we have a function called greet. So greet will take an argument. Let's say the name equals $1, and then we will echo hello name. So no different than what we've been doing currently. We go down here and we swap out ./hello for greet. We call it no different than how we would call an external program. We just call greet. It finds out that it's a function on top. It looks for name equals $1 and it prints hello name. Super simple, super easy to work with. There's one thing before I run this I want to make you aware of, just because it will bite you if you've never seen it before. This name variable is technically global. So when I set name equals $1, it's overwriting name down here. Now they are set to the same thing, but it is technically a global variable. When you are in functions in Bash, you want to use the local keyword. If you use the local keyword, then you're saying, hey, I actually don't want this to exist outside of this function. So you can do that without polluting the global namespace. So remember to put local in front of your variables in Bash like this. So let's save this and let's run greeter. Let's rerun it with foobar and baz. Hey, it works. We get the exact same output that we wanted because it's running the function. We could say hello name from func. And if we run it, we can see that we get from func because it's running from the function. So that's perfect. That's exactly what we wanted. We have made our own little program. We don't even have to do a for loop here. We could just say greet Dave. And then if we just run greeter, it will always end with a greet Dave. So if I do greet, foobar, it'll be foobar Dave. Cool. Awesome. And something to be aware of with functions. Functions, again, they are like mini programs. So they output to standard output. They emit data to the screen as you're seeing there. We are free to write this to a file if we wanted to. We are free to store this in a variable if we wanted to. So let's go ahead and do this. Let's append these to a file, the ones that come from an argument, and then let's put the greet Dave in the variable and then say var is var. So let's go ahead, let's save that. Let's put the source code up here because I know there's a lot going on, and let's run greeter foo bar baz. So as you can see, nothing got printed here. So the data went from this for loop with this greet command into file.txt. As you can see, it's here. We use the append notation. And down here, we set the variable var equal to greet Dave. And then we said var is var. So we have var is hello Dave from func. So this is one of the powerful things with Bash. We can just sort of move data around. We can treat functions like they're little programs. So we can pipe them. We can redirect them to files. We can store them in variables. We can do all sorts of fun stuff. The last thing to keep in mind here, I'm going to delete this line before we don't end up, I don't want to trash that file anymore. The thing also we can do is, yeah, we have the output of it. That's great. But we can also check if it failed or not because it's like a mini program. So it has an exit code. It technically will return successful here because it will return whatever the last command is. The last command's echo. Echo will be successful, so it'll return success. We could manually return success here with a return 0. Return is a keyword that only works inside a function. So if we ran this, we can see that the 0 is at the bottom. If we change this to return 5, We get a 5 at the bottom. That's a failure, okay? So this is super useful. This is how we can get data out of the function. You know, we can save it into var, but then we also have $? So we can get the return code. This lets us know if it was successful or if it was not successful. So something to keep in mind, something to be aware of, something really powerful when it comes to bash functions. All right, so next thing, let's talk about conditionals in bash. Okay, you know, we have the if statement, other things like that, but we have the conditionals that go inside them. So let's go ahead and make a new script called conditionals. Conditionals, make sure I can spell. All right, user bin env bash. You should know the drill by now. I'm gonna right quit this file, chmod +x, give it the executable bit so we can run this file. There's nothing in it, but it runs because it's a bash script with no commands in it, so it'll successfully do nothing. Pretty cool. Let's do some stuff here. Let's say a equals 2. B equals 2. We have two variables. They're set to 2 and 2 respectively. We can check if $A equals $B, then echo A and B are the same. I'm going to use single quotes around this. Technically speaking, you don't need to quote this. I'll just show you real quick. You could put double quotes here, you could put single quotes, or you could put no quotes around here. Double quotes are useful because they will allow variable expansion inside it. Single quotes are useful because they will not allow variable expansion in it. Not quoting your strings is great for quick and dirty hacks, but if I do things like multiple white spaces, as I showed earlier, it'll be lost. So if you see me not quoting things that I give to echo, it's because it's quick and dirty. Otherwise, you should be using double quotes or single quotes. In this case, we're not expanding any variables, so I'm going to opt for single quotes. So we'll put we'll put a phi there, phi, if backwards, whatever you want to put there. So there we go. I have a simple command here. Let's go ahead and run that, and we can see that $A and B are the same. Oh, I forgot I left the $A in there. Whoops. Let's rerun that. All right, there you go. A and B are the same. Hey, that makes sense. That's super simple. That's really easy to figure out. Let's go ahead and copy this. So we're going to change this to C and D, and we'll make this one 2 and this one 3. So they are not the same. If we want this conditional to work, we have to either negate this conditional. You could put an exclamation mark there if you wanted to, or you could just say not equal. A and B, they're not A and B. C and D are not the same. So again, this one should fire. This one should be accurate because they are not the same. And I'm stupid. I put $A. Yeah, this is what I get for copying and pasting code. So $C and $D. There you go. So I'll put the code back up here so you can see what I'm referencing. And then we'll run this and we can see A and B are the same, C and D are not the same. That's good. That's what we expect. So we can use the equal sign, or we can use the not equal sign. Very similar to other programming languages if you've ever seen it. The nice thing here is that this double square bracket notation has a bunch of stuff in it. It can check things about files. It doesn't have to be logical conditions. It can be other things. So let me show you what I mean by that. Let's reopen up conditionals and let's add a new one here. We can say if -f file.text, then echo file.text exists and is a file. So -f checks to see if a file exists and that it's a regular file, so not a directory, not any other sort of weird thing. We can just run this and we'll see that it exists and it is a file because file.text is there. That's awesome. Let's RM it. Now if we rerun conditionals, it doesn't show up. It doesn't exist. Let's touch file.text. Let's put it back there and rerun it. Hey, it exists and it is a file. So this is the nice thing about bash. You can do help test to pull up all of the things it can do. There are all sorts of things you can check. Like we're checking if the file exists and is a regular file. You have -e just for if it exists, -d for a directory, B for block special. Like there's a ton of stuff you can do. S is a cool one. It has to exist and it has to not be empty. So definitely some unique things you can do here. So another cool thing about this is these conditionals I've been talking about. Yeah, there's an if statement, but there's also a while loop. Like bash has while. So we could say while -f file exists and is a file, sleep 1. So we're going to cause the program to sleep for 1 second. And then we're going to put a done down here. What do we need? We have, wait, why is this wrong? Oh, it's wrong because if you make a while loop, you don't put then, you put do. And then to close a while loop, you need done. This will probably trip you up. It's okay. It still trips me up. So let's go ahead and trash some of this stuff we have up here. So Shift V in Vim to highlight like this. I can move up and down, and then I just hit D and I delete it. So while that file exists and is a file, echo file is gone. So what does that mean? What's happening here? While this exists as a file, we're going to print that it exists, and we're going to sleep for 1 second, and we're going to go back to the top, and we're going to check again. So as long as that file is there and it exists, it'll still just do this. Now, why is that interesting? Because here's the fun thing. I'm going to pull up another terminal. It's a little bit small. I apologize for that. Let's go into foo and let's rm file.txt. We're not going to stop the program. We're just going to rm file.txt. And look, it stops. It stops because that while loop stopped being true. That file no longer exists. So these conditionals, these double square bracket things, you can put them anywhere. You can put them in an if statement. You can put them in a while statement. Technically, bash does have an until loop, which is the opposite of while. So I could say until it's a file. So until that file exists, we will print that the file does not exist. And then we can say file exists. So until is the opposite of while. I rarely use until. I kind of just will negate a while. So I could just run this and it will say file does not exist, file does not exist, file does not exist. So again, same deal. Sorry for the slow or the small font size. I could touch file.txt and then that will stop that from running because it checks to see if file.txt exists. So yeah, until exists, while exists, if exists, they all take the same kind of notation. You can use the double square bracket notation for conditionals. But the thing is, they don't have to be like that, okay? You don't actually have to give it the double square bracket notation. You can put anything there. So I can say if, and then some sort of command. I could do if ls, then echo ls worked, fee. So that works. I don't know why you'd want to do ls as an example, but this is just an example. So this is ls printing all the files there, and then it said ls worked. So you could put any sort of command you wanted to put here. If echo hi, so if we were able to successfully echo hi, then we'll echo ls worked. Well, that's kind of wrong, but if statement was true. So this is kind of useful. It's kind of cool. We could put an else here. We could say echo if statement was false, so we can kind of just know what's going on here. This is just a command, and there are two commands that are built into your shell that are super useful. Ready for this? True and false. True is a command. It's built into your shell, and it returns 0. It just returns a successful execute. False is a command. It exists in your shell, and it returns non-zero. It returns a failure. So if we were to look at our conditional script again, we can see if true. So that should always be true. If statement was true. Hey, that's awesome. Let's modify this and change true to false. If false, then we should get false. If statement was false. So yeah, those two commands exist. They are there for you. This might seem kind of strange, but if you're on like a Linux system, you could do something like if apt get update, then we were able to update. Otherwise, something failed. Just as an example, you can just put commands in there to see if they work. So interesting, super useful, something to keep in mind. The flip side of this is also true. The double square bracket notation does not have to be in an if statement or a while statement. It does not have to be the conditional. I can just do it here. I can say, does file.txt exist? It's 0, so it does exist. It is there. If I remove file.txt and I rerun that same command and then I check its exit code, it was 1. It does not exist. So you can just run these like they're commands. You might see people chain them like this. It exists. So that failed. We could touch file.txt, rerun it, and it works like this. You'll see people chain them like this. Something to keep in mind that the if statements don't necessarily have to have the double or single square bracket notation, and the double or single square bracket notation does not necessarily have to be in an if statement. You could use the single square bracket notation here, or you could even use test -f file.txt. These two, I personally stay away from unless I'm writing a POSIX or Bourne shell script. I always use the double square bracket notation when in bash. It is a bashism. It's only for bash scripts, but I prefer to use it. It's more robust and it has more, it has better parsing rules. So more things how do I put this? Less things can go wrong if you use the double square bracket notation. So if you're going to write bash scripts and you need to use some sort of conditional, stick with the double square bracket notation. It'll just help you avoid weird problems in the future. And there's more stuff there to use. There's more conditionals to test with. All right, so next up, let's talk about for loops, okay? We're going to make a new file here. We'll call it for loops. Very simple, not really imaginative naming. bin n bash, that's all well and good. Let's go ahead and plus x that, vim it, and here we are. So we know the basics. We've seen this before. For name in foo bar baz do echo name is name, done. There we go. Very simple for loop. If we run it, hey, look, it works like that. Here's what it looks like. Here's what it looks like when you run it. Very simple. We've seen this before. We already know. So what's the next thing we can do with this? What's more interesting about this? Well, instead of names, let's make something else. Let's just call this thing, because thing is going to change. So I'm not going to tie it down to being a name, okay? So for thing in, we could do this notation. I will expand on this notation later in the course, but for now, look at this. A.f inside curly braces. What does that do? Well, you might already guess what it does. Look at that. It expands. It is a way of expanding text. It will loop through. This will expand into everything A all the way up to F, including F. So it's up to and including. So thing is A, thing is B, thing is C, blah, 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 blah. There you go. Awesome. This also works for numbers. Again, I'll go over more of the specifics of this later, but we can do 1.5, and we get 1 all the way up until 5. Super useful. It's a way of sort of expanding a range in Bash. If you're in Python, you used to like the range or the X range or something. I don't even know if those are still a thing. I might just be showing my age here, but this is kind of a similar thing to it. The nice thing is, or not so nice thing, is if we were to set a max equal to 5, and then we want to do 1 all the way up into $max, watch what's going to happen here. You ready? Uh-oh. That doesn't seem right. It didn't actually loop through them. It just printed the actual literal string. It expanded $max, but it didn't recognize that it was curly brace expansion. And that's because this syntax kind of breaks here. So I want to show you something right off the bat that a lot of people don't know about with Bash, but is super powerful, okay? I'm going to write this out, and it's going to look like I'm making up syntax, okay? Are you ready for this? Here's an empty for loop. For, open double parentheses, I equals 0, I less than max, I plus plus, do. This probably looks insane. This is a C-style for loop. What is it doing in my Bash script? Well, it turns out this is valid. This is 100% valid. You want to do math syntax or arithmetic expression in Bash, you need the double open parens. The double open parens, the double close parens. This tells it we're in math mode. We're going to set a variable I equals 0 at the beginning. We're going to constantly check the I less than max. Notice we don't need the $sign here. We don't need the $sign. We don't need to expand it. This special math syntax is aware of variables. And then we're going to do I plus plus. So if you've written this in like C or something, you've probably seen this style. And do you think it's going to work? Ah, it was so close to working. You guys see what I did wrong? Look, I called it thing and then I used I. Let's change that to I. So my big reveal was going to be that it works. And then it turns out it didn't work because I'm stupid. So let's rerun this. Hey, look, it works. I didn't lie to you. That is something to keep in mind. C-style for loops in Bash exist. They're fast, they're performant, they work, they're great. All right, so let's move on to the next thing. I want to cover input and output like we did before. Remember how we read in information from the user? We prompted them for information. We're going to make a couple little changes to that, and we're going to show how to read multiple lines of data from a user. So I think we have file.txt here. There's nothing in there. That's not great. Let's go ahead and just add some stuff to file.txt. Doesn't have to be much, just, foo, bar, baz. There we go. That looks good. And so we're going to make a script called read input. So read input, like all our other scripts, will start with the same little shebang at the top here. Save it, chmod, plus X, read input. People on my YouTube channel get upset that I run this over and over again. They're like, you should just have a script that automatically creates the file and makes it executable for you. Maybe I should, but you know what? I don't mind writing it over and over again. You get kind of used to it. So let's go ahead and let's read some data in, and we can just say echo, you said $foo. Notice we don't have the P here. We're not going to prompt the user, so this is not going to be that nice of a program. We're just going to know that it's asking us. So if we run this, that's not what I wanted. If we run, read input, we can see that it just hangs. It hasn't prompted us for anything, but it is waiting for our input. So we could say hello, and then it'll say, you said hello. Cool, that makes sense. Read input's very simple. It just looks like this. There is some weirdness with read, specifically around when you give it some backslashes. So if I were to say like, hello, \n world, you can see that it says you said hello N world. So it tried to interpret this. That's kind of weird. It can lead to some weird behavior. So what I like to do when I use read is I pretty much always give it the -R flag. So almost anytime I use the read command, I'm giving it the -R flag. If we look up the help page for read, we can see there's a lot of stuff here, but don't worry, -R. Do not allow backslashes to escape any characters. So basically you can think of R as like raw. It's just going to read in raw input. It's not going to do any backslash mangling. So if I said hello world, it gives me back the literal string with the literal backslash in it. So this is the truest thing to what the user has given us. And I like that. So let's go ahead and show this. So we have our, read input. We can put whatever here and it will just print it back to us. We could also echo whatever and pipe that into read input and we get the same thing. Hey, that's pretty cool. What if we did something like a really big file, user share dict words, remember this giant file, and we pipe that into, what do we call it, input? Read input, I already forgot. Pipe it into read input, what's gonna happen? We only get the first line. Read only reads the first line. You can modify that behavior by changing the delimiter character, but by default, it only reads line by line, and it will only read one line. It successfully read one line. There's more data waiting for us to read. We just never read it. So let's go ahead and make this read all of the lines. How can we do that? Well, we can take this thing and put it in a while loop. Remember how I said you can put commands in an if or a while statement? You can just do while read. There we go. We can change the name of the variable from foo, let's call it line. So while read line, someone would call this, I see this referred to a lot as a while read line loop. That's what it is. So we put our semicolon here, we put our do, that's how we start the loop. We put our done, that's how we end the loop. And we can put whatever body we have here. I'm gonna give you a quick little tip about bash. If you don't fill in this body, if you don't put anything in there, it's invalid. So you will get an error that is considered a syntax error. So if you're used to Python, you would have like the pass command. In bash, we can do true, or some people might even do a single colon. Single colon is just a command that does nothing. Bad example because it's just gonna hang and wait for, it's gonna have to go through and process that line by line. But the single colon is just like the command true. You can do help colon, null command, no effect. This command does nothing, always succeeds. So pretty simple command built into bash. You'll see it used a lot. But now that we have this, let's go back to our read input command here and let's echo we read line $line. So let's go ahead and rerun that, where's that? That cat pipe into read input. And as you can see, it's going through line by line and reading the data. So right off the bat, do you notice something? It's significantly slower to process a file line by line in bash than it is to just run it through cat and maybe pipe it to something else. So be mindful of that. Bash can read things line by line, absolutely. And it's not slow at it, but when you compare it to other tools, like if I were to pipe cat to grep Dave, very, very fast. If I were to go into this example and check like if line equal Dave or something like that, very slow. So just something to keep in mind there, but this is how you can read it line by line, and we can process it, and we can do processing on the lines one at a time, which is pretty neat. And again, there are a couple little gotchas with this. Notice that the read command is the condition of the while loop. This means while read is successful, meaning it was successfully able to read a line. This can be problematic if your data does not contain a new line. So let me show you what I mean. If I echo hello, it prints hello to the screen, but there's also a new line here. Notice that the prompt is on the next line. That's because it's part of the echo command. If I pipe this to something, let's say pipe it to cat -v. Actually, cat -v won't show us. Is it viz? None of these commands show us. These are not what I'm thinking. I'm going down the wrong path here. Let me back up. Let's pipe this to hex dump. Or on your system, you might not have hex dump. You might have OD, or you might have XXD. So there's a lot going on here, but all of them are basically the same. I may have lost you, but don't worry. We're just going to look at echo hello, and then echo hello pipe into XXD. And we can see that we have hello and a period here. This period is a character, but it's not actually a period character. Hello, H, that's 68 on the ASCII table. E is 65. LL, 6C, 6C. O, 6F. And then this one right here. This is hex 0A or decimal 10 or the new line character. I bring this up to let you know that when you echo hello, there actually is a secret byte there, and it's the new line character. So that's why you're getting that there. And that's why when I pipe it into read input, it shows up as its own line. If I were to suppress that new line, I can do echo -n hello. Notice how the prompt is on the same line as hello. There's no new line there. If I were to take this and pipe it to xxd, notice that the 0a character is missing now. If I were to take this and pipe this into read input, there was nothing. It lost that data because it didn't read a new line. That's because this checked that it was successfully able to run it. There are little tricks you can do. I've seen people do this where they say -n line. Basically, this is saying while we were able to successfully read this line, or the line variable has some data in it, then we can do that. So this is good because it will work because we were able to read the line. There wasn't any new line there, but just be mindful of this. If that's gone, we're going to read up to the next new line. So if your data does not end in a new line, it's going to be lost. But let's go back to our first example here. We have user share dict words. We can pipe that into read input, and hey, it works. This is the same effectively as running this. Let's go ahead and read input. Remember how we wrote data out to a file before? We can do the opposite. Okay, instead of greater than, we can use less than, and we can tell it to read in from a file. So we could put the name of the file here. What's the name of the file? User share dict words, and this will be the same thing. There is a slight difference here. Some people will note, if you've seen this before, this would be called a UUOC, a useless use of cat. There's nothing wrong with this, and in fact, when you're learning, I think it's super useful to see it this way. Pipelines are really useful. This is slightly different. We don't fork out the external cat tool. So remember, cat is an external tool. It exists on your system. We're not forking out cat and piping it to read input. There's no cat at all. We are just telling bash, our shell, to read in this data and give it to read input. So bash opens this file, bash hooks this file up to read input, and then bash runs read input. That's basically what happens there. Same effect, like effectively it's the same. I have a video where I talk about the useless use of cat and all different things about this. It's a rabbit hole. So again, like I said, it'll be mentioned in the references. You can check it out in your own time if you want to. So yeah, you can have this. Also, fun little fact, this syntax can be anywhere. So you could put it at the beginning like this. If you're like, oh, I like my file on the left and this on the right, you can do that. That's totally valid. Some people also don't put a space between the two. So again, this is also valid. It totally works. It's just up to what you like in your own personal preference. All right, so now I want to recap and go over what we have. I'm going to do things slightly differently now. And by that, I mean I am going to go to a script that I've already written. I'm going to open it up and we're going to walk through and talk about what it does. You can kind of think of this as like a little quiz, okay? So I have a bash course directory here that I've made. I have my own personal notes that I've been reading off of. And in here, I have a section for, that was the last one, IO, what we have. So in here, I have the notes that I'm reading off of, and I have a script in it. The notes are pretty boring. They just say nothing because the goal is to open the script and have you look at it. Go to the website. There will be a link to the GitHub. You can check out all this code there. So a lot of the code, like if I'm showing you scripts that have already been written, they're probably going to be there along with some other references. I'll check in code as we go. But this script, we're going to look over this together and we're going to figure out what it does. All right, so without further ado, let's go ahead and fire open Vim on 00-script. And here we go. There's a lot here. I'll give you a second to take it in. Otherwise, we are going to go through and we're going to talk about what it does here. I should have given you all the tools to basically have you equipped to know what's going on here. But yeah, let's walk through it. So you pause the video here if you want to figure it out on your own. Otherwise, I'm going to start going. There you go. First thing we do is we make a function called hello. The function called hello takes one argument and we call it s. And then we say hello $s. Very simple. You call hello and it will say hello to them. Then we create a function called goodbye. Takes another variable, calls it s, and it says goodbye $s. Okay, we have a hello function and a goodbye function. Remember, functions are like mini programs, so we will call them like they are mini programs. Cool. The next thing we do, I haven't talked about this. There's some weirdness going on here. But this is a new syntax. I will talk about this more in a future chapter. But right now it's very similar to the double square bracket opening, but there is a double paren opening. You've seen this before with the C-style for loops. This is arithmetic expression. This is for doing math expressions. And of course, it's bash. So we can say help, open parenthesis, and you can get all information about it. It will tell you that it's equivalent to let. So it's equivalent of the let command, but I prefer this double parenthesis notation, but you can do help let, And there you go. Here is everything you can run when you're inside it. There's a lot here. We can do, variable plus plus. We can do basic math operations. We can do exponents. We can do like modular division, remainder division. We can do bitwise operations. It's amazing what we can do in here. But the nice thing is, because it's math expression, we don't need to put the $sign in front of it unless it's certain variables. So in this case, we can't just put a £sign there because Bash would think we're commenting it out. So we do this $sign. I haven't shown you $sign yet, but I've shown you $@, which is the array of arguments. As you can see, we use it down here. $sign is how many arguments we were given. So we check. If $sign is 0, the user has not given us any arguments. We print a warning, and then we exit. A lot of things going on here. We echo name required, but what is this? What's happening here? We are redirecting it. Remember how before we had redirected it to a file like file.txt? Well, instead of redirecting it to a file, we're using the ampersand here, which means redirected to a file descriptor, and we are redirecting it to file descriptor 2. So if you don't know what these are, I'll try to explain it as best I can. But when you're reading input, you're reading it over standard input or standard in, I'll call it. That is file descriptor 0. This exists on every process that is executed on a Unix or Unix-like operating system. So that includes Linux or Mac OS. You have 0 for standard in. You also have standard out, standard output, or std out, you might see it written. That is file descriptor 1. That is always file descriptor 1. That is assumed. If I don't give it anything, it'll just go to normally standard out. So we have this one, which is standard error. ERROR is what I'm saying. Standard error or STDERR. That is always file descriptor 2. By default, it goes the same place as file descriptor 1, but we manually put it there. Typically, programs will output to standard out, like whatever data you were actually asking for, and standard error is where error messages will actually go. I could show you this if I were to, let's say, cat user share dict words, and let's write this out to file.txt. No output appeared on the screen because it all went into file.txt, right? What if I were to cat something else? What if I were to cat, I don't know, this file does not exist? I'll give you a hint, that file doesn't exist. Let's write that to file.txt, okay? We got an error message. The error message showed up on the screen. The error message did not go in the file. That's because the error message went to standard error, which still went to the screen. This redirect only redirects standard output. So we got the error message to the screen. Now here's the fun part. We also clobbered that file. That file's gone, okay? This redirect happens whether or not cat is successful. So cat failed. The file was already clobbered. We got an error message to the screen. That's what happened. So keep that in mind. You could clobber files even without meaning to. Let's go back to the script. Here's another command I didn't talk about, but hopefully it's self-explanatory. Exit. Just like you can return from a function, we like return numbers up here. When you're in a script, when you're not inside a function, you can't use return. It is an error to put return here. It would actually be like, it would cause an error. That's not allowed. You can use exit. Exit is your way of saying, just break out of the script. Like we're done, and you can optionally give it a code. So in this one, we're exiting with code 1, which is an error. So if we were to back out right here and run this without any arguments, we will get an error message. And we will see that it exited with code 1 because that is what we put there. Okay, so here we've seen this before. For name in $@. Again, quoted $@, that's an array version. That's a version that we can loop over of the arguments that were given to our program. The first thing we do here is if name equals D star. Now, I haven't talked about this, but I've hinted at this. This is a wildcard operation. This is valid in Bash as long as you're using this double bracket notation, and it will check that name starts with D. This is totally valid. If you were to quote this, now we're checking that it's literally the string D star. We don't want that. We want it to be wildcard, so we don't quote it. If the name begins with a D, then we say hello name. Elif, I haven't talked about this, but this is an else if the name begins with a B, then we also say hello. Hey, that's nice. We're going to say hello to D's and we're going to say hello to B's. That's cool. Otherwise, else, we say goodbye name. All right, pretty straightforward, right? Let's go ahead and run this. So if we do 00 script, Dave, Buddy, and Guy, we can see that we say hello Dave, starts with D. Hello Buddy, started with B. Goodbye Guy, started with G. Didn't quite match. So there you go. That is what the script does, and if you don't give it any arguments, it prints an error message. So yeah, I threw some new stuff in there, but got to keep you guys on your toes, and I figure one of the best ways to learn is through example. So I'll keep trying to throw some of these into the course where I actually just pull up a script and we walk through and we try to figure out what's going on. Okay, so now we're going to talk about case statements. We are back in the foo directory where we have some of that stuff from earlier. We're going to go ahead and make a new program, and we're going to call it case. So case statements, you've probably seen them in other languages. They're very similar in Bash, and we can go ahead and just kind of whip one up real quick just so you can get an idea of what the syntax looks like, what it does, how it works. So we could do something like s equals $1, and then we can say case $s in, and then we can go through and talk about all our potential cases here. We don't need a semicolon do or anything. We just have an in here. And now we can say what cases there are. So the case would be like Dave. And if it's Dave, we can echo, hi, Dave. And then if it's Buddy, we could say echo, oh, there he is. So sorry, this is so stupid. Now you notice my syntax highlighter got a little mad at me. The reason that happened is because I didn't close this section. You know how in other languages you might have break? Well, here we don't use break, we use semicolon, semicolon. This is how we close the section. And then who was the third guy? Guy, I think I said. Go. Uh-oh. Here comes trouble. I'm sorry, this is so stupid. Let's close that. And then we close it here. Remember how we closed if with fee? We close case with esac. Really dumb, but that's what you do, okay? So let's go ahead and let's run case. Let's give it nothing, and we get nothing because it matched none of those cases. As you can see, we took the argument was blank, it tried to match blank, it didn't match any of it. But if we give it Dave, let's say hi Dave, hey, that's pretty cool. If we give it Buddy, let's say, oh, there he is. If we give it Guy, uh-oh, here comes trouble. If we give it John, just spell it wrong, we get nothing. So as you can see, we get nothing there. How do we handle that case, the default case? Well, we can use, you guessed it, a wildcard. So echo, I don't know who you are. There you go. So now we can run this and it'll say, I don't know who you are. So that's the basics of case statements. They do get a little bit more complex, and we'll talk about the complexities. Also, if you're only doing one thing per case, a lot of times it makes sense to kind of just put them on one line. You can space them out, you can do multiple commands, but if you're just doing one command, kind of doing them like this, very simple to look at, very easy to understand. So yeah, you have this, and you also have wildcards in the beginning. So let's go back. So if you remember in the last one where I talked about what we have, I went in the Bash course and I have my notes, and I think it was 0306. And we have this script from before. Well, this right here with the if and the elif and the else, that's a good candidate for rewriting. So let's go ahead and rewrite this. Let's save this as 01 case. So now we have a brand new script called 01 case, and let's modify it. So down here we have for name in this, and we check if the name starts with a D or the name starts with a B. We can rewrite this. So let's go ahead and rewrite this right now. We can do case $name in D star. Totally valid. And then we'll call hello on name and do the double semicolon to close it. If it's a B star, we will call hello on name and do the double semicolon to close it. And if it's anything else, we can do the goodbye on name and do the double semicolon to close it. Get rid of all this, put our esac here, and we're good to go. We've rewritten the script to use a case statement. So now if we run this, we get name required. Joe, John, Buddy, Guy, Dave. Goodbye, Joe. Goodbye, John. Hello, Buddy. Goodbye, Guy. Hello, Dave. So look, the D's and the B's give you a hello. Everything else gives us a goodbye. So that works. That's awesome. One of the last things we can do here is, if you notice, these two cases are kind of the same. We can do this. Put a pipe character there. We're not piping information from one to the other. Think of it as like a or statement. It's going to match one or the other. So we can rerun this. And it works. We get hello for Buddy and we get hello for Dave. So you can put multiple patterns like this and condense them down into the same block. So case statements can be very elegant. I think they're one of those things where I see people using if statements and they really could just benefit from using a case statement. Sometimes you'll have if blocks that are like 20 lines long and they can be replaced by a case statement that's like 8. So it's pretty awesome. But since we're here, let's talk about the next thing. So in 400, I have created some scripts and we're going to go through this. A lot of this course will be me writing programming and you being able to follow along, but some of this stuff I think is easier if I already come at it pre-written because there's one or two little tweaks I can show you. So we have this case first, and as you can see, this is what we had before. I didn't condense the two cases, but this is the exact same script that we had already rewritten. I'm not going to spend time on that. Let's look at the simple case statement. So as you can see, this is very similar to the one that I originally wrote at the beginning, but I've hard-coded it to Dave, and the reason I've hard-coded it to Dave is to show you that we have matched D star and we have Dave, we have F star and we have foo. So this is really interesting. What do you think is going to happen? We have the string Dave here. It will match D star because it starts with D, so it'll match D star. Will it match Dave? Will it go on and match the next one that it would match? Because in my mind, these two are matches. Let's see what it does. We run it. It only matches the first one. So this is how case statements work with this double semicolon in bash. They will match one. They won't match any more than that. They go by their first match and they completely break out. But there are alternative syntaxes, okay? So let's look at the always fall through example. The name might give away what it does, but look at this. Semicolon ampersand. Semicolon ampersand. Isn't that really interesting? So we have the string here, far. We're not using Dave. We have it set to far. So it should match F star and it will not match foo, right? Because far is not foo. So let's go ahead and run always fall through. That's interesting, isn't it? So what happened there? Let's go ahead and pull that source code up. I'll do this and then we'll run it again. You can see that it matched F star. That was the first one it matched. But this causes it to fall through to the next one. So whether it matched or not, it just moved on to the next branch of code and just kept running all this stuff. And then it moved on to here and it ran this stuff. It didn't match those, it only matched F star, but once it matched, it moved on to the next automatically. You may or may not want this behavior. If you do, semicolon ampersand is the way to do it. And then we have a third one. Believe it or not, we have a third one, semicolon, semicolon, ampersand. Yeah, it's not great syntax. I don't love it. I'm not going to sit here and defend it, but it is what it is. So again, we have Dave here. So we should match D star, right? So what's going to happen? Well, I'm not going to make you guess. We'll just run it and I'll show you. Let's pull up the source code. There we go. So it matched D star. It matched Dave. It didn't match these two, but then it matched star. So look at the name of the script. It's kind of giving it away. Try again. This will go through every possible case and it will match. Anytime it matches, it will run the code and it will check every single match. So it'll go from top to bottom. It'll say, hey, am I D star? Well, I'm Dave. So yes. So let me run this code. Hey, am I Dave? Well, I'm Dave. So yes. Let me run this code. Hey, am I F star? No. Hey, am I foo? No. Hey, am I star? Yes. So these are some alternative syntax to case statements. I will tell you in my experience, I've written a lot of bash code. I almost never use the two alternative syntaxes I show you. I call them alternative. This is the main syntax I use, the double semicolon, where we match the first one that matches and then we break out of the case statement. This is the one I use the most, but it's good to know that the other ones are there. So there you go. All right, so let's talk about indexed arrays in bash. We already talked about it a little bit with the $@ sign, which indexes over $1, $2, $3, etc. But we can define these ourselves. Bash has arrays built in. So let's go ahead and vim indexed arrays, we'll call it. This will be a new script and we can do all of our work in here. So let's save that, reopen it. I forgot to make it executable, didn't I? Well, we can do that later. We can say array equals, just like we're making a variable, open and close parenthesis. This is how you make an array in bash, by open and closing parenthesis. Now we can put things in here. Foo, bar, baz. There we go. That's an array. The array has 3 items. And now we can echo array, right? So let's go ahead. Let's make this executable before I forget. And let's run it. Okay, well, what's going on here? We're only getting the first element of the array. Actually, yes, that is exactly what's happening here. When you expand it like a normal variable, you will only get the first element of the array. That's very important to note. If you want to get all the elements in the array, you're going to need some special notation here. So let's say, not even all the elements, if you wanted to get any other element, if you wanted to index it, you would need an alternative syntax, and I will show you what that looks like. So in another language, you might have like open square bracket, 0, close square bracket. In bash, you have the same thing, but look at the syntax highlighting. You see it's already kind of broken there. We have to do this. We have to put a curly brace open here and a curly brace closed here. So when you want to use that square bracket notation, you do need to use the curly braces around the variable. Technically speaking, this is also valid. This will just expand the way it would without the curly braces. The curly braces are optional. I prefer to leave them off, but you can put the curly braces here and it will expand exactly the same. If I run this, we'll just get foo. But now that we have these curly braces, I can do this, and we will also get foo because foo is the 0th element. But now that we have this, we can duplicate that line, YYP for yank the line and paste. Let's do this. Let's go over here and let's increment this number. Let's increment that number twice. Control A to increment. Is it useful giving these Vim little shortcuts as I go through? I don't know. I'll have to decide if I keep doing that. Hopefully it's not too annoying. So now we have array spot 0, array spot 1, and array spot 2. Let's go ahead and run that. Hey, look at that. We got foo bar baz. That's what's in there. So we can say, that's awesome. Let's go over here and let's get array spot 3. What do we get? We get a blank line. There's nothing there. So it will expand like it's an empty string. Bash kind of treats it like an empty string, and you can use it that way. We also have some magic here. So let's go ahead and do this. Let's make our life easier. Let's say 0 is this, 1 is this. That way we can just kind of see in the output what's happening here. We can do this, -1. So what do you think is going to happen? If we index on -1, we get baz. You can index negatively into arrays in bash, so you can go backwards through an array. So we get the last element with -1. Of course, -2 works, -3, yada, yada, yada. They all work how you expect. So you can do this, and you can index backwards through an array. Super useful. I'll throw another echo here just so we can get more new lines in the output. Now that we have this, we can do another thing. So let's say we want to do index equals 2. We can echo, what was it? Index, and we will get array spot IDX. So let's see if this works. And it does. Index is baz, so that is array spot 2. So we got that from a variable. So you can put the index you want in a variable. Also, when you're using this notation with indexed arrays, you don't need the $sign there. This is totally valid. This is totally works. This is how I prefer to write it. So these two lines will be exactly the same. The $sign is optional when you are indexing into indexed arrays or arrays that are numeric. Their key is numeric, is what I'm trying to say when I say that. So now, how can we look at all the items in an array? This part's where it gets a little bit weird, but bear with me because I will explain some of the differences here because there are some massive gotchas with this. We can do this star notation, and we can also do the @ notation. So the @ is very similar to how we looped over the arguments. There's also star. So I will show you what that looks like. Let's say star : this and @ that. Let's go ahead and run it. And, well, hey, they both gave us all the elements of it, right? Like this, it both seems like they're working totally fine here, right? Well, let's see. So let's go ahead and loop over the elements of the array. So the first thing we're going to do is loop over star. So what that means is for item in, we'll use the star notation. Actually, let's clear things up. Let's go ahead and get rid of some of this stuff right here. And let's get rid of this and just loop over the array. Okay? Do, done, echo, item is item. So we're just going to loop over the array. We are using the star notation and we have quoted it, right? So let's go ahead and run this and see what happens. Well, that's not great. It looks like there's only one item in the array, and the item is foo space bar space baz. So that's not what we want. If we put the @ here, this will properly break it as an array. This is what you want. You want quotes around it, and you want the @. The star is for when you're stringifying the elements of an array, when you want a string at the end of it. The @ is for when you want to treat it like an array, when you want to sequence over it, when you want to iterate over it. Leaving out the quotes is never right. Now you can do it here, and it will seem to work. In fact, if you leave out the quotes and you put a star here, they will effectively be the same. They will both seem to work. And this is great until your array elements have unique members in them. So let's say we have foo, bar, baz, and hey there, friend. A string of hey there, friend. Do you see what's going to happen here? If we run this, it thinks there are 6 items in the array. That is not true. There are 4 items in the array. The last item is a string that has white space in it. So we have to put the quotes back. We have to put the @ here. And this will properly break the array up the way that it's supposed to be broken up, okay? Quotes and the @ sign is how you properly loop over an array in Bash. So commit that to memory. It's important that you know that. Another thing I can talk about is the syntax for making an array. Here, I'll break this down so it's a little bit easier to look at. If you open a variable with a parenthesis, Bash knows you're making an indexed array. You can declare it manually if you wanted to. You could declare -a array. You can run this. Declare is built into Bash. And there's all sorts of things you declare. We'll go through these as the course progresses. But for now, we can declare with -a, make names an indexed array. So -a will make it an indexed array. This is the default for arrays, but we can do this. Totally valid. This is just explicitly doing this. The nice thing about this is you can do these steps separately. You could declare -a array here. So you could, declare the variable and then initialize it later if you wanted to. It's up to you how you do it, but this is the syntax for making an array, but it's assumed. You don't need it. I pretty much omit it because there's no reason for it. Now, here's the interesting thing. Let's say we wanted to copy an array. Here's something that might be useful to you. You'll probably encounter this. You want to make a new array equals this, and you want to copy over this array. Well, how do you do it? Because you might be tempted to do something like this. New array equals array. And then let's loop over the new array. So hopefully it's clear what I'm doing. I made an array. Let's call this first array. And we'll call this second array. And then we want to loop over the second array. So this is the copy of the array effectively. I don't know if this is clear or not. Hopefully it is. Let's go ahead and run this and see what happens. Item is foo. Okay, so we only got the first item out of it, so clearly it's broken. And of course we only got the first item out of it. When you open an array like this, you only get the first item out of it. So you might be thinking, okay, Dave, I listened to you. I know that we have to use this syntax. And thank you for listening to me, but now it thinks it's one big string because we've assigned it like this. We need to use this syntax. We need to put quotes around it. This is not enough on its own because it will still be a big giant string. And now we need to do parentheses. So we're not copying the array per se. We're actually, we are, but let me walk through what's happening here. We're making a new array. The open parentheses here means we're making a new array. And what items are we putting in the array? All of the items that are in first array. We are putting all those in there. In fact, we could add some new ones on. We could put Buddy and Guy in here too. And then if we run this, we will loop over foo, bar, baz, Buddy, and Guy. So this is the syntax for that. I'll go ahead and get rid of this. If you want to copy an array in Bash, this is pretty much what you need to do. And then if you are copying to an array, there's also another syntax you probably want to know about, which is the plus equal. We can push onto an array. Plus equal, and then you have to give it a new array. Think of this like, I think JavaScript has like splice or something. We're basically extending the array. We could put Buddy, Guy, and Joe here. So this syntax is valid. It looks weird, but totally valid. We run this, and now we have foo, bar, baz, Buddy, Guy, and Joe. So that's how you would push onto an array. You're basically extending it. You could extend it by another array. Yeah, this is the notation for that. And one little thing I want to show you is how to pretty print a variable. There's a couple different ways to do this, but here's the cool thing about arrays. I can declare them here if I wanted to. I don't know why I'd want to, but I can just declare it on my terminal. Now I have an array. And if you want to see what's inside that array, it's kind of useful to know that it's an array because you might be like, okay, what am I looking at? Remember declare? Declare has a cool option. Let's see if I can find it. -p, display the attributes and value of each name. So we have echo array here. Let's declare -p, the name, not a $, the name of the variable. And now we get this version of it. Technically, I think we could paste this right back into our shell and it will work. But this shows you the attributes. This shows you how this variable was made. It's a -a, so it's an array. It's called array, and it has 0 is set to foo, 1 is set to bar, and 2 is set to baz. This syntax is valid. So if I just copy and paste this back in, this is valid. You can specify the keys this way. And the reason you might want to do this is because I could set 45 equal to Buddy. And Bash does have sparse arrays. So if I declare -p on array, you will see that there's array spot 0, 1, 2, and 45. If I open up array on spot 45 like this, you can see that we get Buddy back. Now, how many actual elements are stored in here? Are there 45 elements? Well, no, we have to get the length of the array. How do you get the length of the array? Get ready for this. Put a pound sign there. There you go. Now we got the length of the array. There are 5 elements: foo, bar, baz, and buddy. How are there 5 elements? That's wrong. That is incorrect. That is telling you the length of what is that spot. I'll explain this in a second. Put an @ sign here, have that pound sign in front of it, and now we get 4. There are 4 elements of the array. That is what this is telling you, that there are 4 items in the array. This syntax is telling you the length of the string. So the string at array spot 45, which is buddy, has a length of 5. Very confusing, but bash lets you do that. If I were to say var equals hello world, I can echo var, but I can also echo pound sign var, and I have to put curly braces around it, and we'll get 11 because that's the length of that string. So here's a cool way to get the length of the string. You can also use that to get the length of the array. So array, and then you have to just do every element like that with the @ sign, and we get 4. All right, so let's talk about the next data type. We have indexed arrays. Do you know what's coming next? We have associative arrays. Associative arrays. Let me make sure I spell that right. Associative arrays are sort of like, think of like, I think JavaScript has objects, Rust has hash maps. What else do they have? Python has dictionaries. It's like a key value. It's just an array, but instead of having a number, it's not indexed based on a number. It has an arbitrary string as the key. So we can make one here. Let me do this so I don't forget. So remember how we could use declare -a, but we didn't have to? When you make an associative array, you do have to use the syntax capital A. So we have to do a -A here, and now we can make our own array. So let's call it ARR. Now here's the fun thing. Associative arrays are relatively new in Bash, and when I say new, I mean like they're 15 years old, but they are in Bash 4.0 and above. So if you're thinking, I want my script to work on an older system, I should check the Bash version, right? No. You should not do version detection, you should do feature detection. The cool thing is, this declare command, you can check the exit code of. So if I run this script now, we can see that it exited 0. I was successfully able to make an associative array. You could check this and you could exit if something went wrong. So you are free to write code like this. If not declare -a an array, then echo, uh-oh, I couldn't make an associative array. Let's write that to standard error. Let's exit with 1. Let's call phi here. Otherwise, if we were here, then we were able to make the associative array. So you can write code like that, kind of defensive. If you know what kind of version of Bash you're targeting, you probably don't need to do this. But just an FYI, you could totally write it like that, and that's how you would check it. Don't check the Bash version, just check for the features that are there. I'm going to get rid of that just because this is more of a learning exercise. So let's see what we have here. Now that we have this, we can do some magic here. We could say foo equals 1. We can copy this down. Bar equals that. Baz equals this. And we could do 2 and 3. So what happens now? Well, we can go ahead and we can echo that and we can see what happens. You ready for this? Nothing. We got nothing out of it, okay? We actually have to key into this. So let's go ahead and key into this. How do you think we key into this? Well, it's exactly how you key into the other style of array. You use the open and close square brackets, and you put the literal key that you want to get out of it. So you can do this, foo, bar, baz. So if this works, we should print 1, 2, and 3, correct? There we go. Hey, that's awesome. That's great. You can quote these if you want. You don't have to, but you can quote them. They'll work exactly the same. I choose to leave them out if I'm putting the string in there myself, but just an FYI, you definitely can quote them. If we were to put something here that's not valid, if we were to put fake here, we will get an empty string. Same thing as indexing into an array with a bad number. We're indexing it with a bad value, so we just get effectively an empty string. Now, similar to this, we can do what we did last time, which is if we want to loop the array or we want to see what elements are in it, we can try the star notation, we can try the @ notation. They'll look pretty much the same when we run it. We can see 1, 2, 3, 1, 2, 3. They both loop over the values, not the keys. They loop over the values. So if we wanted to loop over the keys, I'm going to go ahead and just get rid of this @ notation because we want to stringify the value for this notation. That's why we're using the star. Star is for when you want to stringify it. If we want to loop over the keys, we can put an exclamation mark. An exclamation mark, this is the indirect operator or indirection operator. You'll see it in other variables. I'll talk about this later. But for arrays, this means act on the keys and not the values. So if we run this again, we can see that we get foo, bar, and baz. We get the keys out of it. So that's what the exclamation mark does there. This is useful because if we were to do a for loop, we could do for key in and then change this to the @ sign because we want it quoted and we want the @ signs, and we do want the exclamation mark there because we want the keys. We can do done. We can echo got key. So let's go ahead and run this, and we should have got foo, got bar, got baz. Hey, that makes sense. Let's go ahead and clean up some of this stuff. We don't need to keep seeing this. So now, how do we get the value out of it? Very simple. We can do value equals, and then we have to index into that array. The array is called ARR, and the key we are using is just called key. That's it. Now here's the thing. If this were a numeric array, this would be totally fine. But with this syntax, it thinks we're looking for a literal key named KEY. So if I were to run this, you can see that got foo, got bar, got baz. I didn't print anything. Yeah, so let's go ahead and got key equals value. So let's print this. So we have got key equals value. We're trying to index into this. And now we have got foo equals nothing, bar equals nothing, baz equals nothing. That's not good. It's trying to key into a literal string there. So when you're using associative arrays, you do need that $sign there. We need to expand what's in the key variable here. And then when we run this, we will see got foo equals 1, bar equals 2, and baz equals 3. So I'll give you a little moment to take this in. But this is how you would loop over an associative array in Bash. They're surprisingly useful to have this data structure under your belt. All right, so now that we have talked about indexed arrays and associative arrays, I want to talk about the IFS variable. So this is built into Bash, and you might be asking yourself, like, why? Is this even related to arrays? It is, and I'm going to show you how it comes up. This plays a bigger role than what I'm going to show you with it, but this is one of those variables where I don't need to modify that much in my script. I typically only modify it if I'm reading data line by line, and I will show you that in further chapters. But for now, I want to show you something magical about it, because let's go back to, let's do our associative arrays here. So actually, no, let's start with the indexed arrays here. So we have our first array, foo, bar, baz, and we do all this. Let's make this simpler. Let's just say array equals foo, bar, baz, and then we can echo array is array. Give it the star because we want to stringify it, and that's it. So if this all works, it's just say array is foo space bar space baz. And that's what we get. That's awesome. It stringifies it, but what character does it use to stringify it? Well, it uses the first character of this magical variable called IFS. This is built into Bash. It's a special variable. Bash uses this to determine how to break up arguments and how to split words and do all this stuff. If you mess with it, it can cause issues, but it's a super useful variable, at least especially to be aware of. So by default, it is set to a space, a new line, and a tab. So just basic white space characters. And the way this star notation works is it will stringify it based on the first character of the IFS. Now, the beautiful thing about the IFS is if the IFS is unset, it defaults to acting like the normal IFS, which is new line, space, and tab and all that stuff. So I'll see people write code like this where they'll say like, what was it? They'll say old IFS equals $IFS. They'll do some work, blah, blah, blah. And then they'll say IFS equals old IFS. You don't really need to do that. There's a couple ways around it. You can just unset the IFS and it's the same as the default way of doing it. The other thing you can do is you can use a subshell and you can wrap it. I'll talk more about that later, but for now, we're not going to worry too much about it. We're going to set it to our own string. We'll set it to hello. This is going to be confusing, but bear with me. Now that it's set to hello, when we get this, we get array is foo, bar, baz separated by h, the first character of hello. So the first character of the IFS is the thing that splits it together, or it stringifies it when you use this star notation and it is quoted. It has to be quoted and you have to use the star notation. But this is useful because I can set IFS to like a colon. And now I have a, or sorry, colon, I said colon, comma. You can set it to a comma, you can set it to a colon, you can set it to whatever. You can get values separated like this and it works. It works really well. So I could say, you know, hello world, and quote that, and then you will see that the commas will do it properly. There's no comma between the two, but there's commas here. So the IFS is very useful and very powerful. It affects how arguments and like words are split in Bash, so you can mess things up. I like to use it under very specific circumstances. You can also wrap this in parentheses And now this is weird syntax. I will talk about this more. This doesn't create an array. This creates what's called a subshell, and it will work exactly the same. But the beautiful thing is any variables created inside here will be lost when this subshell is over. So you can think of this as like a local scope in a way. So any modifications you make here won't actually persist once this is over. Talk about that more. These are called subshells, but that's a great way of modifying the IFS, but not worrying about modifying it for other parts of the script. So yeah, this is super useful. And of course you can, I think I showed this with associative arrays, but now with index arrays, you can put an exclamation mark here. You can absolutely put an exclamation mark here, and you can loop over the keys of the array. The keys are just numbers in this case, but yeah, you can totally do this. There's nothing stopping you from doing that. All right, so the next thing I want to talk about is Command Substitution. Now, I showed it to you before. We use like the backticks or the $sign in the parenthesis. We're going to expand on that, and I'm going to talk about some of the specifics with it, how to use it, and what to be aware of. So I guess first thing, let's clean up this directory a little bit. Let's go ahead and make a new directory. We can use make dir. There's another command. So just like you can cd into a directory, we can make a directory. Let's go ahead and make one called done. And this is where we will move everything that is done. So to do this, it's really simple. We can just say, let's move Associative Arrays, which is the name of the file, into done, and that will move the file into the done directory. Now, if we ls, you'll notice that Associative Arrays is no longer there. If we ls done, you can see it's in that folder, it's in that directory. That's awesome. Do we really have to go through one by one and move them one by one? Because we could move case, we could also move conditionals, and we can move file.txt, and we can move them all into done. Move takes multiple arguments, and it will move them all into the last argument. If there's more than 2 arguments, meaning you give it a lot of arguments, the last argument has to be a directory, but if it's a directory, it works just fine. Now when we ls done, look at that, we have a bunch of files in there. I'll clear the screen, take a look at what we have right here. If you're curious, I do have an alias for L, just because sometimes I mistype ls and hit enter, so that's why L works just like ls does. If we want to move the rest of the stuff here, here's a cool trick we can do. We can move star into done. Now the interesting thing here is that star will match everything. It will even match the directory done. So it will print an error. It'll yell at us saying we're trying to move done inside done, which doesn't make sense. You can't put a folder in itself. So we get an invalid argument there, but don't worry, it worked. Everything else has been moved there. We now have a done directory which has all this stuff, but we have a clean directory that we can just make new scripts in. So let's go ahead and make our first script here. Let's do basic command substitution. We'll call it that. And of course, user bin env bash. Let's go ahead and save that. chmod +x, give it the executable bit. We can run it, and it does nothing because it's an empty script. Now, so I'll go over some of the stuff we went over before, but as you know, I can set any variable here. I could say thing equals, and if I use a single quote, who am I? These are single quotes. These are apostrophes effectively. And then I echo thing is thing. What do you think is going to happen? If I run this, it just prints thing is who am I. It doesn't run the who am I command. Who am I is a command. But in Bash's point of view, because we use single quotes here, this is just a string. We have to change these to backticks. Notice how it changes colors now. Now we'll actually execute that like a command. So if I rerun this, we can see thing is Dave. Hey, that's cool. That's the output of the who am I command. Of course, we could change this. We could change this to uname, and now it should say thing is Darwin, because that's the output of the uname command on my system. Now that's great, but let me show you this is a somewhat contrived example, but I'm going to prove what I asserted before earlier in this video, where I talked about nesting them becoming problems. So let's trash all this, and let's just run the who am I command on its own line. If we run that, it will print Dave, because that's who I am. We could also echo who am I and close it there. So the echo command takes arguments and it will print them to the screen, and the argument bash gives it will be the output of the who am I command. So if this works, it should just print Dave twice. One is the easy way of printing it, and one is the hard way where we use echo and we use command substitution. Again, this is contrived. You really wouldn't write code like this. It's convenient because you could do something like hello, and then you could do this all in one line. So like this example is a little bit contrived. But yeah, let me show you why this becomes a problem, because what if we wanted to nest it? What if we wanted echo to receive the echo command, and who am I is in here, and then we close those two backticks? Like, what's going to happen if we run this? Well, it prints who am I. It doesn't actually print Dave. So that's kind of weird. What's going on here? Well, this backtick is closing this backtick. We actually have two separate, I'll highlight them. We have two separate sections of backticks right here and right here. So echo is running the echo command, which gives it nothing. So there's nothing here, and then there's who am I, and there's nothing here. So all it prints is the literal who am I string. This is a little bit confusing, but if we wanted to nest it, we need to escape these backticks. And when you escape these backticks, now they're not closing this. This all is in one big giant backtick. That's great. So if we run this, what do we get? We get Dave, Dave, Dave. Hey, that's awesome. That's what we expect to get. That's really great. What if we want to do it again? Again, you really wouldn't write code like this, but I'm just showing this to illustrate the point. What if we wanted to echo this, and then echo this, and then who am I? And then we have to close that, and then we have to close that, and then we have to close these, and these weren't escaped. Is this gonna work? Well, let's go ahead and see. Let me :WQ, run that. We get who am I again. Okay, so that didn't clearly work. We have to not only escape the backtick here, we have to escape the backslash. So, as you can see, that's hideous. Not to mention, we haven't quoted any of our variables here. So if these commands had like multiple spaces in them, they would be lost because we are not appropriately quoting them. So let's go ahead and let's rewrite this. So we'll call this backticks, and then we will say echo dollar parens notation. Not the best way of writing it, but here we go. When I execute this command, you will see that we have the backticks up here, and then we have the dollar parens notation down there. So let's go ahead and show what this would look like if we were to use that notation. We do this, and then we run the command we want, and then we close it. That's pretty simple. How do we nest it? Look at that. No escaping, no having to worry about it. This is proper. This works exactly as is. In fact, if I want to nest it one more level, I can just copy and paste this whole thing, put echo here, open it there, close it there, and look at that. Super easy. Now again, contrived example, you wouldn't really be doing this. I'm just showing you why this notation, I would prefer this notation. On top of that, you can also quote your expansions very easily. So I could put quotes there, I could put quotes here, put quotes at the beginning of the dollar sign and quotes at the end of the parenthesis, and it might look a little weird. Again, I can't stress this enough. You're not going to write code like this because yeah, this looks super weird, but it should just work until I have a typo on the last one. Where did I put the typo in there? We echo. Oh, I forgot the open quotes here. I should have looked at the syntax highlighter to even help me out. So again, you're not writing code like either of these ways. This is just sort of to drive the point home that forget the backticks. You might see them, you'll see them in scripts. You don't need them. You can use this notation. It is so much easier for command substitution. This is what this notation is called, command substitution. You put a command in here and bash will substitute it for the standard output of the command. That is what's happening there. So of course, the beautiful thing about this, let's go ahead and trash this whole file, is we can make our own little mini program. Do you remember how to make a mini program? It's a function. We can make our own little function here where our function just echoes hi. That's all it does. Now we can say thing equals myfunc. We call it just like any other program on the system, and now thing will be defined to that. So we can say thing is $thing, and when we run this, what do you think we're gonna get? There's no trickery here. We get thing is hi. Perfect. That's exactly what we expected to get. We are just running this function inside command substitution. Now there is something to be aware of here, and this is really important. In this notation of command substitution, this will run in a subshell. This will run in a different environment than your main program. So let me show you, let me illustrate what I mean by that. Let's make a global variable here called I, and let's set it equal to 5. Okay, right at the top of our script, I is set to 5. Inside my function, let's have some side effects here. Let's not only print hi, but let's also modify I to be 6. Okay, so we have thing is thing here. So now below this, let's go ahead and echo I is $I. Now what do you think it's going to be? Do you think it's going to be 5 or do you think it's going to be 6 if we run this? Let's go ahead, I'll pull the source code up so you can cross-reference it and take a look at that. I is 5. Even though this function ran and this function set I equal to 6, this is dropped because of this notation. When you see these parens like this, there's a good chance it's going to be running in a subshell and this will be dropped. So I was set to 6 for the duration of this function, but it was dropped at the end of this. Once this line is done, I is equal to 5 here. It was never equal to 6 in this parent shell. So this is something to keep in mind. Functions by default can modify the global scope. So if I just ran that function without capturing its output, say I didn't do this, I just ran myfunc here. I didn't capture its output, I just ran myfunc and then ran it. Take a look at this. I'll pull the source code up, we'll run it, what do I call it, command substitution. Now we have I equals 6. So functions can modify the global scope. This is why I tell you to use the local keyword in your functions. You can avoid this. But if you use command substitution, it can't modify that global scope. There is an alternative syntax for command substitution. So let's go ahead and revert this back to what we had here, which was, what do we have? Thing equals myfunc echo thing is $thing. Now there is a new syntax. So this is what we had before. I didn't change anything yet. So we get I equals 5. I was not modified. This new syntax I'm talking about was introduced in bash 5.3. I have a video where I talk about these new changes. When I say new, I mean this patch came out sometime in 2025. So whenever you're watching this, that could be a long time ago, or that could still be relatively new. So it's so new that my Vim highlighter won't even like this. It will yell at me. But if I change this to a curly brace, I put a space here. The space is very important. Look how Vim is really upset with me. And then I change this final thing to a semicolon, close the curly brace. So sorry, Vim is yelling at me. It doesn't like this, but this is valid bash syntax. If you're on 5.3 or higher, you can run my func like this as long as we have that semicolon there. I usually put the semicolon there and put a space here. I don't know if that space is necessary at the end, but the space is necessary at the beginning. So we can run this, and let's go ahead and see what happens when we run this syntax, because this syntax is not, look, even bat doesn't like syntax highlighting. It's very confused. We run this, thing is high, I is 6. So we still capture the standard out of my func, but it didn't run in its own subshell. It ran in the main shell. This is useful, but it can have side effects. If you want your functions to have side effects, like being able to modify global scope, this syntax is great. If you want your functions to be fast, this syntax is great. When you use the parentheses, it is slower because you have to create a subshell, but you get the benefit of not being able to modify any sort of global scope. Cool, so now that you've seen the single open parenthesis, get ready for the double open parenthesis. Now I've talked about this before. This is arithmetic expression, or being able to deal with math in bash. If you want to look up the help page for it, it will tell you to look up the help page for let. When you look up this is all the sort of stuff you can do here. I plan on going through it all real quick with you just to show you what's going on here. So let's make our own script. Arithmetic expression. Am I pronouncing that right? Is it I always say arithmetic, but I don't know if it's arithmetic. I don't know. You guys can tell me if I'm pronouncing that right or not. So we're going to use math expression. There we go. That's safe, right? Just avoid the word altogether. Cool. So what's the first thing we can do? Well, you know how we can say thing equals command here, and we can just put whatever command we want here. The reason it turned orange is because command is actually the name of a command in bash, so it recognizes that. But we could put anything here. We could put uname, we could put who am I, you could put date, you could put whatever command here. Well, we can use double parentheses. Notice the $sign in front of it, because this will expand it using the math syntax. So we can put anything in here that we want that's mathematical. You can put spaces, not put spaces, whatever you want. It's a stylistic choice. So we could do 2 plus 2. Again, the spaces are optional. I'm going to leave them in there just because it makes it easy to see. So we could say thing is $thing. We go ahead and run arithmetic expression. We can't tab complete it because it's not executable. So chmod plus x, now we can tab complete it because it knows we're trying to run it. So if you're having trouble tab completing a program like this, you're trying to execute directly, make sure to check that the executable bit is there. We run this, and thing is 4. Hey, that's awesome. No trickery there, right? We can do this on our shell if we want to. Sometimes I end up doing quick math like this, where it's like, oh, what's 57 times 2? I run this, and it's 114. That's awesome. What's 57 to the second power? 3,249. There's some heavy wind out right now. I think I just heard a tree branch hit my roof. That's awesome. Hopefully nothing breaks. All right, let's keep going. The nice thing about math is you don't even have to have an expression here. You can just say, like, I don't know, 42, and you run it, and it will just resolve to 42. Like, that makes perfect sense, right? Let's go ahead, let's go back into the script, and let's start doing some fun things here. Because we can do, let's say a equals 2, b equals 3. We can echo $A plus $B. We can even use variables, and look at this. It works. I said it works before I even run it. I should be more cognizant of that. So we get 5 because 2 plus 3 is 5. That's awesome. Again, when you are in mathematical expressions here in bash, when you are doing arithmetic expression, you don't need the $signs here. You can just use these. It understands variables, and it will resolve them for you. So that is pretty cool. Something to keep in mind, though, this is something to be mindful of in bash. It's not really strongly typed. There is a way of declaring integers, but they're kind of weird how they work, so I'm going to stay away from them here. If you're interested in looking this up, look up declare-i. You can technically create integers, but I've run into all sorts of problems with them, so I stay away from them. But if I were to say a equals hello and b equals goodbye, I'm setting them equal to strings, and then I'm going to do math on strings. What do you think is going to happen? Well, we get 0. When it can't be parsed as a number, it usually ends up being treated like a 0. This sucks. This will be the source of a lot of bugs. I'm sorry, that's just how it's going to work. So you might have to check your expressions. If you are taking numbers from a user, you may have to check that what they gave you was a valid user. I can talk about how to do that later in the video, but you might want to check, like, you know, does $A equal 0 through 9 star or something like that. Yeah, so when you put the $sign in front of it, that means to evaluate it and print the result. You can actually omit the $sign. It's invalid after echo here, but you can put it here, or you can put it in a for loop or a while loop like you've seen. But you can just do this here, and this will have a side effect. So it'll run that code, and then we can just say echo done here. If we run that, it won't print anything, it'll just print done, but this expression actually did work. So you could say something like C equals A plus B. You could do it like this, and you could say C equals $C. Let's quote this just to be good. Go ahead and run this, and we can see that C equals 0. Of course C equals 0, because I forgot that I set these equal to words. 2 and 3. So if this all works, C should be equal to 5. There we go. That's awesome. That is super useful. The reason it's super useful is because we can do stuff that you might be used to. Let's get rid of A and B, and let's do I. I equals 0, I plus plus, and then we can check what I is equal to. So here's a script, and if we run it, look at that, I is equal to 1. So we have post increment, we have pre-increment, we have all sorts of fun things like that. We could take this I, and we could do something like times equals 5. And let's go ahead and change this from 0, because 0 times 5 is 0. Let's make this 2. So if I times equal 5, we should get 2 times 5. I should be set to 10 at the end of this. If we run this, I is equal to 10. That's awesome. We also do have shift operators, so you could do like shift equals. So you could take 2 and shift it to the right 5 times, and then you run this, you get 0. We could shift it to the left. Ooh, wow, that got all messed up. Shift it to the left 5 times, we run that, and now we get 64. That makes perfect sense. So it's kind of wild what you can do. You can do all sorts of fun operators with this. This is a super useful thing to know, because the math that Bash supports is surprisingly robust. You can do a lot here. We have logical operations. We can do bitwise OR, we can do XOR, bitwise AND. You can do modular division or remainder division, exponents, bitwise negation, logical negation. There's all sorts of fun stuff you can do. You can even do ternaries. Bash does not have ternaries normally, but in this syntax, it does. And this is really cool, because we could make our own little like max function. So we could say, you know, A equals 2. Let's do the basics. B equals 3, and then we want to get whatever the max is. We could say max equals, if A is greater than B, then we want to set it to whatever A is. Otherwise, we want to set it to what B is. If you've never seen this syntax before, I'm very sorry. It's called a ternary operator. It's in a lot of different languages. Now we can say max equals $max, but all we're saying is run this expression, and what comes after the question mark is if the expression resolves true, and what comes after the colon is if the expression resolves false, and we save that into the variable called max. So we run this, and we should get 3, because 3 is the greater of those two options. Perfect. So that's our own little max function determining which number of 2 is bigger. Now, there is something to be mindful of here, and this is something that trips a lot of people up, especially if they do set minus E in their scripts. I will talk about that later in the video. I do have a video dedicated on my YouTube channel specifically to this, because this causes a lot more problems than it's worth. That's my personal bias when it comes towards it. And one of the issues I see from that is people don't realize that this expression has a return code, meaning this can fail. Now, in Bash, if something just fails, if a command fails, we just move on to the next line. That's totally fine. But if we were checking it or looking at the return code, some things might not work how you expect them to. So what I mean by that is if we have, let's say, 2 plus 2, we can echo $question mark. In fact, you know what? Actually, I'm just going to do this in the command line. It's easier to see it here. 2 plus 2. We run that, and it evaluated it. It didn't save the data anywhere, but it evaluated it. So let's go ahead and look at the return code. It was 0, meaning it was a success. 2 plus 2 is a success. Why am I stressing this? Because what about 2 minus 2? That is a failure. Super weird, super bizarre, but you have to shift your mind into thinking like C. If you have if A minus B, then something like that in C, it will check if the answer is 0, then the if statement fails. If the answer is true, then the if statement's true. That's why it works this way. So I can write code in Bash where I can say something like, let's say A equals 10. I can say if A modularly divided by 2, then echo something else echo something else phi. So this might be kind of confusing, and this is a little contrived. I would never actually write code like this, but I'm going to show you what happens when I run it. We're not going to sit here and try and figure out what it does. We're going to explain what happens by running it through some examples. So print something else. So that means that if you do 10 modularly divided by 2, it is a failure. Why is it a failure? Because 10 modularly divided by 2 is equal to 0, and 0 is considered a failure inside math expression. This is the confusing part. When the answer is 0, it returns a failure, and a failure to bash is non-zero. So it's a little bit negated from how you're thinking. If the answer is 0, it's considered a failure in terms of the if statement. So effectively, we could change this something else to like number is even, and we can do number is odd, and now we have a basic is even is odd detector. So if I run this, we can see, okay, 10 is even, that's awesome. What about 11? If we run it against 11, number is odd. That's very simple. Again, I wouldn't write code like this. I would do something like this. I would check very specifically, and then I would negate these. So if you modularly divide it by 2 and it's equal to 0, then we can say that number is 0 or number is even. I like to be very explicit when I code things like this, but I'm just showing you that the result of this can be tested against. That arithmetic expression in this sort of format does have a return code. This trips people up because people will have code like this. They'll have I equals 0 while I is less than 10, which is totally valid. You can write code like this. And then at the bottom of their loop, they'll have I++, and we can say echo I is $I. And that's all well and good. We can run arithmetic expression and we get I is 0, I is 1, I is all the way up to 9. Now there is something I haven't told you about, but you may have seen this before. Some people like set minus E, which is Bash's way of exiting if there's an error. And people claim that, oh my God, this makes your Bash scripts more robust. Maybe it does for some people, but it also causes you to exit early because the output, the return code of this expression is a failure the first time it runs because the answer is 0 when it's 0 plus plus. Even if you're thinking, wait, 0 plus plus, doesn't that resolve to 1? Yeah, but it's a post increment, so it resolves to 1 after it's already considered. So it's like a gotcha on top of a gotcha here. So I might talk about this more later, but just get rid of that and we're good to go. You might run into some bugs, but hopefully by following this course, I can help you work your way out of them and not get stuck by them. There are also some more things to consider with arithmetic expression, just some things to be aware of. There's a lot of things it can do, and it is very powerful. With that, it can also be kind of confusing. So if we have a string with like leading zeros, for instance, we have A equals 06, we can do something that we could echo $A, we can just print it to the screen, and then we can echo, what is it? A like this. So we just treat it like a number. And what happens when we do this? We echo 06 because that's what the literal string is. And then when we treat it like a number, it's 6. Hey, that makes sense. It just stripped off the leading 0. That's super convenient. What if we make this a 7 and then we run it? Hey, that's awesome. It strips off the leading 0. That's so great. What if we make this an 8 and we run it? Oh, that's super weird. That's not what I expected. Arithmetic expression, when it detects a leading 0, it treats it like octal, meaning base 8. So the number 8 is too high for octal. That's what's happening here. That might be confusing to you. You would have to do something like this. 010, this is not binary. This is this is not hex, no. This is not binary. This is octal. This is base 8. So that means 1 in the 8's place and 0 in the 1's place. So we will have 1 8 in this, meaning this should resolve to the number 8. And if we run this, that's what we get. So be aware of leading zeros. They can cause you problems when you're trying to deal with them in a mathematical way. There are ways to get around this. You can force it into a specific base. So if you know what the base is, you can do 10 £. Now the £sign is valid. It won't consider it a comment. Don't worry about it. It's inside this expression notation, so it's not considered a comment. 10 is the base. We're going to say force this to be base 10. And when we run it, oh, we still get an error. What's going on there? This is the time where we have to put a $sign here. I'm sorry, it's weird. Bash is full of weird rules like this, but you need the $sign here. We need to basically turn it into the 08, or sorry, the 010 in this case, and then we'll force it into base 10. And then look, it treats it like the number 10. That's what it knew it was getting. This also works if we were to go back to like 08. Remember this one broke it before? We run this and it treats it like the number 8. So you can use bash to force it into a specific base. This is helpful. You can also put like 16 in front of it if you want to do conversions between like hex numbers and things like that. So super convenient. Arithmetic expression, very powerful and very useful when used in conjunction with like while and things like that to do sort of looping and stuff. Cool. So we have talked about command substitution. We have talked about arithmetic expression. And now we are going to talk about the next syntax you should be aware of. This one's a little bit weird. You may have seen it, but it might be a little bit confusing. I'm going to explain where you're going to want it. It is process substitution. This is not command substitution. This is process substitution. The syntax for command substitution is $parens, and then you put the command you want in there. The syntax for process substitution is very similar. It is a less than sign, and then parentheses, and then the command you want to run. So it still takes command. Technically speaking, you can also have a greater than here, and it will reverse the way that it works. This is a very specific syntax for a very specific use case. I find this one to be used more often. I'll explain the differences as I go through, but I'm going to focus more heavily on the less than variant of it. But let's dive into it. So let's go ahead and make our script process substitution. Make sure I can type. Listen, talking and typing is not as easy as it looks, okay? It's a skill and I've honed it. That's why I am amazing at what I do. No, I'm just kidding. That's why my brain like shuts off when I'm talking, when I'm typing. All right, enough joking around. Let's lock in here. All right, so let's go ahead and do what we have done before, which is we're gonna write a little script to get some words out of user shared dict words, and we're gonna use grep to find words that have a D in it, anywhere in it. So to do that, we're gonna use grep, we're gonna grep for D, and we're gonna grep in user share dict words. And that's how we're going to do it. That's how we're going to get every word that has a D in it. That's great, but let's do some processing on it with bash. So we have process substitution. Let's go ahead and give it a chmod plus X before I forget. Let's vim that file, and there we go. So we're going to grep D and user share dict words, but we do want to process this information, so we want to store it. Let's store it as a variable. So this variable will contain all of the words that we found that are separated by new lines. We're going to read the entire thing into this variable. This will be read completely into memory. Our RAM will hold this for us. So I'll talk about that later. I might be spoiling a little bit, but let's go ahead and go forward with this. Let's say we want to count how many words are in that file. Now, real quick, before I continue, I would be remiss not to mention this. With grep, I can give it a flag -C for count, and there we go. There's our answer. Stick to the tools that work. If you're just trying to get the count of something like that, use the built-in tool, okay? But we're going to do this in bash because I'm teaching concepts here that can be applied to more than just a specific situation, something that can be applied more broadly, and it gives me an excuse to talk about all the fun syntax we have here. So let's go ahead and let's set I equal to 0, and we're going to count every word that we see. So we're going to do for word in $words do. Notice that we're not quoting it. This is important. This is on purpose. We are not quoting it on purpose, and I will explain why. And then I will also talk about, don't worry, what I'm writing here, you should not be writing this. This is the wrong way of doing it, but we're going to iterate and show the better way of doing it. So we're going to echo the word that we saw, and then we're going to do I++. So we're going to increment it, and then we're going to say done. And the last thing we can do here is we can say found $I words. So it should print all the words that we saw, and then at the bottom it should say how many there were. Correct? So let's go ahead and run this. Okay, that worked pretty fast, and we found 60,155 words. I believe that's exactly what grep showed us. Cool. So that works. This code is working exactly how we want it to, but let me give you a little secret here. If you find that you're not quoting this thing in a for loop, and that makes it work, then it's probably wrong. Like, you really shouldn't be relying on this because you're using word splitting here in bash. It's extremely powerful and you can use it if you know what you're doing, but there are better ways to go around doing this. Like I said, I just use it and it works just fine because I know what my input is. I know what user shared dict words look like. If you know your environment, then go ahead and use it. But if you want to make your scripts resilient to any environment or to any kind of input, if you find that not quoting your variable expansion makes it work, then that's a sign that there's something that needs to be fixed with your script. That's sort of my rule of thumb that I operate on. Because if I were to quote this, what happens now? That's not the right command. It printed everything, and it said it found 1 words. So it quoted the whole thing, and it found 1 word. That word just happened to be a very large string with new lines in it. So not exactly what we want, but there are some alternative syntax here. I'm going to teach you a new thing that I haven't talked about yet as I go along. So let's just make some changes to this. Instead of using a for loop, we are going to use a while loop. We're going to do while read -r so we don't mangle any backslashes, word do. So we can get rid of that, and now we have a while loop, and this is going to read any word. The problem is this is going to read standard input. We need to tell it to read this. We need to tell it to read a variable that we have that is separated by new lines. So how do we tell it to read a variable? We're going to use something called a here string. H-E-R-E, as why don't I just type it out? There you go. That's what I'm saying out loud. There might actually be a space here. Now here strings are super nice because they let you pipe data into a command that already exists in a variable that you have. So you may have seen we could do this, and then we could put the name of a file here. So we could put user share dict words here, and that's totally fine, but we want this grep to run, okay? So we can't just put this file here. We want that grep to run. So instead, we can use this syntax. This is gonna be gnarly, but get ready for it. Triple less than. Now that we've done that, we can give it the variable here. That is called a here string. It reads a variable that is already set in bash. The triple less than is the notation for that. So read will get this information over and over again continuously until it's exhausted every word that it's read that's already gone through the grep. So I run that. As you can see, it's a little bit slower, but it works, and we found 60,155 words. So that's awesome. That's great. So this is a here string, and we haven't actually done any process substitution yet, even though that's what this section is about. So let's go ahead and rewrite this again, because you may have noticed that we had to read this whole thing into memory. And that's not great, because 60,000 lines of a file, that's fine. I probably have enough RAM for it. But what if it was, 60 million or something, or 600 million, or 600 billion lines? What if it was an unlimited amount of lines? That doesn't really work if we're trying to total them. But I think you get my point here. We can do this better. We can do this in a streaming fashion. Instead of having to let this line block until it's read the entire file, we can stream that data into the while loop. And I'm going to show you how to do that now. So to do that, we're going to move this line down here, and we're going to get rid of the command substitution. So we just have that grep, and then here's what we're going to do. This is pretty wild. We're going to join these two lines together. I use capital J in Vim to do that, and then put a pipe character here. This is valid. This is totally valid, and it works just fine. You can pipe into a while loop. If you do it that way, you have to get rid of this here string, because we didn't define that variable anymore. So we have this syntax, totally valid, totally works just fine. We can grep for d out of user share dict word, and we can pipe it to while read. We get the word variable, we echo the word variable, and we do I++, and we run it, and it should give us the total count. So you ready for this? It goes through it, and what is this? That didn't quite work. That's kind of weird, right? Well, this is similar to what we saw before. Remember how I talked about a subshell? Anything that's not to the left of the first command here, so anything to the right of a pipe, is being executed in a subshell. This is in a pipeline. So this while read line is working, and it is incrementing I. I is incrementing in its process. And then when its process dies, it's gone. So anything to the right of this pipeline doesn't stay in effect once we're done with it. Once we get to this line down here where my cursor is, I is set equal to 0 because it never got modified in the global scope like that, or in the main process or the main shell. How do we get around this? Well, finally, we can use process substitution. Hey, look, we're finally getting to the thing I've talked about. I managed to talk about 10 different things because we had to kind of work our way there. How do we do that? Well, let's go ahead and get rid of this. I'm just going to trash that all. And now this reads from nothing, so technically it would read from standard in. Let's have it read from a file. And the file we would give it normally would be user share dict blah, blah, blah. We don't want to do that. We want to have it read from a process. So we want to substitute a process, and that's what process substitution is here. So we can use this syntax. We use less than first here on its own to say we're reading from a file, and this syntax gets replaced with a file, and that file can be consumed as though it was like the command that's running inside it. Might be a little bit confusing, but I'll show you what I mean. We can grep for D and user share dict words. We put that there, and now it might look weird. I mean, it does look weird, but if we run it, we do this, look at that. We still get found 60,155 words. So that is process substitution. That allows you to put a process in this file. This gets replaced with the name of a file. I think technically underlying it's like a pipe or something. That's very specific to how your OS works, but it's super convenient because just to illustrate this concept, to bring it home, I could say echo uname here, and that is command substitution. If I did this, just prints a file descriptor. That's just a file descriptor. I can't echo it. I have to cat it because it's like a file. To read a file, you would use cat in this example. I can cat it. Of course, I can also less it. Kind of weird. I don't know why you do that. Oh, Oh, it's not a regular file. Oh, that's cute. Let's do less minus f. Hey, that works. That's awesome. I didn't know less prompt to do if it wasn't a regular file. That's kind of nice of it. So yeah, there you go. That is what process substitution does. You, as a programmer, you almost never need to be aware of the fact that this is the underlying thing. That's just some like specific implementation details of how bash works with your operating system to pass this data along. Most likely it's going to be a pipe that was created in the bash process that's given to your script. Yada, yada, yada. You don't have to worry about that. You get to treat it like a file. So treating it like a file means I can give it after a single less than sign, which expects a file. So this whole thing gets turned into a file that I can read. And what's in the contents of that file? The output of grep d user share dict words. The beautiful thing is this could be a slow command and it doesn't matter. This while loop starts processing immediately. It does not have to wait for the whole thing to be loaded into memory. It can do it in a streaming fashion. That is amazing. However, there are some caveats with it. Because we're not reading the whole thing into memory, because we're not waiting for grep to finish before we start processing the data, we don't have the exit code of grep. This is important. We don't know if grep was successful or not. If grep was given a bad file, we can't easily detect that. Now our script will break, but look at that. We get no such file directory there. We can't easily detect that that's the case. So just be aware of that. When using process substitution, it can sometimes mask the error codes. It can mask the return code. So make sure you're using it with something where it makes sense that you were using it like that. Cool. So now it's time to recap. We're going to go over what we have here. We are no longer in that foo directory. We are in some of the bash course notes that I've written for myself. And we can see that there are two scripts that exist. Normally I like to write the scripts out for you, but we're going to look at the ones that exist and we're going to go through them together and try to understand what's happening. So let's look at the first one, commands and math. Pretty simple. I don't know why I have a comment saying edit these. That was probably a note to myself. I don't need to do that. That's fine. Ignore that. So we have name equals who am I, and we have number equals 2 plus 2. So what do you think the output of the script is going to be? There's no trickery going in here. I'm not trying to like lead you down a bad path, but look at this. Name is name and number is number. Should be pretty straightforward. It should say Dave and it should say number is 4, right? Hey, that's awesome. That's great. Let's look at the second example, okay? Things are going to get a little bit tougher here, but let's not get freaked out. Here's the next example. It is called arrays. So we have some functions here. We won't go into the functions yet, but we'll just look at the fact that we have a function called process indexed. We have a function called process associative, and we have a function called process commands. And this one has a comment saying, next to it. I'll explain why and why that could be dangerous. It is dangerous, but I'll explain why. Oh boy, we have a lot of stuff here, don't we? Cool, so we have command equals $1, and then we echo script called with arguments, and then we print the arguments the user gave us. Then we call shift, we haven't talked about shift yet, and then we say script shifted to arguments that. So we print the arguments out again. Okay, a little bit weird, but what we can do here is instead of going on and trying to understand the rest of the script, we could just call exit here. This way we could run the script and just see what those like 4 lines of code actually do without having to process any more of the script, which is what I like to do sometimes when I'm looking at scripts I haven't really seen before. I can kind of get an idea of what's going on if I start encountering things that are a little bit suspect, a little bit weird. All right, so let's go ahead and run that script now that we've put a manual exit in there. The script is what, 01 arrays, I think. Run this, and we can see script called with arguments, blank. Script shifted to arguments, blank. Okay, let's give it some arguments. Foo, bar, baz. Script called with arguments, foo, bar, baz. Script shifted arguments, bar, baz. So shift is a way of moving the array of arguments over by 1. So $1 was foo, and then we shift it, so now $1 is bar, $2 is baz, and foo has been lost. We've shifted off, we've moved away, we've moved the whole array over by 1. This is useful because we have command equals $1, and then we shift it, and by doing that, we can do a case statement over command, but the rest of the arguments here have had the command removed to them. So think about this as subcommands. That's kind of what's going on here. So let me go ahead, let's get rid of this line, get rid of this line, and get rid of this exit. So now let's go down here. We have a case statement over command. So if we go back here, the command we gave it technically would be foo, and the arguments would be bar and baz, is a way of thinking about it. Let's pull back open the script. We can see that we look for the command to be the word indexed, the word associative, or the word commands. Otherwise, we print unknown command and we exit with an error code. So let's go ahead and just rerun this with foo, because that's an unknown command, and we get the error code 1, which is exactly what we expect, meaning it matched this leg of the case statement. Awesome. What if we give it the word indexed? What do? Well, we run process indexed and we give it all the rest of the arguments, not the name of the command, but just the rest of the arguments. So let's go ahead and look at process indexed to get an idea of what's going on. We take the arguments and we save it in as an array called arguments. Oh, I don't want to highlight every instance of that. That's a lot. So we have a new variable here called arguments, and that has every single argument that this function, this subcommand has been called with. And then we print the number of arguments. So if we gave it like foo bar baz, foo would be the command, bar baz would be the argument. So it would say 2. We can expect 2. Then we set the IFS, we've done this before, to a comma, and then we print out the arguments. Well, that seems pretty simple. Let's go ahead and just run the indexed example. Let's say indexed foo bar baz. Let's run that. Found 3 arguments, foo, comma, bar, comma, baz. Hey, that's great. That's awesome. We could also say something like, hello world, LOL, and give it commas ourselves as one big string because we've quoted it. It only found 1 argument. It looks like it joined up by commas, but we had done that ourselves manually. Of course, we could get rid of these. We could do this, and we could unquote it, and then we give it as 3 arguments, but we get the same exact output because the program did the job of joining them together. That's pretty neat. That seems pretty straightforward, right? What's the next one? Process associative. So let's go back down to the case statement. The case statement's very simple. If we give it the word associative, we run process associative with the arguments. If we give it the word commands, we run process commands with the arguments. Let's focus on associative right now. We take the arguments that the user gives us, we print the number that we found, and now we make an associative array called unique. So we make an associative array called unique, and can you guess what we're going to do? We're going to loop over every item. Notice that we declare item as local, so we don't bleed into the global scope. For item in arguments, we are going to loop over the arguments the user gave us. So in our case, if we gave foo bar baz, we're going to loop over foo, then bar, then baz. We're going to set that key equal to 1. We're just going to set the key equal to 1. And then at the end of this, we're going to print how many elements were in the associative array. That's kind of interesting, right? So why is that interesting? Because if I were to run this, give it the words associative, foo bar baz, we can see that we had 3 total arguments and 3 unique arguments. What if we gave it foo, foo, foo? 3 total arguments, 1 unique argument. So basically, this is a way of sort of deduplicating our data and coming up with which one is unique by setting it as the key of this array, this hash map, this dictionary, whatever you want to call it, whatever helps you understand it. We just set it to 1, meaning, hey, we found this. We're setting this to anything. This 1 could literally be anything. We could just put like anything, LOL, and that's totally valid because it'll just be a string of anything, LOL, and it just works. So that's what's going on there. That is how that works. So cool. I think we understand process index, and I think we understand process associative. Let's move on to this last one, because this last one has a little comment that says, This last one's a little scary, but we'll talk about why. We read the arguments that this function got, so we get the arguments of the function, which will be foo bar baz in our example that we keep using. We print the number of total arguments. Okay, we've done this every time, not a big deal. Then we loop over each item. Notice that we don't specify this. We don't say in that, we just say for item. This is also valid. For loops in bash, if you don't give it anything to loop over, it will loop over the arguments. It will loop over the positional parameters, $1, $2, $3, if they are set. If they're not set, the loop won't do anything. So putting that, totally unnecessary. You don't need to do that. You can just say for item, totally valid, and it works. It's going to run the command, and then it's literally just going to put this here. Notice that there's no echo in front of it. There's no anything in front of it. This is going to get treated like a command. If I give it ls as an example, it'll just run ls. So let's go ahead and test that out. Let's call this commands, and I think it was foo bar baz, and we can see 3 total arguments, running command foo command not found, running command bar not found, baz not found. Okay, it's great they weren't found, but what if I just did like, I don't know, ls uname who am I? Well, it ran ls, it ran uname, and it ran who am I. This is what I wanted to show you. Bash technically does have an eval statement. It can evaluate things, but you don't even need it. Bash will just run this happily. I can put the name of a command in a variable and then run it. Like, I could say var equals ls, and then I can run $var, and it just runs ls. So this might blow your mind. This might be a little scary. It's all just string manipulation at the end of the day. I just wanted you to know how easy it is to run commands like that you take from the user. And because of that, how scared you should be, and how, not scared, but how aware you should be of these things, how easy it is to accidentally run a command that a user gave you. You want to make darn sure that you are not mixing user input with code that is being executed. So what I mean is, this line down here that I have, you should never do this. This is just to illustrate a point. You should never have code like this. This is not how you want to do it. You do not want to mix user data with code that is being executed. That is a recipe for vulnerabilities if I've ever seen one. So be very mindful of this, but I wanted to show how powerful this is, how you can actually do stuff. And there's ways you can do this safely, of course. I'd probably do a case statement over a couple commands that I allow and then execute them in a way I like, blah, 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 blah. Yeah, you can do this in a way that's safe, but just be mindful of this. You just put a command in a variable and you can just execute it. Like, there's no rules. All right, so now I'm going to show you just a couple useful commands you can actually use on your day-to-day. So what we're going to do here is we're going to move Arithmetic Expression, Command Substitution, and Process Substitution into the done directory because we won't need them right now. And if we ls, we can see that there are two new files here that I've created. We have a simple CSV, a comma separated value file, and a complex one. I'm going to show you the simple one first. You can see that it's comma separated value. We have name, age, city, and favorite color. So we have Alice is 30, New York, blue. This is just some like basic data I found on the internet. It's just, you know, random, not important data. I don't know these people. But as you can see, we have 4 people: Alice, Bob, Charlie, and Dana, A, B, C, D. Very easy to work with. And what we can do is I can show some basic sort of shell style CSV parsing. I'm going to show you some commands you can use to parse the stuff. These are commands that are useful to have under your belt. Later in this course, I'm going to talk about some advanced bash stuff where we won't need these commands, but I want you to at least be aware of these commands because they are super useful. I still use a lot of these commands on a daily basis. So if we look at our simple CSV here, we have this. That's awesome. What can we do? Well, there's a couple things we could do. The first thing we could do is we could change the commas to be something else. Well, what's that something else? Well, we could change it to be like a tab character if we wanted to. And now look at this. Hey, that's suddenly like spaced out, way easier and way better to read. So TR is great. It can translate one character to another, so we can swap out the commas for a tab. But we also have another command. We have cut. Cut's useful because we can break like an input stream or a file or anything based on certain characters, and we can extract certain fields from it. So let me show you what that looks like. So if we cat our simple CSV, let's go ahead and let's cut it with a delimiter, -D for delimiter of comma and -F for field. So let's say we want the first field. There we go. We can just extract the first field. As long as we tell cut what character to use to cut and we give it the field number, notice that it's indexed by 1. It's not indexed by 0. We can do that. We could do 2 and we can get the age out of it. We could do 3, we can get the city out of it. Super powerful, super useful tool, incredibly powerful. Really love it. You can also do 1, 2, and we could pull that out. You could do 1-3 and we can get the first 3 fields. You could do 1-2, 4, and you could get fields 1, 2, and 4. You can mix and match all this stuff. The cut command, the TR command, both these are just super useful. So we could take this and we could pipe this into TR. And we could say, you know what, let's do the same thing. Let's turn that into tabs. And now look at this. We have names, we have age, and we have favorite color. Super easy way of formatting the data. The only thing to keep in mind is this isn't true CSV parsing. We are just splitting based on a comma character. So if we were to look into our complex example here, we can see that some of these locations, like New York has quotes around it, but it also has a comma in it. Is that going to be a problem? Well, yeah, it is. So let me show you what that looks like. Let's cat this complex one, and let's say we have a delimiter of comma, and we want the field 1. Hey, we get that just fine. We want the field 2. That's awesome. That seems like it's working. We want the field 3. Well, the location is New York. This one's Chicago. This one's Boston. Oh, that's just misspelled. I don't know how that happened. Let's go ahead and fix that. There we go. Boston. Yeah, that looks right. So what you could do here is you could do 3 hyphen. Don't give it a number. You could just do 3 hyphen and it will go until the end of the file. Now, this is great for our example, but in other CSVs, it might go way longer than that. So just keep this in mind. This is not a CSV parser. We are just splitting on commas. But the cut command is super useful because it can split on like anything. There are all sorts of things it can do. There are, what was it? Path is here. And we have all my different paths. I could pipe this to cut. The delimiter in path is a colon, and the field we want is the first one. I can see that's the first thing in my path. It's right there. I could grab field 2, and I could see that opt homebrew bin is the second one. If I were to do the third one, it should be users Dave cargo bin. Let's go ahead and test that. Users Dave cargo bin. So the cut command is super useful. Definitely something to have in your toolbox. Definitely something to have up your sleeve. Really useful command. TR as well, translating text, being able to take an input stream and make modifications as it goes through. Super useful. I'll talk about some other commands too that are super useful. Okay, now we talked about cut, we talked about TR. I want to talk about some more commands that are super useful. Again, these are not bash specific, these are just commands on your operating system, but it'd be hard to do a bash course without talking about these commands because they are super useful. Again, I'll be talking about more advanced topics in bash where we won't need these commands, but you should at least be aware of them. If no one's taught you them before, hey, I'm glad I could be the first. If you've seen these before, you're not upset because you know how powerful these tools are. I would never get sick of hearing about them. They are that useful of tooling. So yeah, in order to get started here, we're going to do something very fun here. We are on my Mac, but for this example, I don't want to be on my Mac. I want to be on Linux because this file is going to be easier to parse. So I'm going to SSH into my machine. The machine's name is void. It also happens to be running void Linux. So now we're on a Linux virtual machine that I have that's downstairs in my house right now. So the reason we're doing this is because we can look at a file, etc password. So let's go ahead and look at this file, and I wanted to be on my Mac, or on Linux specifically, because my Mac has like so many entries in this. This has very few entries. It's way easier to parse and way easier to understand. So this file, if you've never seen it before, these are the users that exist on this system. So there's a root user, there's a nobody user. There are some users that start with underscores because they are for like system services. There's a Dave user, and I've installed my own Nagios user. There's also an underscore Nagios. Not sure why there's two. Why is Mosquito even on here? I don't know. I haven't logged into this machine in a while. I don't do much. This is just my like Linux testbed machine. So there's probably some weird stuff on here. But as you can see, we have the Dave user, we have root, we have nobody. This file has a format to it. As you can see, it's separated by colons, and instead of me telling you what it is, we can actually just get the man page for it. So we can man password, and password is a command. So we pulled up the section 1 for it, change user password. But instead of pulling up the man page for this, we can pull up, I'm gonna do this off the top of my head, man 5? Oh, I'm a legend. Okay, we can pull up section 5 of the password, and this is on Linux, this describes file formats and conversions. So this is super useful because this tells us what the etc password file actually looks like. So you can see it contains one line for each user account with 7 fields delimited by colons. These fields are name, optional encrypted password. You usually won't find a password here. You'll find that in the etc shadow file instead, which will have more lockdown permissions on it. The numerical ID, the numerical group ID, the username or comment field. So this is just like a user specified field. The home directory and an optional user command interpreter. So this would be like their shell. So with that knowledge, knowing all the fields we have, we can cat etc password, and we can see all this stuff here, and then we could pipe that to cut, of course, delimit it on colons and grab the first field, and there we go. There are all the users on here. Of course, if you didn't want to use cat for whatever reason, cut also takes the name of the file. You could put etc password here, and then you cut out a pipe, you cut out a subshell, you cut out the usage of cat. For this example where I'm teaching you, I like to put it at the beginning because then I can make quick modifications here without having to backspace over the entire file. So if I were to put this in a script, I'd probably approach this way differently, but I wouldn't be doing cat pipe into something if I were doing it in the script. But on an interactive example like this, yeah, I'm definitely doing it this way. So there's our user accounts. There's our encrypted password. As you can see, no one has it set there. We're all using etc shadow. There are the UIDs, the user IDs, the numeric user ID. So actually, let's go ahead and grab field 1, 3. So we can see, and let's grep for Dave. That's me. So we can see Dave has UID 1000. Who am I? Dave ID. This is my UID 1000. My GID is 1001. And these are the groups I'm in, the supplementary groups. So I'm just using this command to show what this is, and then to show that etc password also mirrors that. So if I were to cut for fields, what is it? Fields 1, 3, and 4, that should be my username, my ID, and my GID. So it should be Dave colon, well, it should be Dave space 1000 space 1001. There we go. That's awesome. Not space, colon, sorry. It uses colon because it still uses the same delimiter character. That makes sense. So that's awesome. What else was there? There was 5. Was 5 a comment? Yeah, 5 is a comment that's optional. As you can see, it has my full name here. That's awesome. This is just like human readable string, so I could look at this as a system administrator and try to understand. I could put a useful note for myself, like what this user is for. 6 should be the home directory. So as you can see, my home directory is here. Some of these are set to var empty. They don't have one. Nobody's literally set to dev null. That's pretty awesome. And then the last thing we can do is we can get the shell with 7. I'm going to also print the username, just make it easier to see. So of course, I'm using the bash shell. Root, set to bash. Nobody, set to bin false. You might see some bin false. You'll see some sbin no login. These are ways of denying a user a shell. So like the user Nagios can't get shell access. I'd have to look in to see why some are no login and why some are bin false. I think they effectively work the same way. I don't know if there's differences when it comes to logging in on an actual console. But long story short, root has bin bash and Dave has bin bash. That is what my shell is. And you can parse etc password using this tool, which is super awesome. Now here's the thing. If I wanted to make modifications to this file, I can absolutely vim this file. You probably shouldn't. I've absolutely done it in the past. Of course, most system administrators I know have definitely done this. You shouldn't. There are tools to modify it. There is user mod, which can modify certain things about a user. It could probably change their shell. CHSH to change a user shell. If I run this, it'll ask me what I want my new shell to be. So you won't ever really need to modify this file, but I want to show you just using this file as an example. Not going to make any modifications, but I just want to show you some of these tools using this file because it is really cool. So we can't etc password. Let's go ahead and pipe grep for Dave, and then let's grab these 2 fields out of it. That's awesome. All right, so what if I wanted to change the username? Again, I'm not actually going to change anyone's username on the system, but what if instead of Dave, I wanted to say something else? Well, we know that I can change A to O, and now I can say dove, but then dove executes bin bosh, so that's not great. This is not a bosh course, this is a bash course. So stupid, I'm so sorry. But what I could do is if I wanted to change Dave to something else, there's an easier way than doing DAVE here and just changing it to XXXX because that'll change every instance of D, A, V, and E. It treats them as individual characters. What I can do is I can edit this stream. I can use a stream editor. I can use sed, my stream editor. So with sed, it takes a very specific notation. You may have seen this before. I'm going to put the whole thing in quotes. You start with S, and then you typically put a character here. It's usually a slash, but we'll talk about that. I'll put a slash here. The thing I'm looking for, Dave, slash the thing I want to replace it with. Let's change it to buddy. Notice it doesn't have to be the same amount of characters. Slash, and then close that quote. So it runs off my terminal. As you can see, it's going to get a little bit gnarly here. But I run this, and now buddy has bin bash here. Again, I didn't actually make any changes. Nothing changed on my file system. This is just changing what prints to the screen. So I'm not making any system changes here. I'm just illustrating a concept. Using sed, we can do basic find and replace. But sed, of course, very powerful. Instead of changing D-A-V-E, I could do D, any character, E. So it supports regex pattern matching effectively. There are different versions of sed. Some sed supports a very limited version of regex. Some will have like a more Perl compatible regex. If you don't know what I'm talking about, go down the rabbit hole of looking into regex. What I'm saying is regex. Some people get upset with me. They want me to say regex. I'm never going to say that. But it's short for regular expressions. That's what I'm saying here. These are what goes in here on some versions of sed. So sed is one of those tools. It's going to be on all your systems, but it might work slightly differently. Right now I'm on Linux, so I'm using the GNU variant of sed. On my Mac, the sed over there works differently. That's why, again, later in this course, I'm going to talk about some things where we won't really even need sed or tr or cut or anything. We're going to do all of it with bash. But for now, I think these are important tools to use. Like, these are important tools to know about. They're great. I still use all these on a daily basis. They're so quick and easy to just make quick changes to files. They're great. They're wonderful tools. So we have this. You might also see some people will do -E for expression. The thing here that's nice about this is I can do another -E. So now I could change bash for, let's say, I don't know, fish. Maybe I wanted to use the fish shell. So now we can do multiple expressions. So buddy is using bin fish as an example. Sed is super great, especially if I wanted to change my shell. Now you may notice there's a problem. My shell is bin bash, but it also uses slash characters. So if I want to change bin bash to, I don't know, bin fish, that's way too many slashes. The nice thing about sed is I don't have to use a slash. Slash is convention. I can change this. You could change it to a pipe character. You could change it to a pound sign. I've seen people use both. I'm quite partial to the pound sign or the octothorpe. If you think of pound sign, you think of like money. I'm American, so in my mind, the pound sign is just the little octothorpe guy there, the hash mark, whatever that is. So we can use that. We can put bin bash here, bin fish here. Sorry, that's kind of hard to read. I'm going to go ahead and condense these two lines. Let's go ahead and grep Dave out of etc password, just so we have less runoff on the screen. There we go. So you can see bin bash here, and then this little pound sign, bin fish, and then the little pound sign. You run that, and then it goes ahead and makes that change. So that's something cool about sed. You can just swap out that delimiter character. It doesn't matter too much. So now I want to talk about another tool. I'm going to talk about awk. Awk is amazing. It's incredible. I love it. I took some time, maybe 10 years ago, to really study and learn awk, and it has been one of the most beneficial things I have done. I would recommend you do it. I am going to give you the world's quickest crash course in it. I am going to touch on 0.01% of what awk can do, but I'm going to talk about basically the ways you'll probably see it most often in the wild. Take some time, learn awk. I could make a whole 10-hour course on awk. It is so powerful, the things you can do. So hey, if this course is successful, maybe I will. But let's focus on bash first. I'm just going to give you a quick little deep dive into awk. So we have this whole thing right here where we have grep Dave out of Etsy password. We cut for the fields we want, blah, 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 blah. We can use awk. So let's keep it simple. Let's do our cat Etsy password. And awk, of course, can read in from standard input. It can also read in a file. If I were putting this in an awk script, you can actually make awk scripts. Yeah, I would just pass in the file. I wouldn't pass it over standard in, but we're illustrating a concept here. So with awk is its own language. So I can open a curly brace, and this will run for every line of input. If I print $0, remember, this is all in awk. $0 is not a bash thing in this context. Because it's in single quotes, this is all being passed to the awk program. $0 is just the line in its entirety. $1 is the first field. Notice how it broke the field? It broke the field on white space. By default, awk breaks it on white space. If I want to modify it, I have to give it to an argument, -F, and then the field that I want to use is the delimiter. So in this case, I'm going to use the colon. So now when I do this, there's the first field. There's the second field. There's the seventh field, which is the user shell. So now, let's say I wanted to get just the user Dave out of it. I printed $1, I could print $1, $7, and now we have, notice there's no space or anything. You can put a comma here, and we can get a space between the two of them. There is also a printf notation built into awk. So I could say %s has shell %s new line and put these as arguments, semicolon, and run it. That's a lot. I won't keep it because it makes the command get really gnarly. I just want to show that awk has a lot of things built in. Let's go back to this notation. We have $1 and $7. Let's say we only want Dave. Of course, we could grep Dave and do that, and that works just fine. There's nothing wrong with that. But we're here. Let's use awk. We can go here, and at the beginning, we can put a conditional here. So we could just say $1 equal Dave. Yeah, that's it. You run this. I'm going to get rid of the grep. As you can see, we pipe it into awk. We have $1 equals Dave. So if $1 is equal to Dave, then we will run this line here. There you go. All in awk. We can get rid of a lot of that pipeline, the cat, the grep, the tr, all that stuff. You can get rid of all that just by doing this. Of course, if you wanted to, you could even get rid of the cat. We could replace this with this syntax. Do you remember this? We're going to read in from the file as standard input. And now awk's is reading standard in, but no cat was being forked and exec. So you can get these scripts to be very small and very elegant. Now we could do something different. Instead of just getting Dave, let's go ahead and get all the shells. So $7 is the shell. And there we go. You can see there's a lot of shells here. What we could do now is I will show you some other commands. You could do all of what I'm about to do in awk, but again, it's just a crash course. I can't dive into all the specifics of awk, really. I love awk, like I really do. I'm so, oh man. If I were to ever get off my bash shtick, I'd be jumping on awk and making content about that because it's just so powerful. Now that we have this, we can pipe this to sort. Sort is a new command I haven't taught you guys, but guess what it does? Sorts the input. Very simple. That's what it does. It sorts it. It's amazing. Now I could pipe this to unique. Unique is another command. Unique will just leave you with the unique outputs. Your data has to be sorted first, so you have to pipe it to sort and then pipe it to unique. So these are the only ones that were unique. As you can see, bash was twice, false was twice, and no long it was some number of times. Luckily, unique takes a -c. So here is a frequency count. This is how to do a very simple, a very basic frequency count by piping to sort and piping to unique -c. If you can get your data down to just a list of things, you could pipe it to sort and unique -c, and you can see how many times each one showed up in that input stream of data. Super awesome. Super, like actually super awesome, super useful. And there's another thing I want to show. Does Linux? Oh, my Linux machine doesn't have user shared dict word, so I'm going to back out of here, Control D, end my SSH session. Now I'm back on my Mac. And let's go ahead and cat user share dict words. And we've done this before. We grepped -c for Dave, -c for count. So 11 lines contained Dave in it. That's great, but there is another command I want you to be aware of, and it's called word count. Word count is incredibly useful, like incredibly useful, because I can run word count -l for lines, and I get the same information. I get 11 here, I get 11 here. So word count is super useful for being able to count lines. It also counts words. So keep that in mind. Because let's do something different. Let's get crazy here. Let's do a man ls, and here is the man page for ls, right? Well, I could do man ls pipe grep for Dave, and you know, it's really sad that my name doesn't show up in the ls man page. How upsetting is that? Let's look for a word that will be there. How about the word file? I bet the ls man page uses the word file somewhere. Hey, there's a lot of lines there. That's awesome. Let's go ahead and pipe it to word count -l. There are 70 lines there. 70 lines in the man page for ls contain the word file somewhere in them. In fact, of those lines, we can do -w, there are 738 words. And of those words, there are 5,100 characters. So word count -w for words, -c for characters, or on its own, you get all three. There were 70 lines. Of those 70 lines, there were 738 words, and of those 738 words, there were 53 characters. This is also, you should be careful about this. This is not like Unicode aware. This is not like emoji aware. This is just counting bytes. So WC-C is actually just super useful for counting raw bytes. So something to keep in mind, something useful. But yeah, these tools are really great. When used in conjunction with each other, when passed over pipelines, like I want you to see just how powerful these tools can be. Of course, the later parts of this course, I'm going to be showing you how to avoid a bunch of these tools to do things faster by using the bash built-ins. But that's the point. I want to start from the very beginning and kind of work my way forward with all of this stuff. And I want to intersperse commands that have been around forever with some syntax that's brand new, and just try to show how this stuff evolves over time and give you a little bit of the history of it, and also bring forward the useful stuff. Like, we're talking about tools written in the 70s and the 80s, and they're still useful today. Like, they're awesome. Like, many of them are just feature complete, and that's an amazing, feature complete is one of the best stamps of approval you could give a piece of software ever. Like, I will stand by that. Okay, so another command I want to talk about that's super useful is the find command. The find command is super useful for finding files on your file system. So if we ls here, you can see that we're back on my Mac and I have the CSV files here. If we ls done, there's a bunch of files in there. If I were to run find and give it the current directory as an argument, it will find all the files in my current directory, and it will recurse. It will traverse the file system. It will go into subdirectories and find every file it finds, printing it. Look, there's even a little Mac built-in file there. How annoying. So from here, we can do all sorts of stuff. We could say find dot, but I only want to find regular files. So type F. So as you can see, this filtered out the directory done, and this filtered out the dot. So we just have regular files. By contrast, we could find directories. So these are the two directories that it found in here. Also, if we were to find an empty directory, luckily on my system and most systems, you will find var empty. It's an empty directory. Find var empty. We run this, and all it found was itself. If we do type F, actually put an F there, it found nothing. There are no files in there. For this next example, I'm going to log back into my Linux box because it's a file system I'm more comfortable with. Let's find all the files in user share. So there will be a lot. And as you can see, there's a lot here. We could pipe this to word count -l, and we can see that there are roughly 18,000 files found here. Okay, that's a lot. We could do some other stuff. We could do type F for just the plain files, and we could do type D for just the directories. Okay, that's interesting. So if we take these two numbers and we add them together, they should be the same, right? 1231 plus 15593. If we add these together, we should get 18098, right? Not quite. What's that discrepancy there? Well, there are other types of files. We have talked about -F for a regular file, -D for a directory. There are symlinks. There are named pipes. There are sockets. I don't know what user share has. I'm willing to bet it's probably just symlinks, but let's go ahead and list the symlinks because there are other types. L for symlinks. Oh yeah, there's a lot there. So let me do this again. We have F, we have D. Let's go ahead and do the L one and pipe that to word count -L. And what is it without any of them? It is that. So if I go back to this echo here, 1231 15593 plus 1274. We get 18098. So there you go. So we have regular files, we have directories, we have symlinks. In the man page for find, it should list all those. I'm going to search for -type and see what actual types there are. This man page is gigantic. Oh my god. Here we go. Wow, this took a while to find. The man page is gigantic. At least we know how to search through man pages now. So D for directory, F for regular file, L for symbolic link, sockets, blocks, characters, directory. I already said that, name pipe. Door. So on Solaris, you're going to actually have a door. Oh, that's so funny. I'm on a Linux machine. I didn't realize the GNU find was aware of that. Yeah, because on my Illumos machines, there are definitely files that just exist as doors. Now, there are other things we can do. I'll give you a quick little crash course on find, because we have find, user, share, type, F, and these are all the regular files that we found. As you can see, there's all sorts of different files, like text files, for instance. We can just filter on text files. -name star.txt. Notice that I'm putting in quotes. This is very important. I don't want bash to expand this glob. I want find to take this as a wildcard. So let's go ahead and run this, and we can see that, oh look, we have some text files. That's significantly less. Hey, that's kind of nice. Word count -L. There's 193 text files in user share. That's pretty cool to be able to answer these questions pretty quickly. You can operate on these too. I can pass this to exec, and then I can execute a command on each file. So this can be very scary if you exec rm, for example, but I can exec like echo, hi, I found a file, open and close parentheses. That's a special syntax to find, letting it know to put the name of the file there. Yay. And then I need to tell find that we're done. So I have to give the find command a semicolon. This is not a bash thing, this is a find thing. So I have to give it a semicolon, but bash will interpret that. So I have to either escape it or I have to put it in quotes. Either one is valid. So as you can see, for every file it found, it executed echo, and it said, hi, I found a file. Yay. I'm not going to quiz you on the syntax, but it is useful to know. I would say get comfortable using the -exec with find because it is powerful. If you want to batch process it, get comfortable piping it to xargs. Xargs will take a program, like I could say echo hi, and it will append the name of the file to the end of the command here by default, but it will batch them. It'll batch them in an optional, like you can change the size of the batching. So if you have like 10,000 files and you want to delete all of them, you could batch them in RM 1,000 at a time using xargs. If you're on Linux, you probably have print 0 and xargs -0. Get used to doing that because that separates the files based on null bytes and not new lines, because file names can have new lines in them. I talk about that a lot on my YouTube channel, and it can get us into some weird, hairy situations. I'm not going to talk about it too much in this course. It's not really relevant for this course in terms of learning. If you're interested in all those gotchas and stuff, I would definitely say, like, go check out my videos on my, YouTube channel. Obviously, I'll put the links and the references and stuff because I like to talk about all those weird gotchas. I like to make files with colors in them, so when you ls you can actually see colors, or it makes your terminal move around because it moves the cursor. That's all possible, and I like to have fun with that. In this course, I'm not going to assume that you're on a system that I've messed with, so I'm going to assume that things are safe and predictable. Okay, so yeah, but yeah, that's useful. The find command is super useful, and it recurses by default. Does find have a depth? I think I might be able to say depth 1 or max depth 1. Oh, it's even yelling at me. Find, you definitely have to make sure you put the expressions in the right order. The order 1000% matters. Is it depth 1 like this? This is what I get for trying to make up syntax off the top of my head. Look at the man page. Don't trust me here. I'm not an expert when it comes to the find command. I use it sparingly. I don't really need it that often. So yeah, definitely take some time to learn it. I'll do the same because apparently I don't even know what I'm talking about here. But yeah, that's the find command. All right, so now I want to talk about arguments you can actually give bash. This is a little confusing because we've written bash scripts that have taken arguments from the user. In this case, we can call the bash interpreter, the actual bash executable, with arguments and modify its behavior a little bit. So I want to talk about this. They're super useful. I have a couple scripts that I've already written and we're going to run through them together. So let's take a look at the first one, 00 simple script. All right, so as you can see, the first name is John and the last name is Eddie. Well, that's not right. That's not my name, but we'll get to that. First name is John, last name is Eddie. The full name is first name space last name. So we're making a new variable called full name. And then we check. If the first name is equal to Dave, we go, oh, hey, it's Dave. That's nice. And then no matter what, we run hello full name. So, okay, that makes sense. It seems pretty straightforward. Let's go ahead and run this. And it prints hello, John Eddie, because John is not Dave. So let's go ahead and pull that source code up so you can see it at the same time. And it doesn't print, oh, hey, it's Dave. It just prints the hello line at the bottom. That makes sense. This makes perfect sense. So what am I going to show you here? Well, you know how we're running it with /? We could change that. We could run bash 00 simple script, and this will give us the same thing. But there is an argument we can give bash. I already kind of showed it off a little bit because my muscle memory kicked in. Bash -x. This puts bash into like a debug mode. This is super useful. I love this. This is great for debugging scripts. I wanted to give you this sooner rather than later in the course because this will be super useful when you're trying to fix broken scripts. Bash -x, if we run this, it prints a lot of stuff. It prints what it's doing. So convenient. So the first thing it does, it sets first name equal to John, sets last name equal to Eddy, full name becomes John Eddy. If John equals Dave, as you can see, that's going to fail. That actually fails, so we never run the oh hey it's Dave, we just run the hello John Eddy, and then you can see here's the output of running that echo command. So that is super awesome. Let's go ahead and modify the script. If we were to change the first name over to what it rightfully should be, let's go ahead and put that source code up here. Let's run that, and then we can see, oh hey it's Dave. Hello Dave Eddy, we got the oh hey it's Dave. Bash -x on that, and you can see Dave equal Dave, well then we know it's true, so it ran the oh hey it's Dave. So that's really nice. It is a really great way of being able to trace your programs. If you're running into an issue, think of this as like your bash debugger. You can also, here's something cool, you can turn this on and off at runtime. So you don't need the user to know how to type in bash or bash -x. You can turn it on here. So I can run set, and then I can turn on bash arguments here. Set -x. If I put a set -x here, then it will have the same effect no matter what. This is useful. If I've written programs in the past where I've had like a debug flag or a verbose flag, and if you specify the debug flag, I will turn on set -x for you. You can definitely do some cool things like that. The nice thing about set -x is if you get sick of it, say you only want a certain section to do that, you can do set +x here and disable it. So you can wrap a section of this. -x to turn it on, +x to disable it. So now when I run this, you can see that we did the first name, we had the last name, and then the last thing was us turning it off because it actually does show that. So set -x, super useful to have that under your belt. And one of the last things is we can modify the PS4 variable. So I'll talk more about these variables later in the course, but if we set PS4, not PlayStation 4, but if we set PS4 to hello, :space as an example, and then we run this, that plus sign is actually what PS4 is. So you can modify what it actually looks like. You can modify the debug part of your script. So you could do something like this if you wanted to. You could just say like, debug, and then it makes it very clear like what you're debugging. You could put color output in there if you wanted to or something like that. So yeah, super useful. Bash -x, commit that to memory because oh boy, it is super useful. Let's move on. We have the next one called syntax error. What do you think's happening here? Well, if the name didn't give it away, we have a syntax error. We echo hello, and then we say if true, which is fine. We echo goodbye. FII. FII is not right. That is not how you end a if statement in bash. So let's go ahead and run that, and what do we get? We get hello. So it printed hello. If you remember the script, it prints hello at the beginning, but then it gives us an error saying there was a syntax error. Wouldn't it be nice if we could detect this syntax error without having to actually run the script? Well, you can. Bash -n. -n is a way of doing syntax checking and syntax checking only. A bunch of languages have things like this, very useful flags and stuff. Yeah, I think Perl has like -c, which lets you just syntax check a script without running it. Node.js, I know for a fact, has a -c argument because I was the one who added it in 2015 because I wanted it. I was a big fan of bash -n. We used it at some CI CD thing where I worked, and I wanted it for Node.js. So yeah, if you're using Node.js --check or -c, thank me. I was the one who implemented that. No, seriously, like it was an easy thing to implement. It wasn't that big of a deal. I just wanted it. But I'm a big fan of this. Like I'm such a big fan of this. So bash -n gives you the same syntax error. It returns an error code so you can detect this, but it doesn't run the code. That's the beauty of it. It does not execute that code because that code would be dangerous. If we were to go in here and fix it, so there we go. Now it's valid. We can run O1 and it works just fine. We can run -n O1 and it prints nothing and returns 0 because it's syntactically fine. How cool is that? Let's go break it again before I forget. And let's talk about the last thing, which is undefined. So here we have foo equals 1, bar equals 2, foo is foo, bar is bar, and baz is baz. So you notice there's no baz definition here. So what happens if we run this? What happens if we just run this here? Well, foo is 1, bar is 2, and baz is empty because it wasn't set to anything, so nothing happens there. There is something that is super useful, bash minus u. So this will check for undefined variables. If we were to run this, we can see that we get an error message there when it happens. It still goes through and runs it, but we get at least an error message when it actually encounters that. You can combine these two things together and it doesn't work the way you want it to. So don't expect that to work that way because you kind of need to check at runtime. You can't like statically check if it was defined or not. So don't try to think you combine those two things. You use this and this blows up when it encounters the unbound variable. Now be careful with this because I know a lot of people like to run with this being on 24/7. You can get into some weird situations if you don't manually unset or initialize your variables. And what I mean by that is I can set an environment variable. I can cheat. I can run O2 undefined and I can set baz equals haha right here and run it. Notice the space between the two? That defines baz as an environment variable for the program O2 undefined for the duration of its existence. So bash, by default, its variable scope is the same as your operating system's environment variables. They are the same scope. They're the same names. They live in the same namespace. So be careful about that. If you're checking, oh, is this variable defined? Make sure you, the programmer, have like initialized it somewhere or declared it because you're just going by what the environment is. That might be what you want. But be careful if it's not what you want, because you can definitely override it. In fact, I could do something like export baz equals whoa, and then do this. Now, if I run this again, haha wins because haha is closest. But if I don't have it there, and I'm running on someone else's shell who may have exported that variable, meaning put it into the environment, look at that. So be mindful of that, because if I were to run this, that's not a bug. It doesn't consider that a bug. It doesn't consider it unset. I was the one who unset it. Now I could, what is it, unexport? No, unset. I could just unset baz, and then if I rerun it, now it's an error. But be mindful of that, okay? You don't necessarily know the person's environment in which they're running the script, so make sure you declare initialize variables. If I'm gonna use a variable in a script, you're gonna see me declare it at the top, even if I set it equal to nothing, even if I just go baz equals that at the beginning of my script. That's a totally valid line of code, and that's like just setting it to nothing, basically. The last thing I want to talk about is a super useful tool. I love this tool. I should be using it more often. I showed you solutions to fix these problems using bash, and I like that, bash minus n, bash minus u, because I am using the version of bash that will be executing these. There are also ways to statically analyze your code, and the program I really like is shell check. Shell check is amazing for checking both POSIX shell scripts and bash shell scripts. It might do more, but I definitely can check bash scripts. So you give it the name of the script and it will check for any problems. There were no problems with the first script. That's great. The syntax error one, there will definitely be a problem here. And look how nice this is. Couldn't find the FI for this if. It tells you exactly what's going on here. It gives you actual like error codes with their wiki links, so you can go look up what this error message means if you've never seen it. Also, if I were to give it the undefined example, you can see that it's not an error, but it's a warning, like, hey, you're referencing something, but you haven't necessarily assigned it. If it were in all caps, probably wouldn't yell because it would consider an environment variable. This one, I probably didn't intend that. So shell check is super useful. Love it. Really great tool. It's external to bash, so it might not be perfect. Like if shell check says something's okay and you're on an old version of bash, shell check can't be held responsible for that. So I still use bash minus n or something because it will tell me if that specific interpreter is able of executing the code that I give it. All right, now let's talk about pipe status. This is useful for debugging pipes in bash because pipelines can get very complex. Remember some of our examples where I was piping cat to grep to sed to awk to tr? They can get very complex and it gets kind of difficult to know when something's going on here. So let's go ahead. We're back in our foo directory. Let's move the CSV files into done because we're done with them. We no longer need them. That's great. So let's show what I mean by pipe status. Well, remember, every command has a return code. So if I echo hi, I can also check this and I can see that the call to echo was successful. That's really great. If I were to cat this doesn't exist and then we echo $? We can see that cat failed. It's non-zero. It's any number between 1 and 255, I think, is the max. So yeah, that lets us know that there was a failure here. That's really cool. What if I echo hi and pipe grep for hi? Well, that worked. Grep was able to find hi. So if I do this, you can see that we get a 0 here. What if I were to echo hi and pipe grep for buy? Well, if I rerun that, we can see there's a failure. Echo worked, but grep failed. $? Is always the last thing at the end of your pipeline. Now this is important to know, and it's important to work with this that way, because what if I were to do something like, let's cat, this doesn't exist. That file does not exist. And let's pipe it to tr, and we're gonna turn all the commas into colons. Remember, the file doesn't exist. Let's go ahead and echo $? It was successful. How weird is that? Cat gave us an error, but tr was able to successfully turn 0 commas into 0 colons. You understand how confusing this can get and how weird this can be? Something to be mindful of. $? is going to refer to the last thing in a pipeline. You can set -o pipe fail. This changes that behavior. I typically stay away from it. Some people seem to like it. I have issues with it. I have a whole video on my YouTube channel where I talk about why I stay away from it. It's not relevant to this course, so I won't dive into it specifically, but I want to show you how you can debug this stuff. So how if you're just in a normal situation, you don't have that option set, you can still debug what's going on here. So let's go ahead and take this example. Now that we have this, there is a built-in variable to bash we can access called pipe status. It is an array. So we can't just print it or else it prints the first element of the array. We have to put this here and we have to join it like this. So pretty gnarly syntax, but you've seen this before. We're just going to print out all the elements of the array, 1 and 0. So what that means is cat returned 1, tr returned 0. This is how you can find out if you have a very complex pipeline of like cat, pipe, tr, pipe, grep, pipe, cat. You have something like this. If I echo pipe status, I can see that, oh, cat was a failure. Tr, successful. Grep for Dave, failure. Cat, successful. So pipe status is super useful for figuring out, hey, in that last pipeline I ran, what happened? What was successful? What wasn't successful? You could also do something like this. You would never really write code like this because there's no data being passed between the two. But you can do true, false, and then if you print it, you can see 0, 1, 0, 1. So true becomes 0. That's confusing to a lot of people. True is a command that outputs success. Success is 0. False is a command that outputs failure. Failure is non-zero. So that's what's going on here, but you can kind of see it that way. Another way of showing this very simply is we can use subshells. I will talk about these more later, but if I use parentheses, I can run a command without actually having it affect my current shell. So I could run something like exit. If I were to run exit without a parenthesis, if I were just to run exit, my terminal would close, okay? But if I run exit in a parenthesis, then nothing actually happens because it happens in a subshell. So I could exit with a code here. I could exit with 4 here and nothing happens. I could pipe that to exit 7. These are very contrived examples. You would never write code like this. I am just showcasing something. Exit 100 and then exit 0. So if I run that and then we echo, what was it, $? What do you think it's going to be? 0, because the last thing in the pipeline was 0. Here's something very important. If I were to echo pipe status right now, there's only one thing in the pipe status. That's because the one thing in the pipe status was the command that's before it. So you better save this variable right after you run this command or else it's gone, okay? It needs to be the next thing you do. So if I run this, we can echo pipe status. Look at that. Look how easy. 4, 7, 100, 0. We exited 4, we exited 7, we exited 100, we exited 0. So this is how to get the return code of everything involved in a pipeline in Bash. This will be super useful when you're debugging pipelines because they can get kind of confusing. And you may have code where you're like, I don't care if the first command fails or the third command fails. I really care about the second command. I don't know what that code looks like, but you might have it. I have no idea. So that's what pipe status is useful for. And to wrap up this section on sort of like debugging Bash, one thing I really like is being able to time commands. You can time how long a command takes by simply using time. You just put a command after this and it will run the command and it will tell you how much time it took. There are 3 different things here, real, user, and system. I'll talk about them in a second, but this is super useful because I could time ls and I could see how long it took. I could time grep d from user share dict words and see how long it took. Now, these 3 different times, very simply explained, real is how long it actually took on the wall clock. This is the real time. This is a human had to wait for 0.081 seconds. I had to wait for 81 milliseconds for this to run. User time is how much of this was spent in the user space, and system time is how much of this was spent in the system or the kernel. If you don't know these, it's okay. Don't worry about it. Just focus on the real time. If you know about this stuff, then user space is how much bash is processing, and then system time is how much bash is waiting for the kernel to do something like read a file, or something a program can't do, but it has to ask the kernel to open a file, read a file, things like that, system calls, things like that. If you've ever looked at, I'll show you real quick. If you ever look at like htop, wow, this looks terrible on my terminal. But here we go. You can notice that this is the CPU usage of my computer right now. You see how some of the cores have green and some of them have red. I believe green is user time and red is system time. I might have that backwards, but green is how much your CPU is spent in user space. So that's like what a program is doing. If a program is doing heavy mathematical calculations or anything like that, system time is your kernel's doing work. So that could be my user space asking my kernel to read a file or talk to a network source, or that could be my kernel doing tasks of just like maintenance to keep my computer running. Yeah, probably won't be relevant for many of your endeavors with bash, but it's important to know the difference there. But the real time is actually how long something took. It is super useful to be able to know that. The thing about the time command is it is built in to bash, and it's a keyword, so you can do all sorts of like fun things with it, but you can actually like time an entire pipeline, I believe. Long story short, can you actually, hold on. Actually, let me test it. I think you can do this. I think I can do time ls pipe grep Dave, and I'd have to double check. I think it actually times the entire thing and not just the ls process because it's a keyword in bash. I don't actually know. If I were to have something like this complex, I'd probably be putting it in a script and then just timing the execution of the script. But again, time is also built into your system, so this can cause weird problems. I'll show you what I mean by that. Imagine if I were to run something like, who am I? We can see that it's Dave. Okay, that makes sense. What if I sudo who am I? Remember, sudo is a command that executes or elevates my privileges. So I'm gonna type in a little password here, and there we go. I'm gonna type my password in correctly here. Gonna remember what my password is for this machine. Wow, okay, I almost forgot my password for this machine. That's really funny. Let's just edit that out. Yeah, so I got my password in first try, perfect, no problems there. But as you can see, so who am I gives me root if I'm running with sudo, but it gives me Dave here. Why is this important? Because if I were to time what it took to call sudo who am I, or if I were to sudo time who am I, you get different output. And the reason I'm getting different output is because time is built into bash, and if it's the leftmost thing, if it's the first command I'm running the bash built-in time, and time is executing sudo with the argument who am I. So sudo is running who am I. This case is different. We're executing sudo first, we're becoming root first, and then we're running time. We've become root. Sudo is an external program. It can't go back into our shell and run our built-in time. It has to look for time on the system. So this is actually running bin time or whatever showed up there. Yeah, it's running user bin time. So this is the external command. So be mindful of that. If you're like, oh, I wonder what commands time take, or what arguments time takes, and you go look at the man page, and then you try to use some of those arguments, they don't work. That's because time is also built in your shell, and the bash version of time only takes the -p format. So be mindful of that. You might get some weird output. It does matter the order of your commands there. So that's kind of how to navigate around that. All right, so now we are back in our foo directory, and now we are going to talk about sourcing files. This is how in bash I can sort of have like a library of functions. Now bash is special because it can just execute external commands. So I could just have a whole directory full of commands and I can execute them no problem. And I could totally do it that way. I could also make functions or variables or anything like that in its own file, and I can source it in. Kind of like if you're in Python, you can import. If you're in C, you can include. Rust has all those beautiful crates. It's sort of like that in all those different languages. I know JavaScript has like a whole require, but then replaced by, what do they use now in JavaScript? Import? I don't know. I haven't written JavaScript in forever. But let's go ahead and do that in bash. So to get started, we're going to write our own little program, and we're just going to call our program say hi. All right, so say hi will be a very simple program. We're going to follow the whole greeting thing that we've been doing a lot during this. So we'll save this, chmod +x, vim it. There we go. Now we can do a couple things. We're going to want to greet Dave. We're going to want to greet John, and we're going to want to say goodbye to Buddy. Now here's the thing. We don't have greet and goodbye as commands, so we have to define them up here. So let's go ahead and make some functions here. We'll make a greet function where we will say echo hello $1. There we go. And then we'll make a goodbye function where we will say echo goodbye $1. There we go. So now we have our two functions here. And if we run our script, it should just say hello, hello, and then goodbye. There you go. Perfect. Hey, works just fine. Now here's the thing. What are we talking about with sourcing? Well, we can take these functions and we can put it into a different file, and we can make it accessible to any of our bash scripts in this directory. So let's go ahead and do that. Let's go ahead and make a dir called lib. So now we have a lib directory where we will put our library of like functions and stuff. So let's go ahead and cp say hi into lib greet. So we will make the library called greet, or we'll call it greetings. How about that? We'll call it the greetings library because it has a whole bunch of greetings. It also can say goodbye. Probably should have thought of this name before I started writing it, but hey, here we are. Let's open up that library. Now we have the greet function, we have the goodbye function. Let's go ahead and delete those. So we just have function declarations. We can run that. We can run lib greetings and it will define those functions and nothing will happen. That's what it does if you run it, but we're not really interested in that. We want to source them. So let's go back to say hi and get rid of the definitions for those functions because they're already defined in our greetings library. And let's go ahead and source that. We can use the source built in and we can source lib greetings. So now if we were able to successfully source that, there you go. We have access to those functions. Remember we talked about bash minus x? We could do that here and we can kind of get an idea of what's going on. We source lib greetings, then we call greet Dave, and then there you go. It works because the function was defined in that sourced file. That's super nice. That's super convenient. You may have also seen this instead of the source keyword. You may have just seen a dot. This also works. And this will work exactly the same. Now in other shells out there, I believe ZSH is a shell where dot and source are slightly different. They have different semantics on how files are resolved. I believe that's the case. I could be wrong here. But in bash, that is not the case. If we do a help on source, we can see that there's a whole big long help message. That's super nice. And if we do help on dot, you can see that we get the exact same message. They are exactly the same. There's no difference between them. Source and dot in bash are exactly the same. Dot is what you'll see in POSIX shell scripts. Source, I believe, might only be in like bash or other shells like that. So dot is definitely more portable if you're trying to target something that's not bash. If you're in bash, you can use source. I tend to use dot. The other thing about dot is that it could fail. Imagine if I had a typo here, if I had like greetings with a Z. Well, that's not going to work. So let's go ahead and run that. And we can see that, oh, we got no such file directory, and then it failed to run all that stuff because it kept trying to go. So we could do this. We could say like, if not source, then we could write that and we can catch an error saying like, uh-oh, greetings wasn't found. You could also do it in one line. I've seen people do really simple things like this. I do it myself. This. So basically we're saying, hey, try to source this file. If it fails, then just exit with an error. There's nothing else we can do here. So if you run this now, you can see that we try to source it. We don't move on. We don't run any other commands. We just try to source it and we move on with an error. The nice thing is if we change this back to an S, then everything should work and we get our greetings. Hey, that is super awesome. The cool thing about this is we have our say hi script here. We could also have, we could CP say hi to, I don't know, say bye. And now we have a new script here, but it sources the same library. So we could just change this all to goodbye. There we go. So now we have our say bye script and we can modify our say hi script to only ever say hi. So say hi, we'll say hello to everybody. Say bye, we'll say goodbye to everyone. Even though they use the same underlying function on the hood, that's a way of being able to reuse code easily in bash, and they're functions, so they're fast. There's no forking out to external programs here, which is super nice. Another thing you can do here, which I find really cool, is source has this option of -p, which is really nice. It takes a path style argument. If you remember, path has a bunch of paths separated by colons. You can do the same with source with a -p. I believe this is new. I don't know when this was introduced. I say new, it could be 5 or 10 years old. Just keep that in mind. But the nice thing about that is if we go to our say hi script here, instead of having to hard code lib greetings here, we could do something like this. We could say libdir equals, or libdirs, we can specify multiple ones, equals /lib, just the name of the directory, and then you can pass it as -p here. So hopefully this makes sense what's happening here. But I specify libdirs to be /lib, and then when I source, I can give it as -p here, and I can just give the name of the file that's in that directory. So basically, bash will go through, search through every directory that's here, separated by colons. There's only one, but it will search every directory here for a file named greetings, and if it's found, it will source it. So this will work exactly the same if I run say hi. It'll work exactly the same. This is super nice because you could say override this. If you were making a library in bash and you wanted like a custom version of source, you could say like my source, make a new function called my source, which runs source -p /lib on $1. So now, instead of having to specify this here, I could just say my source greetings. Hopefully this makes sense what I did. I overrode source. I didn't override it. I made a new function called mySource, which just calls source under the hood, but already gives it the lib directory. So you could imagine this being somewhere else. Me, the programmer, I don't have to think about where the libraries are stored. They could be on different places. I just run this little mySource thing and it pulls it right from the library. So if I run this, there you go. It works exactly how you'd expect it to. One last thing I want to talk about this, which is super cool, super useful. If we go into this library where we have greetings here, something you might want to do is test this stuff here. So you may be inclined to just make sure like greet works. Like I should be able to greet Dave and I should be able to say goodbye to John, right? I should be able to do something like that. Well, you don't want to put that there because now if I were to run, let's say bye. Oh, I'm in the lib directory. If I were to run say bye, you can see that it put those things at the top. So any code you put in the library will get run. Source is effectively saying, hey, go to this bash script and run all that code as if it's in my current file. It's very similar to like include in C. So you don't want to put code that really executes here. You just kind of want to put like definitions of things. Maybe you want to put code that executes here, but just be mindful that it will get executed anytime someone sources your code. So Python has this beautiful thing. You may have seen it. If name equal, I think it's this. I may have had that right. I haven't written Python in a while. But if you look at that kind of syntax, you know that, oh, this code will only run if this file is being executed directly. If I'm just being sourced in or I'm being imported, it won't run. So Bash has something similar. It's a wild, gnarly syntax. I'll go and find out the source of this because I actually want to know where I originally found this from. I want to say it was one of the creators on the Bash wiki that linked to this. I love this syntax. This syntax is beautiful. It is so cool. And it's wild. So I'm going to write it and then I'm going to explain it. So there we go. If this thing is true, if this whole if statement is true, then we are being called directly. So this will only run if we're being called directly. If we run lib greetings, it will execute hello, Dave, and goodbye, John. If we just run our say goodbye, say bye, it won't print the hello, Dave, and the goodbye, John, right at the beginning. So it knows if it's being sourced or not. This is so clever. I was amazed the first time I saw this. So we have the parentheses here, which create a subshell. Again, I'll talk about that more later. The reason we create a subshell is so we can use the return keyword. Using the return keyword outside of a subshell or a function is an error. So we put it here. We don't actually return. We just check to see, are we able to return? We discard any errors. We don't want any error messages going to the screen. We just check, are we able to return? And then we negate the result. So let me explain. If we're able to return from this, then we are being sourced. If we are able to use the return keyword, then we are being sourced. If we're not able to use return, then we are not being sourced. So we just negate it. If we're able to return, if the opposite of that is true, if we're not able to return, then we're being called directly and this stuff gets executed. So that's one of those things where I can break down how it works, but just kind of memorizing the syntax is super useful, especially when you're getting started. So you can make library code, but you can have that library code actually do something kind of meaningful if you run it yourself. This is great for just like testing things, making sure your stuff works, stuff like that. So yeah, that's sourcing. I mentioned subshells. We're going to talk about them now because there is some good information here. Here is our lib greetings from last lesson. We're going to do something a little bit different. We're going to make this function a little bit bad, okay? We're going to say name equals $1, and we're going to say hello to name. That's what we're going to do, and we're going to say name equals $1, and we're going to say goodbye to name. Notice we are not using the local keyword. We are purposefully messing with the global scope because I'm going to show some of the differences here. So let's go ahead and make our new program, which will be curly verse parens. I'll explain that naming in a second, but let's go ahead and make a new bash script here. Bash, and then save that chmod +x curly verse parens, and let's go ahead and source that library. So lib greetings. We can be good here and we can check to make sure the source actually works, and we can exit if it fails. That's super good. Now we have our greet function and we have our goodbye function. So let's go ahead and do this. Let's say greet Dave echo $name. So let's specify our name here as Buddy. So we've specified name as Buddy. We've greeted Dave, and now we're going to echo what name is set to. So after greeting Dave, let's see what it gets set to. I think you already know what's going to happen, but let's go ahead and run this. So we got hello, Dave, and after greeting Dave, we got Dave. Dave shows up a lot. Can we use a different name for this? Let's just do name equals that, and we'll do name equals that. So before name and after name. There we go. So we have our before and we have our after. So our before name is Buddy. We greet Dave by calling the greet function. And now our after name is Dave. That's not great. As you can tell, the greet function was able to modify the global scope. So there's a couple ways we can fix this. Of course, we can fix this. We can do the local thing. If we just put the local keyword here, that fixes this issue. That is what you should be doing. You should be declaring your variables local in your function. That is the right way to do it. But there is another way to deal with this, and there's some other side effects. So I want to talk about this. Check this out. These curly braces are going to become parens. Now you may have noticed this. This is sort of a trend with Bash. If you remember the section I did on Command Substitution, you'll remember that there was a syntax with parentheses and a syntax with curly braces. The parentheses ran in its own subshell. The curly braces ran in the main shell. This is the same thing here. When you define a function, you can use parentheses instead of the curly braces, and this makes it all run in a subshell. So now, if I run this again, we can see that before name is Buddy and after name is still Buddy. We're not using local. We're just using parentheses here to make it run in its own subshell. So that is a cool little trick. There are some times where you may want this, sometimes where you don't want this. This is just a good trick to have up your sleeve with Bash. It is a super nice way of saying, hey, this function should always kind of run in its own world. Don't ever let it modify anything in the global scope at all. You can kind of force your function to do this. So say you're sourcing someone else's function. Maybe I'm sourcing a library where I didn't write this code. And as you can see, we have the curly braces and we're not using local. So we're being bad. If we run this, you can see name got overridden to Dave at the end. There's still something we can do. We can force our own code to run in a subshell by just putting parentheses around it. This is valid. This totally works. If you run this, you put parentheses around it, now it won't affect the global scope. It can modify global variables, but once that subshell is over, those global variables don't actually get modified. They only get modified within the subshell. So you can wrap your code in parentheses like this. This is totally valid. It works just fine. And of course, like I mentioned, you can also use curly braces. If you use curly braces, you have to put the semicolon in. This is also totally valid, but you will modify the global scope. Now you might be wondering, why would I ever want to do this? Well, the beautiful thing is that we can do pipelines here. So I could TR and replace A with O to turn Dave into Dove. I could do that like here in its own little world. And you may be wondering, why would I want to do that? Because then outside of this, I can pipe this whole thing to another program. So in this example, I could just have one in pipeline, but this is a cool way of chaining commands together and having compound commands. So I could pipe this all to NL. And I don't know if we've taught NL, but it adds line numbers, NL for numbering lines. So we can see that there's only one line here. So hello, Dove. So this is beautiful because this could also just be a parenthesis. Get rid of that semicolon, put the parenthesis here. So you can group commands together in a subshell and then pipe the entire subshell to another command. Pipelines are very powerful in Bash, as you can see. So really neat stuff, really cool things you can do with this. All right, so another concept I want to talk about is return codes versus output. We've talked about this before in the past, but I want to demystify it a little bit. If I run a command like uname, what does it do? It's an external process. It runs on my system. My bash shell forks and execs. That's how processes are made on Unix and Unix-like operating systems. So it forks uname and it runs, and you can see that it outputs Darwin. So it outputs the name Darwin to standard out, but it also has a return code, and we can check that. We can check if it was successful or not. We can see that 0, it was successful. So cool, that's awesome. Now, if we were to do this in a script, let's do return codes. We'll make a new script called return codes. chmod +x, standard stuff, no trickery here. Let's run uname and let's echo $?. So the exact same thing, nothing magical going on here. We can see that we get Darwin and we get 0. Of course, we can also capture this. So we've done this before. There isn't anything new here. We can do this. We can do this. We could say code equals $?. Remember, you want this to be right after the line. If I were to echo var here, I would actually get the return code of echo and not the return code of uname. So you want this up here, and then we can say output equals var, code equals code. So if we run this, we can see that output is Darwin, code equals 0. Hey, yeah, that makes perfect sense. And the important thing to remember is, what if we didn't want to use uname? What if we wanted to use our own mini program? Remember what mini programs are? myfunc. We can make our own function here. That instead of Darwin, we'll just echo YSAP for You Suck at Programming, my channel name. How about that? We're making our own little operating system. And we return 0. Success. We explicitly return success. So now down here, we don't have to run uname. We could run myfunc. Same exact thing. It'll get it ran exactly the same way, and we can see output is YSAP, code is 0. Hey, that's really cool. If we change this to 45, we can see that, hey, we get 45 there. That makes perfect sense. If we were to change this to 300, what do you think we're going to get? Uh-oh, we get 44. Be careful with return codes. They are limited. It is an 8-bit integer. They can be between 0 and 255. So if I were to make this 254, it works. If I were to make this 255, it works. If I were to make this 256, it looks like success, even though we returned a number. Be very careful. You can return a number larger than 255, but it will get chopped off. You basically like have an overflow here. So like, this is not good. You'll get lost. So if you're writing code where you think, oh, I'll increment an error counter and just return the error counter as my code, that way the person will know how many errors there are. Well, be careful if their error code is divisible by 256, because then it will look like a success. So be careful with that. Let's just go ahead and let's be good, and let's make this return 0. So there we go. There's our mini program. It outputs YSAP and has code equals 0. Now, I've mentioned this before, but the standard output of the program is what gets captured by this notation. So we could change this. We could say echo, this goes to standard out, and that is what will go to standard out. So if we run this, we can see that this goes to standard out and code equals 0. Hey, that makes perfect sense. This is the same as this, which is very confusing. We're going to redirect this to the file descriptor 1. 1 is standard out. This is what's assumed. It's just going to inherit it from my terminal. So this is exactly the same. But I show this notation to show that if I duplicate it, I can change this to standard error, make this 2. And what do you think is going to happen when I run this code? So we have this goes to standard out and this goes to standard error. Let's run this and let's see what happens. So this goes to standard error prints first. That's because this function is running first before the output is captured and stored in output. So this goes to standard error, which means it goes directly to my terminal. I can write to my terminal even before the function is done, but this is what got captured and what got stored in the variable. So this is important to note, because if you're running a program that just chooses to output to standard error or standard output sometimes, you actually have control over this. Like you, the programmer down here where I'm highlighting, you can control that, because I could say, hey, you know what? I actually want to redirect everything to dev null. You would never really write code like this because this notation means you want to capture the output. Why would you throw the output out? But if I run this, you can see that we still get the error, but the output is empty because we threw the output away. You could put 1 greater than dev null. It's exactly the same. This is just very explicitly stating it, but you can do that. Now we could say 2 greater than dev null. We're going to throw out standard error, but we're still going to let standard out go through. So here, I'll show you that code real quick. And if we run it, you can see that this goes to standard out, but there was no standard error message because we threw it away when we ran the script, which is super nice. It's super convenient to be able to do this. There is another thing we can do. We can redirect standard error to standard out. So this is really cool. So now both will go to the same thing and we will get this wild output. Output is this goes to standard out, this goes to standard error, and the code is 0. And it's in the exact same order because they both go to the same place. The file descriptor has basically been duplicated over. So this is a really cool trick. There are some other things you can do here. Like we could redirect standard out to dev null, and then we could say, I want standard error to go where standard out goes. So this is gonna be a little bit confusing, but I will show you what I mean. We're redirecting standard out to dev null, but we're redirecting standard error to standard out. So what happens when we run this? We get nothing. That's because when this line ran, it already had changed standard out to dev null. So this means 2 is also being redirected to standard error because it goes from left to right. If we reverse these lines, things get a little bit gnarly. So let's put that line here at the beginning and let's get rid of it at the end. So now I've effectively reversed these lines. So now we're saying I want 2 to go where standard out is, which is just my normal terminal, which is just going to be captured by this. But I also want standard out to go to dev null. So in this case, we're going to get the opposite that you would expect. We get this goes to standard error. This is a way to capture just standard error and throw standard out. So you can do all sorts of finagling, all sorts of messing with things just by knowing this when it comes to return codes, capturing standard out, basic IO, all that stuff. So yeah. All right, so let's take some inventory here. Let's stop and talk about what we have so far. So as you can see, I'm currently logged into my Linux system, and you can see that I'm in a bash folder I just created for this, and I have 2 scripts in here. So we're gonna go through these and we're gonna talk about what they do and kind of understand them. So the first one is called simple. And as you can see, we wanna get the shell of the username Dave. So it's a little bit gross. I'm gonna explain why it's gross, but we're gonna cat etc password, we're gonna pipe grep for Dave, and we're gonna cut based on the colon and get field 7, right? So let's go ahead and do that. If we run 00 simple, hey, there we go. That's awesome. If we look at the next script, hopefully that first script made sense because we're gonna look at the next script and I'm gonna spend some time explaining this. Okay, so let's talk about this and we're gonna go through it line by line and explain what's happening here. So the first thing we do is we make an associative array called shells, a brand new variable called shells. Now we loop over every single line of etc password. So we're looping over it, and look at this notation. We can set the IFS just for the duration of this read command, and we can do it in a loop. So we're setting the IFS for this read command to be colon. We're telling read, hey, break these based on colons, giving -r like we always do. We don't want to mangle backslashes. And then we can name every variable we give the command. So the read command has a variable name, pass, UID, GID, all this stuff. So now we can loop over it and we can just do work. We can just say like echo found user name. And then we could, let's say, continue here. What continue does is bring it right back to the beginning of the loop. This is no different than continue in other languages. So this code down here is not going to run. I'm not going to talk about that code yet. Let's go ahead and just run this script right now. Found user root, found user nobody, found all this stuff, and Dave has shell blank because it still ran the bottom even though nothing happened yet. As a reminder, here's what the etc password file looks like. So that's cool. We were able to extract this out because the read command can break things based on these characters. We don't need cut, we don't need sed, we don't need awk. We can just do it with bash built-ins. So let's go ahead and do this. I do have a line here to skip comments. There were no comments in my etc password file, which is nice, but some do. Some are allowed to have comments, so this skips them. The way we skip them is checking, does name start with a £sign? So notice that it's quoted, otherwise bash would think that you're commenting this out. So we quote that £sign, that octothorpe, that hash mark, whatever you want to call it. And then we put a star here, meaning it has to start with that, but could literally be anything. If it matches that, then we continue, meaning we're just going to skip over comments. Then we store every shell we see for every user. So we do a key value. The key is the name of the user and the value is their shell. So now we want to see what shell Dave has. We can just do shells Dave. There you go. That's easy. So if we run this, we can see that Dave has the shell bin bash. The nice thing about it is we got everyone's shell here. So we could do declare -p shells. And if we run this, we can see, oh, look, there's every single person's shell. It's not the prettiest output, but there we go. That's everybody's shell. Dude, it's like a windstorm outside. It is nuts. I am afraid to go outside when this is all done and see what's broken. Now, it must be said, you can use bash to get all this information, but you don't need to use bash. If you were going to look up some user shell, I guess ask yourself why you would need that information to begin with. Not in a judging way, just like, why do you need that information? What are you trying to accomplish here? And if you really do need someone's shell, you might want to reach for a tool that can better do this. I think there is the finger command, and you can give it a username, and it will tell you information about them. Or it's not as portable as I thought it was. I thought it'd be on Linux. Is it not? Okay, I'm genuinely surprised by that. I'm going to back out of here. I'm on my Mac now. Finger Dave. There we go. This is what I was expecting. Name, Dave Eddy, shell, this. Tells you a bunch of information about this user. So yeah, I guess this command is not as portable as I thought it was. But yeah, this is what we have so far, and this is how you can use bash built-ins to get that information. So this syntax, I really like this syntax. The while IFS equals :read, because you can name the arguments, you can do all sorts of stuff. You could also optionally put this into an array if you want to. Like, I like naming them, but you could do array, and then everything will be put into an array for you. So array spot 0 would be the name, array spot 1 would be pass, array spot 2 would be UID. Otherwise, we can just name them here. I think this is easier. But yeah, this is a really cool syntax. Definitely something you want to commit to memory. Super useful to have under your belt. Here's a big one, and here's a fun one, okay? I'm excited for this one. We are going to cover parameter expansion. This is one of the most powerful features that I think Bash has. Don't get me wrong, pipelines are incredibly powerful, obviously. I'm not saying this is the most powerful, but this is incredibly powerful. This is one of my favorite things about Bash. This is why we don't need a lot of those external tools. We can do a lot of this with Bash built-ins. I'm going to go over a lot here. There's even more that I'm not going to cover. I'm going to link references for this. The actual bash manual will go over all of the possibilities you can do here, but I'm going to show you a lot of them and a lot of the very useful ones and just get you comfortable with the syntax for it. So let's get started. Let's make a variable here. We're going to do a lot of this interactively. Make a variable, Dave Eddy. Hey, there's my name. Simple, right? If we echo $s, we get my name. Let's be good. Let's put quotes around it. Let's actually put quotes around it. There we go. Cool. So that's very simple. What can we do? Well, we can put these curly braces around it, and we can get ready to start doing some stuff to it, okay? This hasn't changed anything. We've just put the curlies around it. We could put the pound sign in front of it, and now we get the length of the string. Dave plus Eddy plus the white space, 9 characters. So what are some other things we can do? Get ready for this. Let's put a single caret here, or the up arrow, or whatever you want to call it, the thing that's on Shift 6 if you're on a QWERTY keyboard. So what happens when we do this? Look at that. We've capitalized the first letter of the string. So that is pretty cool. Let's go ahead and do a double caret. What do you think is going to happen? We've capitalized the entire string. So capitalization, lowercase, to upper, all that stuff, it's built into Bash. You have it right here. I want to say this was introduced in Bash version 4, so you may want to check to make sure your version of Bash can support it. But yeah, I think it's been around for a while. There are some other things we can do here. We can add letters here. So I could put a D here. And as you can see, we just capitalized the D's. So every time a D showed up in the string, we capitalize it. Of course, we have the double caret there. If we only had a single caret, that means capitalize the first D that we see at the beginning, so like that. So if we have our double caret, the nice thing is here, we could do D and A, right? We want to capitalize the D and we want to capitalize the A. Doesn't really work that way. We need to specify a pattern. So let's make this a pattern. This is a Bash specific syntax, but now we match a D character and we match the A character, capitalizing both of them, which is pretty cool. Now there is another thing we can do. Instead of the carets, what if we do commas? So instead of being at the top, they're at the bottom now. Well, that looks the same, doesn't it? Let's go ahead and change our string a little bit. Let's do all caps, Dave Eddy. Let's go to the top. There we go. Now let's rerun this. Lowercase, comma, comma is 2 lower. If we do 1 comma, it's just 2 lower on the first character. It's all very the same to what I've showed you. You could put a capital D here, and then we lowercase every instance of the capital D. We could do the capital DA, it fails. We could put that in the pattern notation, and it works. Now we're lowercasing the D's and the A's. So yeah, comma is 2 lower, caret is 2 upper, super useful. All right, we're gonna jump around a little bit, but let's go ahead and make a little script for this example. We'll call this, not in the directory I thought I was. Let's go into my foo directory. If you run cd on its own and hit enter, it'll bring you to your home directory. Just a nice little shortcut for you. Now we're gonna go into foo, and we are in this directory that we are used to being in. So let's go ahead and make parameter expansion. There we go. So let's go ahead and let's do name equals $1. Let's echo hello name, and then let's echo done. Okay, very simple. We've written code like this 1,000 times. So what is going to happen? Well, no trickery. It's going to work exactly how I expect it to work. It's going to say hello to whatever argument we give it. We didn't give it an argument. We could get Dave, and it says hello Dave. Cool. Yeah, that makes sense. Perfect sense, right? So what can we do here? Well, we can do some sort of things. We can set default values here, which is pretty cool. So we can do this curly brace. We put the curly braces around it as you're used to. We could do colon hyphen, and we could say Steve. Colon hyphen means if this is not set or it's set to an empty string, we're going to change it for Steve. So what that means is if we run our script, it'll say Dave. If we run it with nothing, it says Steve. So that's a way of setting sort of a default value using Bash like this. Also, we can do variable expansion here. So we could do this. We could say set it to whatever the user gives us, or take their username from the all caps $user variable. So if we don't give it any sort of name, it'll print Dave, because that's my name. If we put John here, then it says hello John. So you can set variables as default values. Another cool thing we can do is you could get rid of all this and just put a question mark here. And this is super useful, because what this means is the argument is required now. So if I run this script without an argument, you can see, parameter not set. It just broke there. Not the best error message, but it broke there. If I give it an empty string, it works because it was set. But if I just run it like this, it says parameter not set. So if you want a better message, you could do something like this. You must supply a name. Yes, this looks super weird, but it works. So now it says, oh, here's the error here. You must supply a name. So that's pretty cool. Like I said, it takes an empty string that is a valid name. If you didn't want it to, you would have to use this alternative syntax where, what is it, a colon, I think? Yeah, I think it's colon question mark, just like it was colon hyphen before. This is going to be the same thing, but it will actually break if you give it an empty string. So if you give it nothing or an empty string, it'll treat them the same. But if you say Steve, it'll say hello, Steve. So yeah, two things to keep in mind. Super convenient. If you're just prototyping a script, if I'm prototyping a script, I'll sometimes just do this because it's a real quick and easy way of saying, hey, they better give me something here. You better supply something, you know? All right, the next thing I want to talk about is replacements. So let's say we have a variable called path. We're just going to make up a random path here. Home, Dave, foo.txt. This file doesn't exist. It's just a string. So if we echo $path, you can see we get that. Hey, that makes sense. Of course, we could do things. We could pipe it to tr, and we could change a for o, and we get dove, obviously. We can also do this in bash. So we can just do our curly brace notation, as we're used to, and then we can change all of the a's for o's. And the way we can do that is by /a/o. So after the first slash is the thing you want to find. After the next slash is the thing you want to replace it with. And there you go. Now Dave has become Dove. Now here's the thing. What if we wanted to go backwards? What if we wanted O to become A? So we would have, Haim and Dave and Faye.txt. I don't know, it's weird. Notice that we have Haim here, but we still have foo. That's because it only does this expansion or this substitution once. You need a double slash here. Once you have the double slash, then it will do it for every time it finds it. So you can see this became Haim, this became FAA. So that's how you do find and replace multiple times with the bash built-in parameter expansions. I want to show you these two commands. We can do dir name on path, which will just give us the home Dave component. Actually, let me just echo path so you can see what we have. So here's what we have. If we run dir name on it, it gives us the directory name where the file is. And if we run base name on it, we can see that we get the foo.txt portion. This is super useful, but these are not built into your shell. They're external commands. They're pretty much going to be there. You can probably rely on them, but we can do this with bash built-ins. The syntax is going to be a little bit weird. I know some people don't prefer this, but let me show you. If we echo the path with the curly braces, there's no change there, right? Now, what we can do is we can say from the beginning of the line, that's what the pound sign here is for, from the beginning of the line, match anything up until a slash and delete it. This will remove anything from the beginning of the line all the way up into a slash. So if we run this, we deleted the first slash and that was it. Okay, well, it's kind of not really what we wanted, right? We wanted it to do it greedily. We wanted to match all the way up until the last slash. We want it to be greedy in its left to right search. So we do double pound sign. If we do this notation, looks gnarly, we get the base name of the file. So that's pretty cool. Pound sign is a way to start from the left and delete going to the right. The opposite of that, percent sign. Percent sign starts from the right and goes to the left. Double percent sign makes it greedy, but a single percent sign starts from the right, goes to the left. So now we want to match /*. So what that means is we have the file name right here. We're going to start from the right and we're going to match anything up until the first slash. So we match this, there we go, and we delete this. So we should be left with the dir name. So these are some really cool ways of just changing things with bash. You can do all sorts of changes. So pound sign, delete from the left, percent, delete from the right, slash, find and replace. So the find and replace, like, we could find all the A's and replace them with O, and we get this. You can also do patterns here. So I could find an F. I could do it like that. And now we replaced all the A's and all the F's with O's. We could replace them with, like the number 5, which might make it easier to see. We could replace DV. You just put as much as you want in there. So that's pretty neat. You can also change this to an ampersand. And now it looks like nothing's changed. Ampersand actually is the thing that matched, kind of similar to like set if you've ever seen that. So I'll put an underscore here and underscore here. This is just for visualization. But you can see that we've replaced the D with underscore underscore D underscore 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 A underscore underscore. So this is cool. This is like a back reference to it effectively. I think it's a shell option that is turned on by default in newer versions of bash. So this can trip people up. If you want a literal ampersand, you have to escape it or quote it. When you escape it, then we get literal ampersands here. So yeah, definitely something to keep in mind, something to be aware of. Now, another thing we can do here, let's go back and let's make our nice little string, Dave Eddy, cool. And now we can echo S, that's just our string, nothing going on there, :0. Okay, Okay, that just looks like our string. :1, :2. See what's happening here? We're making substrings. We can make substrings with bash, and colon is the starting position. So what comes after the first colon is the character in we want to start. So we want a substring starting at the 4th character. We want a substring starting at the 5th character. It goes until the end. We can specify 0, that's a full string. We can also give it another number here, and we can say, I only want 2 characters from it. I only want 4 characters from it. I want to start a character 2, but I want 4 characters. I want to start a character 1, but I want 4 characters. See what's happening here? So you can substring strings with bash, which is super nice. And one of the cool things about it is we're substringing at 1. We can also substring it at -1. So what do you think is going to happen here? It's a little confusing, right? What's going on? It just says Dave Eddy. Be careful with this, because this :- operator is actually taking precedence here, and it's saying, oh, if s is not set, then become the literal string 1. That's not what we want. We want it to treat it like a number, so put a space here. Put a space here, and now we can substring s backwards. So we have that. We can go backwards. We can go backwards 2. We can go backwards 3. So you can substring from right to left effectively, which is super nice. A really cool thing that you can do. You can also, of course, do something like, I want to start at the 1st character, and I want to go all the way until the 2nd to last character. Totally valid. You just chop off the 1st character and the last character. I don't know why you'd want to do this, but you absolutely can do this. And I'll teach you a cool little thing. If you want to loop over a string character by character, we have all the constructs we need to do that. So let's do car by car. We're going to make a new script here where we will loop over a string character by character. chmod +x car by car. And then we can do s equals Dave Eddy. We can get the length of the string, which is the # and then s, and then we can do our C style for loops. I = 0, I less than len, I ++, there we go. And now we just need to get the character out of the string. And the way we can do that is we can substring s. What are we substring it on? We start at character I, and we only want 1 character. So we are substringing this, starting at I, just extracting 1 from it, and then we have the character. So we can say $C here. So with this, we are able to, I'll show the source code. We can loop over a string character by character. You may want to do this. Maybe you want to load it into an array or something. Here is the knowledge to be able to do that. You can just substring it like this. Substrings, parameter expansion, all that stuff in bash, super powerful. I have scratched the surface with things you can do. There is also like parameter transformation and stuff. It can get pretty crazy here, where if I have like $S, I can also do this and put an @ here and put like a capital A. The @ is way different, and this gives it to you in a shell safe way that can be parsed. I can paste this back into my shell and run it. I can look at the attributes of a thing. I think Q is to quote it. I'm making a lot of these up off the top of my head. I knew them at one point. I think U is for uppercase and stuff like that. You can also just use this notation. That's called parameter transformation, very similar to parameter expansion. But if you want to look it up on your own time, go take a look into that. Parameter transformation, really cool. A lot of cool ways you can mess with data in bash. And I think the next thing I want to talk about is this syntax, very similar. You will see this with arrays. So if we make an array here, foo bar baz, we have a brand new array here. We can list the elements of the array. I don't remember if I've showed this syntax or not. This is amazing syntax. I love this so much. This is from the WooLedge wiki. Thank you so much. I have used this for the last 15 years. It has been so helpful in my journey of learning bash and using it on a day-to-day basis. Printf. I have a whole section dedicated on printf, so I'm only going to show you a portion of it now, but we can give it the format specifier here, %s, and a new line, and then we can just give it arguments here. This is the cool thing about printf and bash, is it will repeat the format specifier for the arguments. So if I say, hello, how are you? We get them all on separate lines because of that new line character here. So really, really cool. The reason this is really cool is because I can put the array here. Remember to use the @ to open an array and expand it and iterate over it. Foo, bar, and baz. That is super cool. That's awesome. I can also substring into the array. It's not really a substring. You're kind of like taking a slice of it, but you're basically, I can start the array at spot 1. I can start the array at spot 2. I can start the array at spot 0, but grab the first 2 elements out of it. This syntax is totally valid. On top of that, guess what else is totally valid? Find and replace. I want every element of it, but I want all the A's replaced with O's. Foo, bor, and bas. It works. This totally works. I want this same thing, but I want any sort of Z removed from the end of the string. Foo, bar, and ba. I want this, but I want B removed from the beginning of the string. Foo, are, and as. So this is really cool. It's really powerful notation. You can do a lot of cool things with this. It's not all the same notation, but for the most part, a lot of the things translate over to arrays, kind of how you'd expect them to work, which is really neat. So yeah, really powerful syntax, really cool things you can do without having to like loop over manually one by one. Just with syntax like this, we can make transformations to our arrays, which is just incredibly powerful. And of course, don't get tricked by this. Some people will get confused and they'll want to omit the quotes or they'll want to use the star. Both those things are wrong. Yes, in this example, they both work, but they both work because there's no weird white space in the elements. When you want to loop an array, you always want to quote it and you want to have the @ sign. When you want to stringify the elements of an array, you want to have your IFS set to whatever you want to separate them, and then you want to echo the array with the star notation. I forgot that, didn't I? There we go. So now this is how you join them. So when you want to stringify an array, you want the star. When you want to loop over them, when you want to iterate them, you want the @ sign, and you need the quotes. You also need the quotes for the star. This might be a little bit confusing for people. You do need the quotes there because that does change how it works. Super weird, throws people off, but it's just a good rule. Quote your expansions. Just every time you expand a variable, put quotes around it, you're going to be fine. The only time you see me not really putting quotes around thing is during variable assignment. So like, I could have Dave here. I'll also just do Dave. This is totally fine. You don't need to quote this. So if you had something like, I don't know, var, and var had a bunch of gnarly stuff in it, the assignment works just fine. That's like the only time I really don't quote my expansions. But other than that, quote your expansions and you'll be good. All right, so let's talk about basic globbing now. This is wildcards on your shell. This is super useful. I love this feature. Let's clean up a little bit here. Let's move some of these files, char by char, curly, parameter, say anything, return codes. Let's move them all to done. And now we have a nice clean directory with done and lib. Let's make a new directory here called files. This is going to have random files. They're not going to be real files. We're just going to make them to illustrate a simple concept here. So we're going to go into files and let's make some fake files. Bar.txt. I don't know why I started with bar. Foo.txt, foo.jpg, and touch bar.jpg. We should probably also make baz since we're here. There we go. Little confusing. Let's back out of this. Let's ls files, and we can see we have foo bar baz as text and JPEG files. They're just empty files. I'm just using those names so we can illustrate some concepts here. Let's go ahead and ls them. We can ls files. We can also, if you want to see them on their own line, ls-1. I like this option. This separates the files based on new lines. Super useful. Yes, file names can have new lines in them, so be careful about that, but still very useful here. We can also echo files star. That's a glob. That is called globbing. This will get replaced with this, and echo will receive this. So this command, actually, bash ran that. That is what it ran. Very confusing, but it ran that on my behalf. It got a lot of arguments there. So we can use that printf notation. We're going to use this a lot. I really like this notation. We can do the %s, new line here. We can do file star, and then we get new line separated based on the glob. So again, this got expanded into multiple arguments, and printf will repeat the format specifier for each argument it got. Super useful, really nice to be aware of. So go back up here, ls-1, files. We have this. We can do files star. ls got every single file as an argument. That's why ls now puts files in front of it. So just a little thing to be aware of, but this is going to turn into every file that's there. We can also do star.txt if we just want to list the text files. Star.jpg if we just want to list the JPEG files, which is super nice. We can do the opposite. We can say foo.star if we just want to list the foo files. Foo Files, my favorite band. So dumb. I gotta cut out so many corny jokes. Nah, I'm gonna leave them in. You guys have to suffer. Bar star. So there's all our bar files. Now, of course, there are some other things we can do here. There's a couple little things. I'm just gonna show a little bit of it, but we can do BA question mark. Question mark.txt. Star matches anything pretty much, 0 or anything. Question mark means it has to be something, but it can be anything, but it has to be something. So it'll match bar and baz. So it was just any character there. You'll notice if you're familiar with regex or regular expressions, it's very similar. It's not exactly the same, but it is very similar. So that can be kind of useful to be aware of. Also, a lot like regex, we can specify patterns here. We can say, I want to match anything that has an A, a B, or a C here. Now that doesn't actually match anything, so we get an error, but I want to match something that has an A, B, C, or an R. Now it does match something. Bar has an R in it. We could put a Z here, and now it matches bar and baz. So we are free to put patterns there, and you can mix and match. We could do this, and now we match everything that's BA, any of those characters one time, literal period, and then a star means anything at the end of it. This is a basic introduction to globbing. It's incredibly powerful. It's such a useful tool, but it can get more complicated, and that's what extended globbing is for. All right, so let's talk about extended globbing. This is really cool. This is a feature you can turn on your shell. It may or may not be on by default. It's on most of my shells, so I'm just used to it. It is a shell option, so I have to teach you the shell option built in. Shopt. Shopt is short for shell option. It's built into your bash, so you can run help on it, and you can get all information about it. So if you run shopt on its own, here are a list of all the shell options, and you can check if they're off or on. So the thing we want is extglob, extglob, or extended globbing. So you can give it as an argument, and then it will tell you extglob is on. That's super cool. If your machine was off, you can turn it on with -s, and then you can check to see that it's on like that. If you wanted to turn it off, you can run -u. Now, if you're like, Dave, that's really confusing. Why is it -s for on and -u for off? -s for set, -u for unset. That's the way to remember it. -s will set it, -u is unset. So that's how it is. If you get confused, pull up the help page. -s enable, set each option. -u disable, unset each option. That's why it's that way. So let's show some examples. First things first. Have you ever gotten that error message on bash where it yells at you, where it shows an exclamation mark and says event not found, and you're like, I have no idea what that is? That is going to be history expansion, and that has bitten me a couple times, especially when I'm dealing with extended globbing. So I'm just going to turn it off for now. If you're running into issues that you don't know what's going on, you just keep seeing event not found, you have no idea what that means, set -h. That turns off history expansion. We can turn it back on later with set +h. But set -h, if you do have any problems with any of the exclamation marks that I'm going to show in these examples, set -h will make those go away. So now we turn on xglob, which I believe is already on, but it doesn't hurt to just run it again. Now we can do some really fun things. So let's talk about what we had before. We can check star.txt. That's awesome. What if we wanted everything that's not a text file? Well, we can negate this. We can put parentheses around star.txt, and it's an error, but if we put the exclamation mark in front of it, now we've negated that glob. This is extended globbing. This is extra things that are on top of globbing. We can get everything that's not a text file, which is cool. In this example, it's just JPEG files, but you can see that it works like this. On top of that, we could do some really cool strict pattern matching. So we could do +foo::bar.text. This will match foo.txt or bar.text, which is super cool, really nice. The plus sign means it has to match it one or many times. Very similar to regex. I will give you a little bit of a guide to kind of explain this. I'll just open up a blank Vim window just so I can type for you. In extended globbing, you're going to see syntax like this, where it's plus thing, it's going to be question mark thing, and it's going to be star thing. These are roughly the equivalents in regex to thing plus, like that. Or let's do a question mark and star here. They're roughly the equivalent. So plus thing means one or many times, question mark means 0 or 1 times, and star means 0 or many times. I'm pretty sure that what's that mean? It's been a while since I've done regex, but I'm pretty sure that's what that is. But these are basically analogs to each other. So this notation might look kind of weird, but think of it similar to regex, and that'll kind of get you, and that'll kind of work for you. So there is another one though, because we have, plus foo bar. You could put a question mark here. There is another one to be aware of, which doesn't have an analog to regex, which is the @ sign thing. So this is going to be weird. I'll show you an example of it. Let's do +foo.star, and we can see that we have foo.jpg and we have foo.text. That makes perfect sense. What if we put an @ sign here? We have foo.jpg and we have foo.text. So hold on, what's going on here, Dave? These are just exactly the same. Let's make a new file. You ready for this? Touch files, foo-foo. foo.txt. See where I'm going with this? Now we have foo.txt. Let's go ahead and list all the files there. We have foo and we have foo.txt. So what's going on here? Let's go ahead and list it with the @ sign. The @ sign must match exactly that and nothing but that. Whereas if we were to use the plus sign, we can see that it matches foo as well. So the @ sign is just for a stricter, tighter match on things. I haven't found myself using it that much, but it's cool to know that it's there. There's probably more intricacies about it that I don't actually know. I'm not super well versed in it. Even when I was reading the documentation, I was like a little bit confused on exactly what it does. I came up with this example, but yeah, I'm not super confident about this one, so I may get a couple things wrong. I would invite you to go look it up if you're interested in this very specific syntax. So yeah, let's have some more fun. Touch files bar.txt. Okay, cool. Now we can ls files @ sign foobar, so we can put patterns in here exactly the same .star, and we can see that it only matched bar and it only matched foo. It didn't match foo and it didn't match bar. These names are wild. Of course, we can also do patterns inside here. So a question mark is totally invalid. We want to match foo or we want to match ba anything. And there we go. Now we match baz and we match bar. So you can mix and match a bunch of these styles. It gets kind of gnarly, but it's still like a really, really cool feature. I think it's really awesome. All right, and finally in the realm of globbing, we have glob options. So I showed you shopped and we have extended glob. There are more options for glob, and there's probably more than I'll even be able to go over because there's a lot here, but there are some that I want to talk about that I think are really, really cool. So let's go ahead, let's look at what we have here. Let's make a new dir called empty. We have an empty directory. I can prove that. I can ls empty and I can ls empty star, and we get an error message. It's very important. We get an error message. So ls got this literal string. It didn't expand anything because there were no files there. So the bash glob, the wildcard, couldn't expand. There's nothing there. So I can prove this. We can do the printf notation. I'm going to do this. I'm putting less than and greater than around it just for a stylistic choice. So if I run like hello, how are you? You can easily see which one is the actual argument to it just because it has less than and greater than around. It's just for style. So if we were to run empty star here, we can see that printf did get one argument and it was star. It had a literal star there. That's not that great. So what happens if we touch a file in empty? Let's go ahead and make a file called foo, rerun that. Now we have empty/foo. Hey, look, it expanded to something. That's great. If we delete that foo file, we're back where we were before. We get what is almost like an error message. We get a string here, but it just has a literal star in it because it failed to glob. There's an option that is super useful for this called the null glob. When you turn this on, now when I rerun this, we get nothing in there. It didn't match anything in there. Okay, my terminal just tried to do a little upgrade on me. Sorry about that. So we're back here. We have null glob turned on. We're going to rewrite this %s like that, and we're going to glob over what is an empty. If you remember, empty is empty. There should be nothing there. We run it, and we get nothing. We still print something. That's just because that's how printf works. If I were to delete this completely and just have nothing there, it prints this. So this is our way of saying there's nothing there. There's no arguments. There was nothing given to printf. It is effectively empty. That's the beautiful thing about null glob. It won't turn into a literal string. It will just become actually nothing. We could store this in an array. We could make a new array, and the array could be a glob. Now, if we echo how many items are in the array, we get 0. There's no matches. If we were to turn off null glob, remember, unset it, and then rerun this command, remake the array, and then reprint out how many items are in it, there's 1 item in it. And if we print the array, the first item, we can just do it like this. You can see it's a literal star. So yeah, null glob is super great when you set it because it will actually resolve to nothing, which is great and ideal for a lot of situations. Now there is something to be cognizant about this, is that because it will turn into nothing, if I do this, notice how empty was empty. If I run this, it lists my current directory. Be mindful of this because this turned into nothing. That means ls ran with no arguments. So ls listed the current directory and not the empty directory. So null glob is great, but only turn it on when you need it because it can kind of give you some weird situations. I would have much rather ls give me an error message here. So if I had turned off null glob, if I had unset it, then if I rerun this, I get an error message, and that's way easier for me to understand. Like, oh yeah, I'm trying to list something that's not there. So that's null glob, but there is more to the story. So let's go ahead and talk about another option, and to showcase that one, we're gonna make a new file. Let's touch something in empty, but this time we're gonna touch a hidden file. Okay, so we have a hidden file in empty. We can ls-a empty, and we can see that there's a hidden file there. Cool, yeah, that makes sense. If we echo empty star, there's nothing there. As you can see, we just get that star. It failed to expand. But we can turn on .glob. .glob does exactly what you think it does. It allows you to glob also .file. So anything that starts with a dot, a hidden file, it will get glob. So this is super useful because you can do all the same stuff. I could say array equals empty, and then I could echo, let's see if I get this right. There we go. I can echo that, and we can see that there is one item in that array. If we were to just print the entire array, we can see that there is a hidden file in there. That's what we would expect. That's what we'd want to see happen, which is nice. I could ls empty star, and it will just ls the hidden file because the glob expanded, the wildcard expanded even before ls ran. So super useful. If you don't turn this on, because it can be surprising to have it on or not, if you have it off, you can still get this behavior by doing this, empty dot star. Because remember, to put things next to each other in an array, you just put a space between them. So if we glob star and dot star, then we go to print what's in that array, you can see that we have the star one failed, but the hidden file one worked. So you want to pair these together. We want to set null glob, but we want to unset dot glob. A little confusing, I know. Apologize, it is confusing. But yeah, so you want to have null glob enabled and dot glob off if you want to use this notation. Be careful with this notation, because if you have dot glob enabled and you do this, think about it. This is going to glob all the dot files as well, and this is also going to glob the dot files. So what does that mean? We're going to get duplicates. So be careful. You have to make sure you're using these options in a way that makes sense. I like to just turn them on for whatever work I'm doing, and then kind of just basically set them as I need them in a script. Or the best thing, of course, do them in a subshell. Wrap parentheses around it, modify it, and then I don't have to worry because they're done by the time my function or whatever is done running. And there is one more thing I want to show. This is a really cool thing. So let me do that printf real quick, and let's just list files that we have. New line, and we can do star here. So there we go, there's our files. We have .glob enabled, so we're seeing that hidden .ds store file. That's fine, I don't have a problem with that. All right, so let's go ahead and show something really cool. Remember the find command? If you run find dot, it lists every file that it sees. We can do this in bash. Now, if you notice bash, when I just give it star, it only lists the directory. It doesn't recurse into the directories. I can make it recurse. You can turn on an option called glob star, and this will make it recurse. This syntax won't recurse. You need to use a special syntax, which is star star. When you use star star, this will start recursing now. So when I do this, I will get the same output as find. It might be slightly out of order, maybe like slightly different, but it will have all the same files. So bash can recursively find files in glob based on that, which is pretty cool. And you can do some really cool things with it, because I could do something like this. I could do text equals, make a new array, and I could do something like, hey, find anything that is a text file. So now, if I print the items in that array, let me remember the syntax, there we go. There are 6 text files that were found. If I print them out, here were all the text files that were found from that glob. So you can recursively find files just using bash built-ins. You don't even need find. So yeah, it's pretty cool. We could verify this. We could do find type f dash name star.text. And there we go. If we pipe that to word count -l, we can see there are 6. So we found 6 there, the exact same way we found 6 here. So globstar built into your shell, super awesome, super useful. Love it. I think it's great. All right, so now we're going to talk about brace expansion. We can use braces to expand strings and stuff like that. It's slightly different than globbing. I will show you some of the differences as we go along. Let me just show you some quick examples here. So what exactly do I mean by brace expansion? Well, I talked about it a little bit earlier, but I didn't go too deep into it. But we can do some cool things. We can use curly braces, and we can say something like hello, comma, world. And then we close this curly brace, we hit enter, we get hello, and we get world. this got broken up into 2 separate arguments that were given to echo, so we can expand things like this. We could put multiple things in here, foo, bar, baz, and now we have multiple arguments here. I can prove they're multiple arguments. We can use a nice little printf. We can do that notation of %s new line here, and then we can see it separates them all by new lines, which is pretty cool. If you quote them, it gets the literal string. So if you want literal curly braces, quote them. But without the quotes, you get that nice little expansion, and it is super useful. And this is really cool because you can do things like getting file names. So here, let me make a little script here. We'll call this curly brace expansion. And we'll go ahead and do what we always do. There we go. Now we have a nice little script, chmod +x, curly brace expansion. Run that, and now we can do something simple like this. We could do file name equals my file, and then we can echo file name dot, and then we can do multiple extensions here. We could say text, JPEG, MOV, but remember what I said about the quotes? We have to close the quotes here. So you could close it here like this if you wanted to. You could close it here. As long as this is outside of the quotes, you will be fine. So let's go ahead and run this. Let's run curly brace expansion. And as you can see, we get myfile.txt, myfile.jpg, and myfile.mov. Here's what the source code looks like for that. So yeah, as long as you don't put that in the quotes, you'll be fine. You'll get the expansion you want. Here's the cool thing. To bash, these are just strings. These don't actually have to be files on the file system. They don't check to see that they're files on the file system. This is just a string. So that means there's no looking. It's not like globs. Globs need the files to actually be there, the wildcard notation. This is just expanding into strings. So Echo doesn't care if these files exist or don't exist. Echo just prints them out to the screen. That's what's happening there. Now, the cool thing about this is we can modify this slightly. So we have this curly brace expansion here, like this. We could do this. We could say ARR equals this, and we could make an array. Now we have an array, and here, I'll put some spaces here just so you can see it. The spaces are optional, but I'm putting there just so you can illustrate the concept better. Now we could do something like for item in array, loop over the array with this syntax that we've used before, and then echo item, done. So now we have that. I'll go ahead and pull that source code up. You can see what it looks like. You run it, and we can see we have myfile.txt, myfile.jpg, and myfile.mov. So you can store this, the output of the curly brace expansion, in an array, and it will store this properly as separate arguments, which is super nice. So they're separate items in the array. Now this comes in handy when we have like certain file names that we want to loop over. So let me give you a different example here. Say we had a file name on our system. We could do something like Etsy, foo, or bar, and then inside there might be 1, 2, or 3.text. We could store that in an array, and then when we loop over that array, we will see that we get all the combinations of that. So we can use multiple curly brace expansions to get multiple combinations of it, which is pretty neat. It's pretty cool. It's a pretty powerful thing when you start synthesizing multiple curly brace expansions together like this, because again, we're not checking the file system to see if they're there. We are just doing basic string manipulation. So when you look at this, you can see there are 6 items in that array. So that's pretty cool. All right, so now I want to show the power of using globbing and brace expansion together, because this is really cool. So if we look at our directory here, we can see that we have our files directory from a previous lesson, and in here we have a whole bunch of different files. I'm going to go ahead and get rid of the bar file and the foo file. So now we are left with foo. Let me sort this like this. Now it's easier to read. Foo.text, foo.jpg, bar.text, bar.jpg, baz.text, baz.jpg. So that's cool. That makes sense. So now, while we are in that directory, what we can do here is we can delete these files. I'm going to go ahead and delete every file there. Now this directory is completely empty. Why did I delete every file? Because we can recreate them. We can recreate them really easily. Before we recreated them one by one, now we know better. Foo, bar, baz, dot, JPEG, or text. Remember, these files don't have to exist. They will just get expanded by bash as strings. Hit enter, and there we go. There's our 6 files back. That's how easy it is to recreate those files. Now that those files are there again, we can back out here. We can loop over them. Remember how we did this with globs? We did, let's do %s with this less than and greater than around it. We could do file star, and we could loop over every file that's there. Well, we could also do files, foo, bar, baz, and we could do, you know, .text and .jpeg. The difference here, like I said, is it's not looking at the actual file system, so I can just add more things to this. I could add MOV there, and now it totally enumerates MOV files. Those don't exist in the file system. If I were to use a glob, it would fail because they don't exist in the file system. So globbing and wildcards, even though brace expansion seems like it's very similar, brace expansion just deals with string, globbing and wildcards actually looks at the underlying file system. So keep that in mind. Now you can actually combine them, and this is something that's very interesting here because I could do files star, and then I could do .text or JPEG. So now we're only matching .text or JPEG. In fact, I could make this just text or MOV. And now it matches, it looks for star.text and it looks for star.mov. Star.mov doesn't match, so we don't actually list anything, but we expand to star.text because that expansion match. So you can mix and match globs and curly brace expansion. You just have to realize that globs are going to look at the file system. Curly brace expansion is not going to do that. So of course, just to drive that point home, we have this empty directory that has nothing in it. If we were to ls empty star dot text or JPEG, you will see that we get, you will see that we actually just ls our current directory. That's because I think we still have null glob on, shopped null glob. Yeah, it's on. So let's go ahead and turn that off. There we go. And let's rerun this. We should get an error. Notice we get two errors because it tries to enumerate .jpeg and .txt. That fails. But by contrast, we could just do printf here, %s new line, and it works because it will still enumerate them. So yeah, that's braces and globbing together. That's the power of using both of them at the same time. It's pretty cool. So the next thing I have to talk about is we've done a lot of stuff with curly braces. I want to show something else that curly braces can do. I talked about this in a previous lesson, but it's really cool. We can do numeric expansion with curly braces, which is kind of awesome. So we know we can do something, comma, something, and it will break it into the two like this. We can also do 1, ... 2. Now this is specific to numbers. So this actually creates a range from 1 all the way up to 2. Now it looks the same here because 1 just goes up to 2 really simply, but what if 1 went up to 20? There we go. 1 all the way up to 20, inclusively. Notice that it starts at 1, it goes all the way up to and including 20. And we can change some of these things. We could do 5 all the way up to 10 if we wanted to. And now it creates a nice little range like this. We could do it backwards. We could do 10 all the way down to 5, and Bash is smart. It will figure out what direction you're trying to go into. In fact, Bash version 4 and above, I believe, supports this syntax. 1 all the way to 100, skipping by 5s. And there we go. So 1 plus 5 until it goes all the way up to including 100. So that's a pretty cool thing. If you've seen the seq command before, you have the sequence command. You can do very similar things. Sequence up from 1 to 2 or 1 to 10. Sequence 1 to 20. Notice it puts them on new lines, slightly different. You can do sequence 5 and it goes from 1 to 5. It assumes the default argument. It starts at 1. So that's just a slightly little difference with Bash. You have to give it a starting and ending thing in Bash. Now, if you recall from this curly brace example, we could do the beginning, the end, let's do an end of 50 actually, and the step. This is how much to step up by. And we go 1 plus 10 all the way until we get to 50. So that's the order of it. SEQ sequence is a little bit backwards. You can't do 1, 50, 10. You have to do it the other way around. If you give it 3 arguments, it has to be 1, the step, and then where it's going to. So the arguments are a little bit different. Here's the fun thing. You don't need the sequence command, okay? You don't need SEQ. If you're writing Bash scripts, you do not need it. Everything you would need the SEQ command for, you can do it with Bash. So I'll show you that. Let's go ahead and make a new file here. We'll call it Braces Numeric. That's what we'll call it. And we'll do the exact same thing we've always done. User bin env bash. We'll go ahead and save that file. chmod +x. Vim braces. I should get an award for how many times I've typed that. Oh my god. So let's do a basic for loop here, and we're going to show how you might see it. This is what you would see like in maybe like a POSIX shell script or something. You might see this in Bash scripts, but we can rewrite it to be better. But I'll show you what people would normally do. They would do sequence 1 to 10 like this. Do echo $I, done. Now remember my rule I said before, if you're not quoting this, if it works because you're not quoting it, then you're probably doing something wrong. That's what's happening here. This only works because we're not quoting it. I'll show you what it looks like. It's very simple. It just does exactly what you would expect. It counts from 1 all the way up to and including 10. Now we can rewrite this, of course, to be better. Get rid of this fork and exec, get rid of that external program SEQ. We don't need it. We just go 1 all the way up to 10, and the for loop will handle doing the range for us. So the for loop will properly iterate over this. I'll show you the source code, and we'll go ahead and run it. And there you go. It's using built-in commands. We're not forking out to seq. We don't have to worry about that. We don't have to worry about quoting expansion because the expansion breaks properly. When I say break, I mean it gets split up properly by bash. So it's a good thing. I don't mean break in a bad way. So now that we have this, here's the cool thing about bash for loops. I've talked about this before. You can just throw stuff in here. So I could just do like foo bar 1 up until 4 baz. You can just do this, and this is totally valid. If I save that and run it, you can see that it just puts foo there and then counts up to 10 and then prints bar and then counts up to 4 and then prints baz. So yeah, pretty cool thing about for loops and bash. You can kind of just put things together. So that's kind of neat. Also, of course, you could do 1 up to 10 and skip by 2. You could put the skip in there, and that totally works exactly how you'd expect to do 1, 3, 5, 7, 9. That goes all the way up to and including 10, but it doesn't quite reach 10 because no amount of adding 2 to 1 will ever get you to 10. Now, of course, I showed this before, but I'm going to reiterate this. It doesn't hurt to go over it again. If you have like a max variable here and you want to go I all the way up to the max, if you recall earlier in this course, I think I showed this, it doesn't work. It doesn't work. If you do a variable expansion here, it does not break it like it would with curly braces. In order for the curly brace expansion to work, you can't have variables in it like this. So it just does not work. This is where you'll see people using the seq command because they're like, oh, I can just put a variable in it and it works. They're right, it does, but we can just use the C style for loop here. I equals 0, I less than equal to max, I plus plus, do, and there we go. We've rewritten it. There's no external fork and execs. When we run this, hey, it works. I can print it right here. Of course, I set I equal to 0. You could set I equal to 1 and you get the same effect. I think the point stands. And if you want to, of course, skip up by 2, then I plus, what was it? Plus equal 2. You just do that. You can also put spaces here. Doesn't matter if there's spaces or not. This totally works. Let me go ahead and run that. And there we go, 0, 2, 4. So yeah, you have the C style for loops and bash. Don't forget them, they are super useful. Cool, so let's switch gears a little bit. We are gonna talk about printf. I've used it before. If you wanna print something on the screen, we use echo. We can say, hello, how are you? And it prints to the screen and it gives us a new line. That's great, that's fantastic. It makes it really easy to work with. There's also printf. We could say, hello, how are you? We have to quote it. It has to be all one big argument to printf. We print that and it's kind of missing the new line, so we have to manually put a new line character in there. So why would you ever want to use printf over echo? Well, if you've used other programming languages, maybe you've coded in C or something, you know that printf is in C. I can do man3 printf because 3 is going to pull up the library section for the man pages for printf. And you can see that the function is here and there is a lot of stuff it can do. I'm just scrolling down and doing page down right now. There's a lot that printf can do. It is for printing formatted data. So in my mind, echo is when I want to print something very basic to the screen. But when I need to format the data, when I need to massage it, when I need to change its format just ever so slightly, I'm going to reach for printf because printf and bash is really powerful. So let's show some of the stuff it can do and let's show how it can be a little bit dangerous, okay? So here's what we'll do. I'll make a new variable, hello world. So we have this new variable s called hello world. We can echo $s and this prints the variable plus a new line at the end. Makes perfect sense. You could do this. Don't do this. Do not do this. This is wrong. It will work and I'll run it. It's not a huge deal. Now, the reason it's wrong is only because this data could be coming from someone else. In our example, I wrote $s, so I know it's in control of the variable. It's not wrong. But you could imagine a scenario where you're taking that variable from, you're taking that data from a person. You don't want to ever give user specified data as the first argument to printf. That's going to be very dangerous. You want to put a print specifier in there yourself. You want to say, hey, %s, that means just format this like a string. %s new line means format it like a string and put a new line. And then the first argument that I give it will go to the first format specifier. So the % letter is a format specifier. The first argument here goes to the first format specifier. So printf will format whatever's in $s as a string. Hopefully that makes sense. When I run it, I get exactly what we would expect here. Now, the nice thing about this, why you would want this, is because I can say my string is, and then I could put parentheses around this. This is a very nice way of seeing how we're formatting this. So normally you just put like the variable inline here. No, you could specify a format here and then just apply it against the variable that you give it, which is kind of nice. It's a really nice way of seeing this. I like printf for very like specific use cases. Now there are some cool things here too. Let's not use that variable anymore. Let's go ahead and printf %s space %s new line. I can give it 2 arguments now. Hello, world. So there we go. Okay, I just put a space here. I can put multiple spaces here, and then when I print it, we get multiple spaces in the output. Yeah, that makes sense. That makes perfect sense. What are some of the cool things we can do? Well, with %s, we can actually do something very unique. We can give it a number. I can say 5 here and %5s. Now when I print it, it looks exactly the same, kind of boring. So what happened? Let's make this 5 a 10. And let's make this 5 a 10. This is going to really illustrate the point here. Look at that. It printed hello and it printed world. But you notice what happened? There are 10 characters here and there are 10 characters here. Printf padded the argument up to 10 using spaces and right justified it. That's what happened. That's the power of printf. It is really cool. Let's go back to this example where we %5s and just give it A and B. Now we can really see what's going on. We have A over here with 5 spaces, so 4 spaces, and the 5th character would be A, 4 characters, and the 5th one would be B. That's what's going on. It's padding it up to 5. If we want it left justified, you put a hyphen here. This is not specific to Bash. This is printf in most languages. If you're in C, it's identical what I'm doing here. You run this, and now it's suddenly left justified. We have 5 spaces here. We even have 5 spaces here. Even though it doesn't really matter, we just have a new line. There are 4 spaces after this B is what I'm trying to say. So cool. Let me illustrate this concept a little bit more. We can surround this. I could surround this in a less than and greater than sign. These are not special. These are just for aesthetics. So we can kind of see that A and B is justified to the left. If I get rid of the hyphens, it's going to be justified to the right, which is pretty cool. Another thing we can do, which I think is really neat, this is just printf specific as well, is I can put a star here. Now the star is special. The reason the star is special is because now, even though I'm only taking I have one format specifier here, I'm only taking 1 argument. Technically with the star, I'm taking 2 arguments, all right? I take a number and I take a string here, like hello. So now the amount that this gets spaced out is actually given as an argument. So you could take this from the user, you could calculate this on the fly, you could do all sorts of stuff. You could also put a hyphen here and left justify it as well. I could say, let's make it 20 spaces. There you go. Now we've left justified it with 20 spaces. So yeah, it looks a little bit hard to understand, but these format specifiers are incredibly powerful. Bash can also do more than this. This is just printf in general, but instead of %s, I can give it %d. %d means a number. So when I'm formatting a number, it just looks exactly the same. That makes perfect sense. I can also put this in front of it. I can say 5D, and now we've padded it over 5 spaces, which is pretty nice. Of course, we can do the hyphen in front of it, pad it to the left, so there is spaces to the right of it. You just can't see it. Here's the cool thing. We can give it a character here. Instead of saying 5D, I can say 05D. And you know what's going to happen now? We've padded the number with zeros. How awesome is this? This is super convenient to be able to pad the numbers with zeros like this so easily. It is just, it makes it awesome. Cool thing about this is if I give it something that's not a number, we get an error message. How cool is that? And it returns with an error message, meaning we can catch this in our code if we wanted to. If we wanted to code defensively, say we were taking information from a user and we want to check if it was a number, you could run it through printf theoretically. I wouldn't do it. There's some gotchas with it. I'll go over some of the gotchas with it. Now, like before, we've done something similar to this. Let's format a number, and the number we're going to give it would be 06. Do you see where this is going? We've done this before. 07, that works. 08, we get an error message. We get an error message because it's octal and it's too big. It does give us an error return code, so that is very convenient. I do appreciate that. So of course, with the leading 0, we can format octal and it will turn it into the number representation. So you can do like this and it will convert it to whatever that is in octal, which is so nice. The other thing you can do, which is really cool, is hex. I could give it 0A in hex and it prints 10 because that's what 0A is. I can give it FF and it will print 255. So you can use this to format your numbers. Printf, print format. You give it a format specifier. Super nice. Now, if I do help on printf, it'll say that it supports all of these. These are all of the format characters it supports. It doesn't give you documentation for them. If you want them, you have to look up the documentation here. This notation means look in the man pages in section 3 for printf. That's how you understand this sort of syntax that you might see. It supports some other options, though. You can see %b, %q, %big Q, and %t. We're going to talk about some of these. %q and %big Q are very similar, but let's talk about some of these ones that are bash specific. I really like this one. Printf, what was it? %q. Let's talk about that one first. Q, and then a new line. We can do foobar like this. We don't have to quote it, but we can. And it just prints like that. Okay, is that safely quoted? It's supposed to be safely quoted for the shell, right? Quote the argument in a way that can be reused as shell input. Okay, well, foobar isn't that scary to the shell. That's fine. What if we put a potentially scary character in here? Like a $sign is kind of special to the shell, right? Look at that. It quotes it for us. It will safely escape it in a way that we can pass it back into the shell. So %q, very, very cool. It's a nice, cool option that they give you. The other one that was there was %b. And %b is cool because it will interpret backslash hex notation, a couple different backslashes actually. I have to double check on this one. Expand backslash escape sequences in the corresponding argument. This one's really cool. I'm sure you can use it for more than I've used it for, but you can give it raw hex codes and it will just interpret them. So what I mean by that is I could say like FF and it will just print that to the screen. As you can see, it's this nice little question mark. It's an unprintable character. But if I pipe that into some sort of hex viewer, you will see that I actually got FF. So Bash can write binary. I have a video on my YouTube channel where I do BMP, bitmap graphics generation using Bash, and I'm able to do it because printf can write binary to the screen. So it's pretty awesome. I can link to that at the end. But one of the cool things about this is I could print like hello world, and then I could do a %b here, and I could give it 0a. So as you can see, it says hello world, and there's this period here with a 0a character. And do you know what a 0a character is? A new line. That's what it is. So I could put a new line right there if I wanted to. So yeah, kind of cute. It allows you to do like raw binary with it. And before I move on, one last thing I want to talk about with printf, which I really like. So let's say we say hello %s, and then the thing we give it will be Dave. It'll print hello Dave. That's super nice. What we can do is we can give it a -v argument. This is a bash specific thing. Give it the name of a variable, and it will write the string instead of to the screen. It will put the string in a variable for you. That is super nice. It's super convenient. It is a very quick way of saying, hey, format this, but also store it in a variable because I might want to use it later or reformat it or do something with it. So yeah, really cool. Printf, super powerful. All right, so now I want to talk about formatting dates with Bash, because you actually can, and as you saw in the last chapter, we talked about printf, and we have this format. I don't want to spoil it yet. I want to give it its own section. So let's say we want to format a date in Bash. Well, you might have seen the date command. You run the date command, and it tells you the current date. Hey, that's pretty cool. You can run the date command with a +sign, and then you can give it a specifier for the date. This is different than printf specifier. This would be called the stirf time or stirf time. If you do man stirf time, you can find out this. It's all defined here. There are all different characters. So this is replaced by the full weekday, the abbreviated weekday, the full month. This is how you find how to output in this format. So %ymd if you give it a %F. So that's kind of cute. I'm going to, well, actually, let's just make up one right now. Let's come up with our own date format. We're going to make a variable called date format, and we'll use a %m, %d, %y, month, day, year. I'm just kidding. This will upset a lot of people. Let's do it in a way that's agnostic to where you live. %y for the year, %m for the month, and %d for the day. So year, month, day, space, hour, minute, second. There we go. That is our date format. We are saving that as a string so we can reuse it later. There's no trickery going on here. This is just a literal string that has % in it. So now you can do this. You can fork out to the external date command, give it a +sign, and then you can give it this date format. Now there are different versions of the date command, so only certain versions support this. I've seen some weird versions of date or very stripped down versions of date. So this works for us, this works for our use case, but this may not work for everyone. This may not work for every version of date out there. So luckily, we can do this with Bash specifically. So let's look at help printf, and we can see right here, we can do a %t, but inside parentheses, we have to put a format thing. So the format is a format string for stirf time. So what does that mean? We have that format string right here. So we could use the variable, or we could just take this. I'm just going to copy and paste this in just to illustrate this point. Let's printf the date is %t new line. Now we have to put a parenthesis, open and close parenthesis here, and we have to put the stirf time format in there. And there you go. If we run this, we get the current time and date. If I keep running it, you can see it keeps updating as time goes on. So yes, I am recording this just before midnight. Yeah, that's how I roll. Now the cool thing about this is, let's say we wanted to add another string to this, like name equals %s, and I want to pass in a name argument. Well, how do I pass it in? If I put the name Dave here, it's going to try and interpret Dave as the time, and things are going to get messed up. So there are some sentinel values here that you can care about. -1, you give -1 to the date format specifier with printf, and it will use the current time and date. If you give -2 to it, it will use the date the shell was started. So this shell, this terminal was opened yesterday, a couple hours ago. So that's what's going on here. So -2 is when the shell was started, -1 is the current date, 0 and above are epoch times. So that is the number of seconds that have elapsed since January 1st, 1970. So if I give it 0, we can see that it actually, it doesn't give me 1970, it gives me 1969 -5 because of my time zone. That's what's going on there. But you could give it any sort of epoch time and it will format it in a nice way. So eventually, if I keep giving it enough zeros here, it'll get out of 1970. Hey, look, we're almost there. What do you think? One more 0? 1970? No, probably one more, right? There we go. Now we're in 1973. So that's cool. So it might be a little confusing at first, but we can give it a stirref time formatted string here, and then you can give it the epoch time you want here, or a -1 for the current date and time. Now we can do the opposite. You've probably seen +%s to get the current date as an epoch time. We can also do this with printf. We can do printf, %t, open and close parens, and then %s in here. Let's put a new line there, and then give it a -1. And there we go. There's our current epoch time. Or here was the epoch time that the shell was started. Note that that will never change. If you want to see that in seconds, you can look at, not uptime. What was I thinking? I totally just blanked on that one. Seconds. It's literally a variable, all caps, called seconds in bash. When you run this, this is the number of seconds that the shell has been running. So cool. It's just a cool, nice little internal variable for you. Also, if you're trying to get just the epoch time like this, if your version of bash is new enough, you probably have epoch seconds, which is the exact same thing. It will get updated every time you expand it. And epoch real time, this is the same thing, but with microsecond resolution, which is pretty cool. So kind of neat, kind of cool. Okay, now I want to talk about something really cool. We've been talking about matching patterns and all that stuff. We've been talking about formatting data. We have regex. We have regular expressions in bash. They are built into bash. It has its own regex engine. It might link against the system, whatever. The specifics don't matter. Bash has its own regex engine and we can use it, which is super cool. So I want to show you what I mean by that. If you've never seen regular expressions before, I'm sorry, it's going to be a little bit confusing. I can't go over all of it in this course, but I can touch on it. I can give you some of the basics, all right? So let's jump into it and let's talk about, first of all, what do we want and what do we have? Because as you notice, I'm in a directory here that I've already set up. I have a couple scripts waiting for us, and I have an images directory and a want.txt. Let's talk about that. Okay, so in our images directory, it's a little bit of a lie. They're not actually really images. They're just empty files. But take a look. We have 2 files in there. I'll go ahead and list them for you. We have fun family party and then a random date stamp, and not fun enemy party and a random date stamp. So not fun enemy party is so dumb. So what do we want? Well, luckily we have want.txt. So here's what we want. This is a little challenge for us. We want to take these file names and extract this metadata from it. So we want this date here, but we want the date to show up at the beginning. We want there to be a colon, and then we want the name of the file, which is the part before the left of the hyphen. That's how we want to format this data. So the challenge becomes, how do we do this? Well, we have 3 different scripts here, and I want to talk about them. So let's go ahead and look at the first script here. Okay, so here is our simple script, and I'm going to walk you through it, so don't worry. The first thing we do here is we define a variable called re. This is our regex. This is how you make a regular expression in bash. We just made a very simple regex that matches the beginning of the line. It looks for either the text Dave or Joe, and then the end of the line. That's all it does. Now it's in a parenthesis, so we're capturing it, and I'll talk about that in a second. And then our input is Dave. So then we check if input matches the regex, then we print match or we print no match. Now this should match because it's very simple. Dave should match against this regex of simply Dave and Joe. So once we're in this branch of the if statement, there's something kind of magical that happens here. We have a magic variable called bash rematch, which is for the regular expression match. It is an array. There are multiple elements in this array, so let's go ahead and print out what is in this array. So there we go. We are printing out bash rematch. Let's go ahead and close those quotes right there, and we're going to print out every element separated by new lines. So when we run this, we can see that there are two elements, Dave and Dave. They might be a little bit confusing, but if you've used regex in the past, it will make sense to you. What's going on here is the full string is always the first match, the first part of the array. The first part of the array is always the full string. That is everything that was there. And now this one is the first capture group, and then so on and so forth if there were more capture groups. So we have Dave and Joe here. Now in this example, it's just gonna match the full string always, so that makes sense. Let's go ahead and change this to just beginning with D or beginning with Joe and having anything here at all. So that means it has to start with a D or has to start with a J, but we have parentheses around it. So if we rerun this, it will match the full string was Dave, and the part that matched, the part that we captured, was D. So that's what's going on here. This is the basics of doing regex here in Bash, and it's incredibly powerful. So let's get back to our original challenge here. We have these images, and we want them to look like that. We want to print this to the screen. Well, let's go ahead and look at our fine example. If we look at our fine example, you can see we do for f in images star. So we're going to loop over every file that is in the images directory. We're going to get the base name of the file. Then we're going to echo the base name, pipe it to cut. We're going to cut it based on hyphens, and we're going to get the first field. That might be a little bit confusing. Let me go ahead and pull up the source code for that, and let's go ahead and ls the images. All right, let's do them separated by new lines. So we're going to get the base name of this file. So the base name is this whole string. Then to get the name, we're going to take the base name and put it into cut, look for the hyphen and grab the first field. So here's the hyphen. We're going to grab the first field here. Notice there is extraneous white space to the left of it. Then we're going to grab the second field and so on. So everything after the hyphen, because look, there are also still hyphens here. So we're going to grab all of this. We're going to cut it based on a period and get the first field. So we're going to get just this section of it. And then we're going to pipe it to xargs echo. This is a nice little trick to get rid of extraneous white space. Remember, this is a fine solution. If I saw a script like this and it was quick and dirty, I'd be like, yeah, I know what you're doing. I get what's going on here. That makes perfect sense to me. So if I run the fine script, hey, look at that. It gives us what we want. It works. It works for all intents and purposes, and it's fine. There is a better way to do this if you use regex. Let me stop right there. I don't have a problem with this. I think this just could be rewritten to have a much less fork and exec and to use a lot of bash built-ins. Like again, if I saw this, I wouldn't be like, oh, this is terrible. I'd be like, no, this is a bash script. I understand what's going on here. But let's look at how we could redo this with regular expressions. So, like I said, if you have never seen regular expressions before, you're going to look at this and be like, Dave, are you really telling me this is easier? Unfortunately, yeah, because like, I don't know, I kind of just like regex, so I look at this and I can see exactly what's going on here. So we're matching anything up until a slash, and then we want anything with a space hyphen space, and then we're looking for is a number 4 times, a number 2 times, and a number 2 times, because remember, year, month, day, and then dot anything, because there's going to be an extension. So we loop over the files, we check if the regex match. If it didn't match, we just try again. We just do the next part of the loop. We have pretty decent error checking here. Then we can extract the name by looking at the first part of the array. Then we can extract the date, and then we just print this. So even though this might be confusing and it's tough to write this once you have this, look how simple this becomes. So again, this is a static choice. This is a personal preference if people like regex or not. There are people who are like, no, I don't ever think it's the right solution. And you know what? I kind of low-key agree with them, but it's an incredibly powerful thing, and I would be remiss not to show Bash's regex engine because it's really, really powerful. So look at this. We get the same output here. We're using regex, and the cool thing is we're not forking out to external tools. So if we were to run, what is it, 01, it does a lot of fork and exec for all those tools. We could time this, and we can see that it takes 0.039 seconds. Again, very fast. When you're benchmarking something, you shouldn't be, you should be in the realm of seconds, not milliseconds, because then you're getting down to the level of like the system actually having to do things. Long story short, if we run this, we can see that it executes roughly, 3 times faster. So if you were doing this across a lot of files, you can see that that would make a big difference. Yeah, 0.039 for the fork and exec version, 0.013 for the regex version. We're not forking any external tools. We're using all bash built-ins. So again, if you were doing like a lot of data, a lot of batch processing, then this is just probably going to be faster. It's still regex. It might be a little bit brittle. Again, if you're using regex to try and parse something out, you're probably not in the cleanest API that's ever existed, but you know, that sometimes you're there. Sometimes you just need to bust out the regular expressions and hey, bash has them built in. That's the point of this lesson. So now I want to talk about another bash built-in that I think is super cool. It's very powerful. It is called mapfile. There's mapfile and there's read array. Now here's the good thing. I'm not actually going to talk about two built-ins because take a look at this. If we do help mapfile, we can see that we get a whole help page. I'm not going to go through all this. I'm not going to scare you. Don't worry. Let's do help on read array. Oh, a synonym for mapfile. They're the same program. They just run the same thing. So that's super nice. It makes it very easy to understand. I kind of just use whatever one makes sense with what I'm doing. If I'm trying to read data into an array, I'll use read array. If I'm trying to map a file, I'll use mapfile, but they both accomplish the same task. So let's talk about it. There's a lot here. So I have a bunch of scripts that I've already written because I feel like this is going to better illustrate what's going on. Notice that I have a data.txt. Let's go ahead and cat what's in that. Let's actually just cat it. There we go. There's 3 lines of data and there's multiple words on it. In fact, we know about word count. We can see there's 3 lines of data, there are 12 words, and there are 66 characters. Hey, that's super cool to know. It says, yo, what's up, everyone? My name's Dave, and you suck at programming. That's kind of my tagline. It's been my tagline for my videos for a couple of years now. That's awesome. So what's going on here? Let's take a look at our first script, 00 while read. Here is a basic way to read that data, to read that file into an array. So we make an array here. Cool. We loop over every line in that file. So we read that file, and then whenever we get a new line, we push it into the array. So this is very verbose here. And then we print the array. We've used this printf notation before. We put the less than and greater than just because it looks kind of neat. And if we run this, what do we get? Well, we get all 3 lines. Yo, what's up, everyone? My name's Dave, and you suck at programming. Hey, that's pretty good. What is mapfile? And why is it better? Not necessarily better, just serves a different purpose, but I want to show you how simple this can make it. Are you ready? Remember all those lines of code? Look at this. That's so easy. Mapfile. We run mapfile and it reads in from a file. This argument is optional. This is the name of the variable. So array is the name of the variable. So when I go to print array here, it's defined because mapfile defined it. So let's go ahead and run that now. And what do we get? Well, this isn't great. Look at that. Why are these showing up on the next line? That's because mapfile doesn't trim the delimiter by default. The default delimiter is new line, and it does not trim the new line off. It retains the new line. It's probably not what you want, so let's look at this other file that I have called mapfile trim. The exact same thing, but look at that. -t. -t will just trim the new line. No trickery going on here. Look at this. It's exactly the same as the first example, but one line to read an entire file into an array. That's awesome. Be careful with this. You better know how big that file is, because what if that file is huge? You're trying to read the whole file into an array. You got to be careful with that because you're reading the whole thing into memory. So know when that this is appropriate to use. Or let's talk about this example, mapfile limit. Look at this, -n2. Now, instead of array, we called it foo. That's the only difference there. But other than that, it's exactly the same. We're reading in, but we're giving it a -n2 argument. What does that do? Well, it limits it. Yo, what's up, everyone? My name's Dave. And it just doesn't have the 3rd line. So -n2 tells it to only read the first 2 lines, and then it stops after that. It reads up to 2 lines. So that's what's going on there. Now, mapfile, as you saw from the help page, there's a lot of arguments going on here. I'm not going to talk about every single one, but I am going to talk about one specifically that I think is really cool. Now, brace yourself. There's going to be a lot here, but we're going to work through it. This is mapfile with a callback. So let's ignore this function real quick. Let's go down here. Mapfile -t, we know what that does. -C, and we give it the name of a function. -c1, we don't know what that is yet, and foo. So it stores it as foo, as you can see right here. But my func is defined up here. We have my func up here. It takes a line as the first argument, and it says mapfile, called with line. Here's the cool thing about mapfile. It takes callbacks. I can process the line by line as it comes in. So mapfile still works the exact same way, but it will fire off that function every time it reads a new line, and I can deal with it there. The reason it's every time it reads a new line is because I gave it -c1. That means only read one at a time and fire my callback. Only fire my callback after reading 1 line. Because -c is the callback. Evaluate callback each time quantum lines are read. How much is the quantum? Well, we can specify it with dash lowercase c. We specified ours to be 1. Quantum, I think, is way bigger than that by default. I don't actually know. It might say it somewhere. But, oh yeah, the default quantum is 5,000. That's crazy. I don't know why you'd want that. But, yeah. So you can actually register a callback to fire whenever a line is read. I have yet to find a super useful use case for this, but it's still a really cool thing to know about mapfile. And again, mapfile and read array, they are just the same thing. So you can just do that, run that, and it works exactly the same because they are just synonyms of each other. The same way that dot and source are like the same program. Cool, so let's switch gears a little bit. There's something else I want to talk about. I want to talk about test versus single square bracket versus a double square bracket. We touched on this early in the course, but I promised I would go deeper in depth, and here we are. So let's talk about what I'm actually talking about here. We have a lot of files here. We're not going to jump into them yet, but what I'm talking about is the double square bracket notation, the single square bracket notation, and the test command, just so you know what's going on. Here's the quick little synopsis. Test is both built into bash, and it also exists on your system. Single square bracket is exactly the same as test. The only difference is it requires a closing square bracket. That's just part of its syntax. But here's the thing. It's built into your system, and it's also on the file system. This exists. This is a program on your file system. I can run file bin open square bracket, and I can see it's an executable program. I can run it. I can do this, -f, etc password, close the square bracket, and then I can check to see that, yes, that file did exist. So it is a program that exists on your system, but it's also built into bash. Bash does have its own thing, though, which is this. And as you can see, here's the difference. Test is a shell built in. Single bracket is a shell built in. This is a keyword. Keywords are slightly different. They have different rules about how variables are expanded, so you can get away with some stuff using double square bracket that you can't with single square brackets. When you're using single square brackets, you want to quote all your expansions because it's being executed like it's a program. The double square bracket, you don't need to quote your expansions. You don't have to quote every single expansion. Some you will want to, but you don't have to because it's a keyword. It's processed with different rules than built-ins are processed with. So let's go ahead and jump into some of this. Let's look at the first example here. Simple test. If test-f foo.jpg echo foo.jpg exists. This seems pretty simple, right? We're going to run this command. It's going to check to see if foo.jpg exists and is a regular file. And if that command's successful, then we will echo that. So let's go ahead and run that, and it doesn't exist. So let's go ahead and create, what was it, foo.jpg, run it again, and hey, foo.jpg exists. That makes sense. That was very simple. Let's go ahead and look at this example. So this is the same thing, but instead of running the test command, we're just using a single square bracket, both the beginning and the end of it there. So if we run this, we should get the exact same thing, foo.jpg exists. Cool. Let's look at the next one. Simple double square bracket. The exact same thing, but we're using double square brackets. So let's go ahead and do this, and hey, we get the same thing. Cool. So they all operate pretty much the same way. Anything you can do with the single square bracket or the test command, you can do with the double square bracket, plus it can do more. I personally always use the double square brackets with bash. I will never use the single square bracket or the test command. There's just no reason for it. The double square bracket does everything I need, and it's a keyword, so it's parsed in a different way than other built-ins are. So let's look at the next file here. We have 03 patterns. Now this is interesting. We make a variable called f, and we call it test.jpg. So we're not actually looking at the system for this. We just have a string called test.jpg, and we're checking if $f = star.jpg. So that's a wildcard match. What do you think is going to happen? Are we going to print that it is a JPEG file or that it's not a JPEG file? Let's go ahead and run it, and it is a JPEG file. Hey, that's cool. It passed the test. That is awesome. Now we have one called pattern fail. Man, I really didn't bury the lead at all with these file names. Same exact thing, but we are using single square brackets. $f = star.jpg. So let's go ahead and print that and then run it. And we can see test.jpg is not a JPEG file. This command expects a literal match. It's looking for an actual star.jpg here, so you better be careful with this. Also, if this file exists on your file system, you might want to be careful about this. If we touch test.jpg and then we run it again, now we get too many arguments because it expanded. Multiple JPEG files were in there. We can see we have foo.jpg and we have test.jpg. It expanded those in place and added it as another argument. So you got to be careful when you're using the single square brackets. This is why I stay away from them. Proper way to handle it would be like this, and then you can see once I quote it, I don't actually have the wildcard match, so this just isn't what I want. This is why I stay away from them. Let's go on to this one. With the double square brackets, we can quote it, and if we quote it, we will disable the expansion. So let's go ahead and look at the example 5, and then we'll run this, and we can see test.jpg is not literally star.jpg. It is not literally equal to that star. So if you want to forego the wildcard matching and you just want literal checking, quote the right-hand side of the expansion when you're in double square brackets. Quoting will disable any sort of special meaning, usually in the shell. The next thing we have here is numbers. So we have a equals 9 and b equals 10. Now we are going to use the double square bracket notation to check if b is greater than a. So b is 10 and a is 9. So is b greater than a? Well, yeah, 10 is greater than 9, right? So let's go ahead and look at this. We have b is greater than a, otherwise it's going to print uh-oh. So let's go ahead and run this, and we can see uh-oh. Well, this is weird. Hold on. Didn't I tell you guys to use the double square brackets and now this is happening? What's happening here? Well, here's the thing. This notation, this greater than, is checking a string comparison between these two, and 9 sorts before 1, or sorry, 9 sorts after 1. It's comparing the 9 against the 1 here, so it's comparing them like they're strings. It's like an alphabet, or is it lexicographical sort? I might have butchered that term, but yeah, that's what's going on here. You would have to use a different notation instead of saying, what was it, 10 is greater than 9, which will be a failure. You would have to use dash GT for greater than, if I can find the dash character, dash GT for greater than. You have to do that way if you want to compare them like numbers, okay? If you've done POSIX scripting, you've seen this before. Here's the thing, we're in bash. We do not have to worry about that. Circumvent all of that. So I actually, oh wow, I already have a fix for it here. So I forgot I wrote this one, but yeah, I have a fix for it here where I fix it by doing the dash GT notation. Then you can see 10 is greater than 9. That makes sense. Here's the thing, we are in bash, okay? We're in bash, so let's not forget that we have double open paren. Just do the double open paren, b greater than a. We don't need to quote the expansions. Look at that. We run this and it compares them like numbers, and it works exactly how we would expect it to work. So there you go. This is a quick little synopsis of test versus single bracket versus square bracket. I do have a longer form video where I dive into it more specifically, I think, and kind of just talk about some of the history of it and stuff. I can like every video, I'll link it at the end. I gotta stop shouting these out. Cool, so now we're going to talk about special strings in bash. Now what do I mean there? Because when I echo something like hello, I can also quote it. I can put single quotes around it, which will prevent expansion of variables. So if I put hello $user, you can see that it does not get expanded. I can use double quotes, which is the same thing, but it does expand expansions like that, which is pretty cool. So what do I mean by special characters? Well, I'll show you. Let's do hello tab user. If I print that, it doesn't print a tab, it just prints a literal backslash. But I can do echo -e. -e tells echo to read a backslash tab and turn it into a tab character. So this is still a backslash tab. We're giving echo a backslash tab, but echo is operating differently because we gave it -e. So echo is interpreting that as a tab and putting a literal tab character there. That's awesome, but here's the thing. We can do this ourselves. We don't have to tell echo to do that. We can give our own string with a $sign and an open single quote or double quote, but we're gonna use a single quote here. Open single quote, $sign, open single quote, and now it will actually go through and it will expand these special characters. That's what the syntax means. We can expand special characters like this. Notice we use single quotes, so it didn't expand $user. If we change this to double quotes, we can see that we still get this, so this isn't great. It's because of the string parsing rules in bash. We technically have to escape this or do something weird. We can also store this as a variable, so we could say var equals hello tab world, do this, and then we can echo var. Notice that we have to quote it. If we don't quote it, the tab will get turned into a space because of word splitting, and that's how bash handles it. So we have to quote it, and we will get the literal tab character there. Notice that we're not giving echo the -e. We're not giving it a /t. We're giving it a literal tab character. So this is incredibly powerful because we can do some kind of neat things here. We could say, foo new line bar, and now we can emit new lines like that. There are some other characters. We have tabs. There's a really fun one. V, I don't know if you've seen this. This is a vertical tab, so it goes down on a new line and then also tabs it. So this is kind of neat. I don't see this one super often, but that's kind of a cool way to draw things, isn't it? We can also do \B for a backspace, so we could do foo bar like this. And as you can see, it kind of backspaced it. So let's put another backspace there. Okay, and let's put a third backspace there, and then you would never know that foo was even there. Technically, the character is still drawn there, but the terminal hides it from us. If we wanted to, we could pipe this to XXD, and we could see that we have foo, 3 unprintable characters, and then bar and a new line, and the unprintable characters are 08, 08, 08, which are going to be this backspace character. So that is pretty cool. These special strings are super useful. You will see them used. People will do something like IFS equals space tab new line or something like this. If you use the special character, you will get the special meaning from it. Pretty cool. Some people just do things like tab equals this, and now they have a tab character they can use anywhere in their code. So they could say like Dave tab, and now there we go. Now we have a tab. And of course we could say Dave tab buddy, but that's not really going to work because tab buddy isn't a variable. So this is where you'd want to use those curly braces. Now we can separate them with a literal tab between them. So you can store special strings in variables, which is pretty cool. Pretty nice to be able to do that. All right, so now I have a fun one for you. We're going to talk about signals. We're going to talk about communicating with our process from within our process or from the outside world. So we're going to talk about signals. Signals are handled by your operating system. You might be used to like sig term or kill-9, which is sig kill. You can't trap that signal, but there are other signals you can trap, and we're going to talk about that. So these are provided by your operating system, and we're going to show you how to, I'm going to show you how to trap them and how to respond to them in your bash code, which is pretty cool. So before we even jump in here, we're going to be using the trap built into bash, so you can do help trap on it and you can see it. There's a whole bunch of options here. One of the things I like is trap -L. This lists all of the signals that you can respond to. So these are the signals that your operating system makes available to bash, and we can trap any of these. SIGINT, this is the interrupt signal. This is what is sent when I hit Control-C. SIGINT is what is sent when I do that. SIGWINCH, this is sent if your terminal is resized. SIGINFO is only available on certain operating systems. With my shell, because I'm on macOS, I can give a Control-T and it will print a SIGINFO. There's no process running, so I'm just getting a little bell warning up here. Yeah, there's all sorts of fun signals. So let's go ahead and look at what we have here. So we have our simple exit script right here. So what we do is we define a function called cleanup, and then we echo cleanup function running. Okay, very simple. Then we trap cleanup to exit. So the way trap works is here's the code you want to run. So I just gave it a simple function name, and here are the signals you want to trap. You can give it multiple signals. I just gave it exit. Exit is a special like pseudo signal, which basically hooks it up to the @exit caller. This means before bash quits, before this script is done, it will always run this code, which is super nice. Put a little asterisk next to always. You could technically kill -9 and then it wouldn't have a chance to run this because you can't trap it. But this is your best effort at trying to run something at the end of the script. So we're going to print script starting, ... script done, and then we have that cleanup function. So let's go ahead and look at that source code. Let's run this, and we can see script starting, ... script done, and then cleanup function running. So this ran at the very end because we trapped it to the exit signal. So that's pretty cool. Here's a really cool way to sort of like defer cleanup. If you make like a temporary file or something like that, you can put that in your cleanup function to remove that file or whatever you need to do. The next one here is we need to talk about codes. So take a look at this. Script starting, ... script done, and then we exit manually with the code 1. Now notice the cleanup function will run, and cleanup doesn't have exit in it at all. So what's going to happen when we run this? Let's go ahead and run our code here, and we echo $?, and that's the nice thing. The code that we exit here is retained. So whatever runs here doesn't really matter. We're still going to exit with that same code unless we override it. So let's talk about this next one, which is called exit override. Hey, look at that naming. I'm awesome. So we have the cleanup function that exits 2 here. That's the only addition to the script. We're going to exit 1 at the bottom. We're going to exit 2 at the top. Let's go ahead and quit out of this, pull up that source code, run it, and we can see that the cleanup function is running. That's all well and good. Let's print the exit status, and look at this. We get 2. So you can override it in the cleanup function. I don't really mess with this myself. I don't worry too much about it, but this is just good to know, good to be aware of that this is a thing that can happen. All right, so let's talk about this next one. This one's called trap debug. This is really cool. This is another bash internal thing. This isn't really a signal sent from your operating system, but you can trap something called debug in bash and have it run myfunc. So my func up here just prints debug running, and then there's a variable called bash underscore command. So let's go ahead and run this and see what happens. Look at that, debug running, echo script starting, debug running this, debug running that, debug running that. It's very similar. If you remember bash minus X, we could run that and we can get the sort of debug output. So you can actually trap that signal and run code as a response to it, which is kind of cool because it's a little bit more advanced than bash minus X because I'm running code here. I could do some work. I could format data. I could grab something off the file system. Probably don't want to do something too heavyweight here, but you could, the option's there. And last but not least, I want to show this because we can trap siginfo. Now here's the thing about siginfo. I mentioned it, it's on my system, but some operating systems don't have siginfo. Like I don't think Linux has siginfo, so you can do error checking. Trap will return a failure if it's not there. So on this program, this is only going to work if my system supports siginfo. Otherwise, it's just going to stop the script. But if it does work, we're going to go into an infinite while loop where we sleep for 1 second and we print the word running. So if we go ahead and do this, we go into an infinite while loop, we print the word running. I'm going to hit Control T. And we'll get some debug output about what's going on, but look at this. It printed hello world. So we can actually trap that signal. Now, of course, we don't have to trap siginfo if we didn't want to. We could trap sigint, and this is the interrupt signal. So now, when I hit Control C to stop this, it doesn't stop. So what do I do now, huh? Ready for this? We're going to Control Z it, which puts it in the background. Now it's in the background, but it's paused. It's not running. If we wanted to start running, we could type BG and hit enter, and then it starts running the process. I can't actually talk to it. That's super annoying. So I'm going to type an FG to bring it back to the foreground, hit enter. Now it's running in the foreground. Control C, I still can't stop it, so we're going to kill it. Control Z stops it. It's not running. I can run jobs to see all of my currently running jobs, and I have job 1 here. So let's go ahead and kill %1. There we go. So now that process is dead. It has been terminated. Terminated with signal 15, which is sigterm, the default kill signal. So that's what happened here. That's how we broke out of it. So yeah, backgrounding jobs is super convenient. When you have anything running on the shell, you could do like sleep 60. I can Control Z that. It stopped it. It paused it. It sent it a sig-t stop signal. And now I can either make it run in the background with BG, or I could bring it to the foreground with FG, or I could kill it with %%, which is %% is just the last process that was put in the background. So that's how that worked. All right, now I'm going to show you guys something cool because this is not bash specific. This exists on your operating system and other programming languages can use this, but we can use something called a named pipe. Now, you know, in bash, we have a basic pipe like cat, pipe, grep, and here's the pipe here. This only exists between these two processes. We can make a pipe that's like a file. It sits on your file system and technically any process can write to it. So I could have communication between like a process written in C and a process written in bash. I could have the C program writing to it and the bash process consuming it, which is pretty neat. So I'm going to show how we can do that here by making a pipe. So let's go ahead and make a pipe. Make FIFO. First in, first out. We'll make FIFO. We'll call it pipe. This is just the name of the file, so we could put // here. And now we have a file here called pipe. And pipe is pretty cool. It's very, very simple. Let's go ahead and do something very rare. I haven't done this yet. I'm going to pull up a tmux just so I can split this terminal so you can see both of what's going on. I don't have a session, so let me create a new session. Let me split this pane. Do I want it vertically or horizontally? I think I want it horizontally. There we go. Okay, so now I have tmux here, so I have 2 different terminals running, and you can see each one here. Here's the cool thing. I can echo hello and put it into pipe, and it just hangs. It just hangs until something comes and reads it. So I can go down here, and I can read that pipe. Ready? When I hit enter, watch what's going to happen. Both of the prompts return. I get the data down here, and this echo is done hanging. So pipes are really cool. The opposite is also true. If I cat pipe, it will hang until something writes to it. So if I go up here and I echo into it, echo returns immediately. The cat finally hangs. This is why pipes are so useful, because they will block until something else is talked, so you can synchronize communication between the two things, which is really nice. And of course, you could have external processes reading and writing a pipe, or you could have the same process talking to itself over a pipe. You may want that for some reasons, depending on what's going on here, or something else can tap into that pipe and see what's going on. It's really cool. All right, so let's see what we have here. We have a script called Basic Reader. Basic Reader is very, very simple. Look at this. We just do a while read line, we read in from pipe, and then we print read line and then the line that we read in. There's no trickery here, I promise. We're just going to run this, and this is going to hang. It's going to hang until something writes into the pipe. So let's echo hello into the pipe down here, and watch what happens. It prints hello up top. We got that message successfully. But you notice it just exited. So it read it once, and that was it. So if we want to read forever, how can we do it? Well, get ready for the cheapest solution ever. Put the whole thing in a while true loop. I mean, it works. You can totally do this. I'll show you other ways to do this later in later examples. But for now, this totally works. So we'll run that forever reader, which looks like this. We'll run the 01 forever reader, and then we can go down here and we can pipe data into it. We can continually pipe data into it. We could run a command and put it into the pipe. We could do anything, really. We could printf. Remember how we learned how to use printf? Hello, and then pipe that into pipe and get nothing? What happened there? Oh. Wow, okay. I'm actually glad I messed this up. I'm really glad I messed this up because this is a good learning experience. Do you know what's happening here? The above example is waiting for a line. It's reading a line. I have not omitted a new line yet. So let's go ahead and omit a new line. Let's just echo a new line into the pipe. There we go. Now it read all that garbage there. Did it lose all that stuff? I don't actually know what happened there. There we go. This is what I expected. I'm gonna be honest, I don't know how we lost that data. I'll have to do more digging into this. But yeah, so this is the beautiful thing. We can just kind of read until we see a new line, and we can get that data up on top. We technically don't have to read to a new line. We can just read until data is put there. There is a max size of how much you can write to a buffer at one time, so be careful of that. You will bump into some sort of limits there. But this is the cool thing. This thing will forever read up here. Let's back out of here and let's see what we have. We have the forever read. Let's go ahead and start that and just let that keep running. And then we'll go down here and we'll look at the client writer. So this is an interesting script. We start the script, we give it a name, and then it sleeps for 3 seconds and it says client name, and then it writes to the pipe. So let's see what that looks like. Let's give it a name of foo. Okay, we run this, and remember it sleeps for 3 seconds before it does anything. So look at that. Every 3 seconds it says that it read a line, it was from client foo, and it said hello. That's great. Here's what we can do. I haven't showed this yet, but we can put an ampersand at the end of this command, and it will put it in the background. So remember how we Control Z a program to put in the background? This is the same thing, but the program won't be frozen, it will be running. So that program's in the background, and it is running. So every 3 seconds, it will write up here. We could put another program in the background. We could make another instance of this and call it bar. We can make another instance of this and call it Baz. Now we have 3 writers all writing up there and being read in there. So now we have 3 programs that are running in the background. We can run jobs to see them. We have job 1, job 2, and job 3. These are all running. So they will just continue to run and to continue to go there. And this will just happen forever until I kill them. So let's go ahead and do that. Let's kill %3. Let's kill %2. And let's kill %1. Now, if I hit enter, you can see a bunch of jobs terminated. They're all done. If I go up here and put a bunch of new lines, nothing else should get read. So yeah, that's a simple example. That shows the power of having one reader, but multiple writers. So you could have multiple things talking through this pipe, kind of signaling their progress if they were working on something. All right, so this is really cool. Let's back out of tmux and let's look at the final example here. We have something called all-in-one. There's a lot going on here, and I'm going to explain what's going on here. We are using a new built-in we have not seen before called exec. Exec can do a lot of things, okay? Exec can execute commands and make your shell become that command, but it also has this alternative syntax to open file descriptors. So I can do something like, hey, open file descriptor 3 for writing, and I want it to be dev null. So that way when I write to file descriptor 3, like echo hello, and write it into file descriptor 3, it goes directly to dev null. You can do that with exec. Now, instead of hard coding 3, we can use this syntax to store the file descriptor number in FD. We say, hey, open this, give me whatever file descriptor number you want, and I want to open this file for reading and writing. That's what the less than and the greater than's for. And the file we're opening is pipe, the FIFO that we created above. So now we go down here, let's ignore the function for now. We fork off a client foo, we fork off a client bar, we fork off a client baz. Very similar to what we did before. And then if we look up here in this function, the client is exactly the same. We take the name as the argument, we go into an infinite while loop, and we sleep for 3 seconds, and then we just write into that pipe. Now down here, here's the key. Remember that forever read where we wrap the whole thing in a while true? We don't need that down here because we're not putting the file name here. We're not doing this. We're actually telling read to read in from a file descriptor. Read takes an argument -u, which is a number of a file descriptor to read from. So we're not telling it, we're telling it, hey, you're not reading from standard input. You're not reading from a file. You're reading from this already open file descriptor. So it'll happily do this. This is all of the stuff we were doing in that last example, all in one script. So this script is basically talking to itself. It's forked off 3 children that are running in the background, and they're talking to that pipe, and as that data becomes available, it's there. So that pipe still exists in the file system, but it's open. It's an open file that exists in that program until I kill it with Control Z. And that's all there is to it. And then when you're done, you can clean up, you can just remove that pipe, and you're good to go. It's just a file that lives on your file system. All right, so now I want to talk about something fun. I want to talk about color output, putting color on your terminal. What am I talking about? Well, take a look at this. Notice how Dave and YSAP is colored. We have a nice little blue color here. We have a green color here. If we were to pull up some commands, I think earlier I pulled up htop. You can see that there's a whole bunch of color going on here. How do we get that? Well, I'm going to show you the basics of color because we can use it in Bash. This is not a Bash specific thing. You can do this in any language. I'm going to show you how to use Bash to create these sort of color codes. So let me explain that if you've never seen this before, imagine we were writing HTML for a website, okay? You might have something like this where I can say, what was it, bold? I don't think people use the bold tag anymore. This is very old, but let's say we're using a bold tag or B for bolding your stuff. You could say, this is bold. And then you close that B tag, and there you go. This is how you do it in HTML. This is how you instruct your browser to make that text bold. This doesn't work on a terminal, obviously, but there is a way we can instruct our terminal to make the text bold. The way we do that is by using something called ANSI escape sequences. Here is what I'm saying, ANSI escape sequences. And we do that by using the escape character, which is a specific byte that we can emit to the screen. And then we put some other text after that, and then we close that sequence. So basically how we did this, you can think of the escape character as this less than sign, and the rest of this is the sequence. That's not exactly what it is, but I'll show you what I mean by that. All right, so if you don't know what I'm talking about, I'm gonna pull up a web page here real quick. So in order to talk about that, we have to talk about the ASCII table. So these are ASCII characters. There's a lot of history here. There's a lot of stuff I can get into here. I don't have time to really talk about all of this. It's kind of outside of the scope of this course. But what you need to know is there are 256 possibilities here. So another way of saying that is 256 possibilities. That means there are 8 bits. You can see what they look like in binary here. Or there is 1 byte because there are 8 bits to a byte here. Now, there were 128. Now there's 256. They all fit comfortably into a byte. It might even go beyond that. There's like ASCII and then extended ASCII. There's a whole rich history there. Like I said, I don't have time to get into it, but let me show you just a quick example. Like if I wanted to print the letter A to the screen, I actually have to write this binary, this single byte. It takes a whole byte to print the letter A, or I could print the number 141. No, that might be octal. The number 97. Or I can print 61 in hex. So this is a hex number right here. So you can see like 5F, 60, 61. So that might be a little bit confusing, but if I emitted hex 61 to the screen, I would get the lowercase a letter. And then if we scroll up, we did this before earlier in the course, I emitted 0A if you remember. If we scroll up here to 0A in hex, you can see that that emits a line feed. That is the new line character. So let me go pull up the terminal real quick. So on the terminal, we can use printf. We did this previously to print raw bytes to the screen using %b as the format specifier. Technically, we don't need the quotes because there's nothing special with %b, but I just put them here to let you know that this is a format specifier. This is just a raw string. Printf is taking the string in, and then it will format the arguments so it will interpret backslash. So I can do \x for hex, and then I could say the letter A, which was 61, and then close that. Then I could do it again, because remember, printf will repeat the format specifier for each argument we give it. We could say 0A. So if this works, we should print the lowercase a and a new line. And there we go. We get the lowercase a and a new line. We could prove this. We could pipe it to XXD, and we just get 61OA, which makes perfect sense. We have 61OA. So that's what's going on there. This is important because now we can print characters that are unprintable. There are certain characters that have a special meaning but don't actually show up in any sort of meaningful way on the terminal. So let me go back up here and show you a character on the website. This one's going to be super useful. If we scroll up, we're going to see right here, the printable characters start at hex 20. Above that are the unprintable characters, and there's a lot of weird stuff here. We've seen some of them. We've seen things like horizontal tab. We've seen line feed, which is like the new line. We've seen vertical tab. We did a \V for that. There are some interesting ones here. The one that we care about is 1B. I just happen to have this memorized because I use it a lot. 1B is what we care about. Hex 1B, it is the escape character. So it's 1B in hex, it's 33 in octal, and it's 27 in decimal. So I will show you what that looks like. If we wanted to print the escape sequence, we could do printf %b, and then the same notation here, 1B, and then it won't actually print anything. Nothing will show up to the screen because it's unprintable. But if we pipe it to XXD, you can see there's a 1B there. Okay, cool. That makes sense. We can also give it octal if we wanted to. So 033, I think it was what it was in octal. Oh, nope. It's trying to convert that to a word. So I actually have to do this notation. There we go. So, yep. So same thing. We can give it the same kind of notation, but this time it's octal, but we still get 1B there. And the other one was the decimal notation. I actually don't know how to do that. I don't think you can just do that. Yeah. So it just assumed it was octal. I don't know how to do a decimal representation like that with printf, but you never really are going to use that because Bash has a special character that is built in that we can use, which is \E. So as long as we use that, that is the escape character. That's built into Bash. We don't have to worry about it. \E means the escape character. But that's just the character. So like in my HTML example, that would just be the less than sign. We still need the bold, and we need to close the actual HTML sign here. So we're going to do that now, but it's not HTML, remember. We're going to put a sequence here that tells it to be bold, and then we're going to close it. So let's tell it to be bold, and then let's close it. There we go. So now I can just printf bold like that. And then I print it, and there we go. It prints bold, and that text is actually bold. I should probably put a new line here so it's easier to read. Hey, that's really cool. That text is bold. Now, the funny thing is this text, as you can see, is also bold, but it's not bold up here. So we never actually closed the bold. Think of it like this. We opened up a B tag for bold text, but we never actually closed it. That's the HTML example. So let's go ahead and close it. We do the same thing. We need an escape character, which starts a new sequence, and then we will reset it. So instead of 1, we're going to give it 0, and then M to close the escape sequence to say that we are done. So if we have this, now we have bold. We have bold text here. So we have not bold, space, 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 and then bold over there. And you can see, hey, we have bold text in the terminal. That is really amazing. Now the terminal, when I say my terminal, I don't mean Bash, I mean my terminal. This program that I'm running, iTerm2 on my Mac, is what's responsible for interpreting that. Oh, cool. I accidentally cleared my terminal. Yep, sorry about that. So my terminal, the program, is responsible for interpreting that. What Bash is actually outputting, so there's a lot going on here, but as you can see, Bash is outputting all of this to the terminal, and the terminal's rendering it. So we have 1B, which is our escape sequence. We have 5B, which is the open square bracket. We have the number 1. We have the letter M, and then we have we have BOLD. So these 4 characters are BO and LD, the actual character's bold. And then we have, of course, our 1B here, which is our escape sequence. And then we have the standard 0. You don't need to memorize all this. You don't need to think about all this. This is just an easy way to debug it. Let's not use the hex viewer because that might be a little bit confusing to people. We can get bold this way. That is super cool. There are some other sequences we can do which are really neat. Instead of 1, what if we gave it 33? Okay, it says bold, but it's not actually bold. What if we called it yellow? Look at that. Now we have yellow. How cool is that? So I'll show you some more examples, but before we get into that, I want to show you that you can also store the escape sequence. Just like we've stored other characters before, we could do something like escape equals, and then we can do this special string notation. We could put the E like this, and now we are free to use it inside echo, which is cool. So we could say something like escape, and then it's the open square bracket 1M bold, and then we could do escape open square bracket 0M to close that, and we run it and we get bold output there. So that is pretty cool. Same thing, we could put 33 here. We can get yellow. It says bold, but it's still just yellow, and the 0 still actually properly closes the color, so we don't have any color leaking over into the next command that runs, which is pretty cool. I see a lot of code out there. In fact, I even use code like this where I generate my website. If you haven't seen my website before, I'm surprised I went this far into the video without showing it. ysap.sh, you suck at programming.sh. If you curl it, my website renders in the terminal. It's pretty cool. I have a whole video dedicated to how I make this, so of course that'll be linked in the references. But as you can see, there's a lot of color code stuff happening here. So there's a lot of escape sequences being opened, a lot of color stuff. There's even some italics going on. You can get very, very fancy with the code, and it's really, really cool. If I were to pipe this to XXD, there would be a lot. I'm not going to go through all of this, but feel free to take a look at it sometime. There's a lot going on there. So like HTML instructs your browser on how to format things, ANSI escape sequences instructs your terminal on how to display things. That's a good way of thinking about it. There is another thing you can do. You don't have to hard code these commands. This ANSI escape sequences, I find they work for most terminals out there. Most modern day terminals will handle them just fine. There is technically a command. This is not a fully portable command, meaning it might be different on different operating systems. I've had some issues in the past where FreeBSD's arguments to tput was way different than Linux's arguments to tput. I think for the most part, they're pretty similar now, but still I've been burned by in the past. So I just kind of put all my ANSI escape sequences in myself. I just write them myself, but you can use tput as well. Tput makes things very easy. Take a look at this. Tput bold, and this just prints the bold thing to the screen. Now, nothing was after it, but watch this. Echo high. There we go. High is bold. And then we can do a tput reset. Don't actually write reset, write SGR0. There you go. Tput reset, I think, does exist. Yeah, that'll just reset your terminal in case you get into a weird situation, or if you mess up your terminal, you can run tput reset, or your system might even have a reset. This doesn't reboot your computer, don't worry. This just resets your terminal in case you get like weird color or your cursor's in a place you don't expect and things got all messed up. Reset command is a lifesaver. But yeah, with tput, we can do all sorts of things. So remember how I used that color 33? Well, I can actually do tput setaf3, echo high, tput sgr0, which is the reset, and it says high. So yeah, no trickery going on here. If I were to do, what was it, tput bold and pipe that to XXD, you can see that it's doing the same thing. It's still giving me the escape sequence 1M. So it's the same exact stuff because my terminal supports this. Tput might be better at supporting other terminals out there. It's outputting something slightly different. I'd have to look in to see exactly what this is doing. This one's not exactly what I thought it'd be, but that's interesting. Set AF3 was to change the color to yellow, and as you can see, it just does 33M. Now I'm using 33. You could really use anything you wanted there. We have, let's change this to, instead of yellow, we could change this to 30M and just put color here. And we can see that we can't see it. That's because it's the black color. Then we have red. 32 will be green. 33 we've already seen as what? Yellow. 34 is cyan? No, blue. Oh man, shows how much I know. Magenta? Hey, got it. 36 is cyan, isn't it? Nope. I should stop. Oh no, it is cyan. That is cyan, right? Am I crazy? I don't know. I should just stop guessing. There's like 8 colors you can use here safely. And then there's an extension which gives you 256 colors. And then there is another extension which gives you like, what is it, 24-bit coloring, so like roughly 16 million colors. You can basically do hex red, hex green, and hex blue if your terminal supports it. I'll show you all that stuff. It can get a little bit confusing here. But yeah, we have like our colors are here, so we can do like 32 and now it's green. You could change this to 42, and now we've set the background color. So you can totally do that. You can change the background color. You can reverse the foreground and the background color. There's all sorts of magical, fun things you can do with colors here. I am just scratching the surface with it. There is, like I said, let's talk about the 256-bit color. This one's pretty cool. We do the escape sequence. We open this up, and we do, instead of like 33, we do 38, but now we put a semicolon here, and this next one tells us what color mode we are in. So let's do 5, and now we are in 256 color mode. So we can do 256 colors. So we have the number 0 all the way up to 256. So we could do something like that, put the M there to close it, and we could say color 0. And then let's go ahead and reset this and bring this back to done. Let's put a new line in there so it's easier to read. I know these printf commands can be kind of hard to understand, but hey, look at that. That's what color 0 looks like. This is what color 1 looks like. We still wrote out color 0, so it's a little bit confusing, but I have 256 colors, so I can put a large number of things here. So in fact, let's go ahead and make our own little color script. So let's cd into our foo directory. We are in our home directory, foo. Let's go ahead and make a script called 256 colors. Okay, user bin env bash. There we go. Let's back out of this. Go ahead down here, and we can do, let's just make it, what should we do? Let's do for I in 0 all the way up to 255. This is every single possible color. There are 256 possible colors, 0 through 255. And let's go ahead and printf the same thing we did before, which was the E, the 38 semicolon 5, the number, which we can use %d to put a number in there, and then we can put an M to stop it. Now we can say color %d, put the number in there again, put a new line here, and then let's go ahead and reset that with a nice 0M. All right, and that should be good to go. I think that's all we need. Let's go ahead and put the new line after the reset. Doesn't really matter here. And we're using the same number twice, so we only have to supply it as an argument once, which is kind of nice. This should be good enough. Let's go ahead and test this. I normally have notes that I can look at a little bit and kind of get an idea from running this. I'm writing this all by scratch, so we're going to see if this works. Let's go ahead and clear the screen and run it. Hey, that looks pretty cool. I don't love that it prints color 0 every time, so something didn't quite work there. Oh, this was my mistake. This is what I get for trying to code on the fly like this. You actually have to pass the argument twice. I got confused. I said that we have multiple things in this printf, but we only passed one argument. That's not okay. The opposite is true. If we only had one variable mentioned in the format specifier, we could pass multiple arguments. This is the opposite situation. We're mentioning a number twice, so we do have to give it twice. So my bad there, $I. Now we'll run this, and there we go. There's our beautiful 256 colors. So you also have this color palette to choose from, which is really neat. On top of that, there is also another one which your terminal may or may not support it, which is RGB true bit coloring. It's 24-bit coloring. All right, so to do this is printf, open up that escape sequence, open up this square bracket, and it's 38 semicolon 2, not 5 this time, 2. And then here we can do R, G, and B. And that's what we can do. We can specify a certain number of R, a certain number of G, and a certain number of B. So I will do %D, semicolon, %D, semicolon, %D, M to close it. And we can just say color, LOL. Like, it doesn't really matter what it is. So, and then let's go ahead and reset this with a 0M. We'll put the new line there. And now we can give it an RGB value between 0 and 255. So if we give it all 255, this should be white. There we go. Hey, that's awesome. If we turn down some of the blue, so we have red and we have green and we only have a little bit of blue, look at that, we get yellow now. If we bring that down to 0, then we have a more pronounced yellow. So you can mix and match. You could put like 45, 45, 90, and you can just start mixing colors together and get the exact color you want. If you know a hex value you want. If I wanted something very red, 255 red, a little bit of green, like 100 green, and just like a tiny bit of blue, give it like 60 blue, then there you go, you get a color like that. So yeah, my terminal supports it, your terminal may not support it, but this is how to use ANSI escape sequences to actually output color to the screen. There's way more you can do with this. You have bold, you have underline, you have italics and stuff. What I like to use, my reference, I've mentioned this before in a previous video, my reference is this gist, which I will link in the references at the end of this course. This gist is amazing. I love it. It talks about, it is a cheat sheet for every single thing you can do. So it talks about like the colors and stuff. It gives you the whole palette here. You can scroll down, you can learn everything about it. And there's way more that you can do with ANSI escape sequences. You can like move the cursor around and stuff like that. So there's a deep rabbit hole here. So let's talk about that now. Let's talk about using ANSI escape sequences to actually move the terminal around. This is what you would typically see if you were building like a TUI, a terminal user interface. Something like HTOP, where I can press up and down and that little bar down there moves. Or if I were to Vim a file, notice that like Vim is still on my terminal, but I can move the cursor up and down. I have free range over it. This is a terminal user interface, and you would use ANSI escape sequences to do this. There are higher level libraries you can use. I don't know of any in Bash, but like if you were writing it in C or something like that, you might have ncurses. If you're on Rust, I know Ratatouille is a library that people seem to really like, but we can go ahead and I can show you some of the ones just to sort of get you started. So let's just talk about what we know here. We have tput setAF1 and we can echo high, and now we have the red color. And if we pipe this to XXD, we can actually see like, oh, that's not what you want. You want to actually pipe it to XXD. We can see that it just outputs the escape sequences for us, which is pretty nice. There are some other commands you may not even think about. Clear. What does clear do? Clears my screen. How does that work? Well, we could pipe it to XXD and we can see, here's how clear works. It just prints this. That's what clear does. It literally just prints this to the screen. And if you print this to the screen, you will clear your screen. Printf, we can do it ourselves. The escape sequence, open this, 3, capital J. The escape sequence, H. The escape sequence, open, square bracket, 2, J. We just copied all that. If we print this to the screen, we've cleared it. Hey, that's pretty cool. So you can get really fun with this. You can get really unique things going on. If we pull back open the reference website, there's all sorts of stuff we can do. Erase and display, erase from cursor until end of screen, erase the entire screen, erase saved lines, erase in the line, set graphics mode, set dim mode, faint mode, italics, underline, blinking. There's a ton of stuff you can do here. Again, I can't cover it all, but I want to leave you with this document because you can go through and do a ton of stuff. Move the cursor to the home position, move the cursor to a specific line, move the cursor up some number of lines, save the cursor position, and then restore the cursor position. So I could save where the user's cursor is, jump somewhere in the terminal, maybe to the bottom for a status bar, and then jump back up. I have a video where I make a progress bar in Bash. It's very similar to like apt update or something like that, or apt install if you've ever used that. I'll link that again, but it all uses ANSI escape sequences. That is how it accomplishes it. So let's show some real basic examples of that. We could make a script called move cursor. All right, we have move cursor, user, bin, env bash. There should be no secrecy about what's going on with that shebang. We've done it 8,000 times so far, so what's 8,001 really? Let's go ahead and let's do some magical stuff. So we want to save the cursor. Let's actually describe what we want to do before we go ahead and do it. We want to save the cursor's position. We want to jump somewhere. We want to print hello world, and then we want to restore the cursor. Okay, yep, that makes perfect sense. So let's go ahead and do this. Save the cursor position, jump somewhere, print hello world, and then restore the cursor. Wow, I really can't type, can I? So how do we save the cursor position? Well, if we pull up that sheet, I won't do too much of this cross-referencing during the video, but if we pull up the sheet, you can see that to save the cursor, we need the escape sequence and the number 7. That is it, the escape sequence and the number 7. So we printf the escape sequence and the number 7. That's it. That's it. We have instructed our terminal to save where the cursor's current location is. Now, if we want to jump somewhere, how do we do that? Well, there's a couple different ways we can do this. In this example, I want to use this notation where you give it the capital H or the lowercase f, doesn't really matter which one. We'll move the cursor to a specific line and a specific column. So who cares where we jump? We'll just pick like, I don't know, 2020. That sounds fine. We'll printf and we'll do the escape sequence. We'll give it a line number and a column number. So if you look here, I wish I could have both these on the screen at the same time because it's kind of annoying. But look here, we can see that it takes the escape sequence, open square bracket, the line, semicolon, the column, capital H. So we're going to make use of that. We're going to jump to line 20, semicolon, column 20, H to move the cursor there. Awesome. Now that we've moved there, we can printf hello world. We don't have to worry about emitting a new line because our cursor's in a completely random spot. We don't even want to go to a new line. And let's restore the cursor. The way we do that is how we did 7 above. We're just going to do 8 here, which will restore the cursor's location. So if all this works, what should happen now? If we run move cursor, look at that. Look at that. Hello world. Look at that. It prints it down there. And because we saved the user's location and we moved it back, it'll just keep going there. So if I get down here, we'll overwrite it, but then it writes it right back. So you can see hello world is just nestled nicely in there for us. So pretty cool, pretty neat. We can clear the screen, it's gone, run the command, it's back there. This is fun. This is scratching the surface of stuff you can do. There are some other things you can do with this. Of course, you could build on this. You could make a whole terminal user interface. Like I said, I have videos where I do that. I'll link them below. Last Christmas, I did something really cool. I made a bash script. You can use curl, which gets a web resource. We used it before to curl my website. You can curl xmas.ysap.sh, and this actually just prints a bash script. So that's pretty cool. It prints a whole bash script, and I have a whole video where I actually write this on stream, which was a ton of fun. So I'll link that at the end. If you pipe this to bash, be very careful when you pipe things to bash from a web server like that. I wrote this, I can trust this myself, but be careful when you do this. But take a look at this. Now it says Merry Christmas. It took over my whole terminal. It says Merry Christmas. These colors are changing. It's all using ANSI escape sequences to like move the cursor to the right place and draw the right thing and refresh the line. And then when I control C, we're out of it and it's gone. So that's a really cool thing. Like I said, that's sort of bonus. That'll be at the end of the video. I'll put a link there so you can see how I made that, what went into that, and how that all works. Because that's a really cool thing. Cool, so there's something else I want to talk about. This is a nifty little thing called isATTY. Now, before I explain what that is, let me show you an example of why it's useful, okay? If we do ls, we can see we have a whole bunch of stuff here. In fact, we're done with most of the stuff. Let's move 256 colors, braces numeric, curly brace expansion, and move cursor into the done directory. There we go. So now if we list the done directory, oh boy, there's a lot of stuff here. Let me ls it and pipe it to word count minus l, which counts the number of lines there are, 25. So we have 25 files there, right? Be careful. Yes, we have 25 files, but what word count -l actually counted was the number of new lines. Remember, a file could technically contain a new line in it, and then it would throw us off here. For the most part, though, this is probably safe to rely on. But here's the interesting thing. Here's the part I want to focus on. Look at the output of ls here. Look how many lines there actually are. Here's 1 line. Here's 2 lines. Here's 3. Here's 4. Here's 5. I'm doing a bad job highlighting. 6, 7, 8, 9. There's 9 lines. So why, when we do this, do we get 25? Well, let me show you something else. Instead of piping it to word count minus l, let me just pipe it to cat. Cat reads from standard in and writes the standard out, so it's just going to flow through like there's nothing different. Now it's separated by new lines. How interesting is that? There's no color and it's separated by new lines. So what's going on here? How is ls determining this? ls is not the only program that does this, by the way. You've probably used other programs that do this. Imagine if I curled, let's do this before. We curled my website, ysap.sh. Cool, it prints my website, nothing else but my website. Let me redirect this to dev null. Let's see what it's gonna print. We get a progress bar. So when the output's being redirected or sent somewhere else, it seems like we're getting a progress bar. And when the output's being redirected with ls, it seems like we get this. Close, very close. ls and curl are both detecting if your output is a terminal. That's what is a TTY is. It is a C standard library call. You can look it up here, is a TTY. You can see that it's in 3 here, so it's just a library function. It checks to see if a file descriptor is a terminal. So this is really cool, and we can do this. We have ability to do this in Bash. We have -t. -t takes a file descriptor. Remember, 0 is standard in, 1 is standard out, and 2 is standard error. We can give it 1 here, and this will check if 1 is a terminal. So let's go ahead and put this in a script because it'll be easier to understand there. Let's make a script called check terminal. And we'll do this, user bin env bash, and we'll do something like this. Let's say, chmod plus x, check terminal, vim it, there we go. If --t1, that is standard out, then echo standard out is a TTY. Okay, cool, that makes sense. Else echo standard out is not a TTY, fi. Okay, cool. Yeah, that makes perfect sense, right? So if we run check terminal, standard out is a TTY. If we pipe it to cat, standard out is not a TTY. If we pipe it to less, standard out is not a TTY. It's at the bottom now. So if you pipe it anywhere, if I grep for standard out, we get standard out is not a TTY. So if it's not outputting directly to terminal, in this case, this is outputting to cat, this is outputting to less, this is outputting to grep. Technically, they're just outputting to a pipe, and these programs are reading in from that pipe. So check terminal doesn't technically know it's going to cat, it just knows it's outputting to something and something else is reading it. In this case, it knows it's outputting directly to a terminal. If we have a file descriptor on our system, we are allowed to ask, hey, is this a TTY? Is this a terminal? So that's what's going on here. You can write code this way and you can make changes based on this. So I could do something like, oh, if the output is a terminal, then I could say, let's do the tput example, setaf1 echo, it worked. Well, 1's gonna be confusing because it's red. Let's do a 2 for green. Tput sgr0. And then also down here, we could say, it worked. You could do something like this. This is a contrived example, but the reason you would do something like this is like, oh, if I'm running a program on the terminal, I get color output. That's great. If I'm writing it to a log file, log.txt, and then I check log.txt, there's no color output in there. That's good. That's probably what you want. You'd probably implement this differently. I have code where I've implemented it where I store the colors up here. I would store something like red equals, and then I would do the escape sequence for red. And then if I'm down here, I'll just close this. I'll do a full example. I don't know why I'm skimping on this. Let's do 31M like that. So we have red up here. And then otherwise we'll just say red equals an empty string. And that way, if you're down here, you could say like echo red, it worked. And then this will be set if it's going to a terminal or not. So if I run this, we can see that we get red. And if we pipe it to cat, then we don't get red. So the way I solve that, the way I use this in code typically is I check if it's a TTY for standard out, then I'll set the color codes. Otherwise, I'll set them to an empty string. That way I can use them down here without having to know where the output is going to. If you write code like this, please let the user override it. Curl does this, ls does this. Let the user give flags to recreate that behavior. So you see how ls works like this? I can give it ls -1 to separate it by new lines. I could also pipe it somewhere to separate it by new lines. Give the user the ability to force one way or the other. ls actually does this. The GNU variant of ls is really good. We have color equals auto. This will auto detect whether color should be used based on if the output is a TTY. They also have always, which will always make color show up even if you pipe it through cat. And then we have color equals, I think it's never. There we go. So never will there be color. So this is my advice to you if you're writing programs and you want to make a decision based on if they're outputting to a terminal or not. That's all well and good to set up some sort of sane defaults, but please let the caller of the program override these and set whatever they want. If they don't give you arguments, fine, you can do whatever you think makes sense. But if they give you an argument saying, I never want color, don't give them color output. That's my plea to you from one programmer to another who's seen a bunch of programs out there that just don't seem to behave very nicely. Cool, so now I want to switch gears a little bit. We talked a lot about scripting in Bash, which is super nice. I actually want to focus on another topic, which is the interactive use of Bash. Because as you've seen, I'm using Bash interactively here. It is the terminal I'm using. I'm also writing code for Bash, but I'm using the terminal here. And what you may have noticed is we have Dave at YSAP with this nice little $sign. Hey, this is kind of nice. You may have noticed that I press L, but I still get LS because I seem to have an alias already set up. That's kind of cool. I definitely seem to have some aliases. What about chommed? Because sometimes I misspell chmod. Yeah, definitely aliases set up. So how do I do that? Well, the way that I am accomplishing this is in my home directory, which you can get by doing the tilde operator. Tilde will expand to your home directory. There is a file there called .bashrc. You may or may not have this file. If you create this file, it should get used by your shell when you log in. There are some intricacies around it. Again, I've made a whole video deep diving into it, but for the most part, you should just be able to modify your bashrc and it should just work for you. Now, if we vim this file, let's go ahead and vim the bashrc. Uh-oh, wait, hold on. What did I just do right there? Look at that. I typed in vim $! This is a form of history expansion in Bash. In fact, I think Readline even handles this for you. That's for the nerds to let me know. This exclamation $! Basically says, give me the last argument of the last command that was run. So it's really cool. If I were to echo, hello, how are you? And then I were to echo bang $! We get echo u. It prints the command fully and then it runs the command. So you'll notice that it prints this vim command and then it actually ran vim. So that is a form of substitution there. It's super nice. You can expand basically to that. If you want to run the last command again, you can just do this, bang, bang. And there you go. It will expand to the last command. And of course, this is all part of history. So if we run that history command, you can see there's all this stuff going on here. What if I really quickly wanted to run this command? Command number 2396, exclamation mark, 2396, hit enter. There you go. Yeah, so previously I think I talked about history expansion with set -h and set +h. If you have set -h set, then it should work for you. Hopefully in my last action I had this right because there's set -h and set +h. I may have told you the wrong one. Wow, I really hope I didn't. And when I go back in editing, I'll hope that I didn't make that mistake. You can do set +h and this will turn it off. So now exclamation marks are just literal exclamation marks. They won't have any special treatment, but this means that your history expansion will break. So if I wanted to rerun the history command, the last command 2418, it'll just yell at me and tell me 2418 is there. So set -h will turn it on and then that works how you'd expect it. So that's a form of history expansion. So that's one of the cool things of dealing interactively with this. But yeah, let's go ahead and reopen that bashrc. Oh, wait, hold on. What's going on here? What's happening here? Reverse search? What's going on? I press Control R. Press Control R and I can search through my history in reverse. So I hit Control R, I start typing the command I want, V for Vim, doesn't quite show up, I could type I, and there it is right there. The other thing I can do, I do Control C to break out of it. Control R, V, it doesn't show up, I can hit Control R again, and this will jump to the next thing it found. So this is super useful. It is super convenient to be able to jump through your history like this. Let me vim the bashrc, and here we go. Here's a very basic bashrc. How many lines? I think it's 158 lines. There's a lot here. I don't expect you to understand all of this, but I'm going to show you that my dot files are online. I will put them in the references here. You can pull these down and look through them and see how I set things up. So here we go. we have the first thing I like to check. You don't technically really need to do this, I don't believe, but I like to make sure if the PS1 variable is set. Remember we talked about the PS4 variable. There's also a PS1 variable. We'll get to that. If the PS1 variable is already set, then we just stop running, because that means we're not running interactively. Something has sourced this file. It probably shouldn't have, but we're not running in a way that makes sense. So let's just go ahead and return here. You'll see this is common in a lot of bash RCs. Then I like to set my environmental variables. We use the export keyword here. I haven't talked much about this. This puts the variable into my environment. So now when I fork and exec new commands, they get access to these variables. So I like my editor to be Vim. Grep color, certain versions of grep will allow it to highlight the color that it sees. I don't actually know if my version of grep was doing that or not. But yeah, I do like to sometimes give it color. LS colors, some versions of LS support this, some don't. But when I run LS, these are the colors I like everything to look like. I don't remember this syntax off the top of my head. I wrote this probably 15 years ago, so feel free to steal it if you like how my colors look with LS. The pager I prefer is less. The time zone, it used to be set to Eastern Standard Time, and then it yelled at me and it said it wanted a place, it didn't want a name, so New York is one of the most common Eastern Standard Time. So hey, easy enough. Visual, Vim. That is used by some programs to, I don't even remember the difference between visual and pager, to be honest. Someone can tell me what the difference is. I just forgot at this point, but I just put Vim there because like, hey, I don't know, open in Vim. I don't even know many programs that even respect visual anymore, to be honest. I'd have to pull that stuff back up in my brain. And then path, I just add something to my path variable at the end of opt homebrew bin because I'm on my Mac and I want to pull in the homebrew thing. This is just for the record, this is a stripped down version of my bash RC. This is specific for this bash course, so it's more approachable. The one in my GitHub is a little bit more complex. There's a lot more stuff there, so feel free to peruse that at your leisure. We go down here. I stole these a long time ago maybe from ZSH. I don't remember where. It might even be on like an Arch Linux. No, this would be before this. Some very old version of Linux. I honestly don't remember. It's been so long. I wish I could remember. This tells less how to color things. So there's a lot of stuff here. But if you put all this stuff in here, I'm surprised it even uses tput. But if you put all this stuff here, when I man something, notice that my man pages have colors. If you're wondering how do I get this, that's what I'm using. I'm using the less term cap little variables here to do it. So super duper useful. Now we have some more stuff. We have some shell options. I will dive into these more in the next section of this, but let's jump down here. So we have our bunch of aliases. We have, oh my goodness, so many aliases, so much fun stuff to talk about. Let's talk about make prompt. So this is a function I wrote and the function immediately gets called. The reason I do this, the reason I picked this pattern is because functions can have variables that have limited scope. So I don't want these variables to be defined. If I just define a variable here, like foo equals hello, when I'm on my terminal, I'll just have access to foo. I'll be bleeding into that space. I don't want that. So I put the variables in here behind the local keyword, and then I don't have to worry about them. They get thrown away after this finishes. So make prompt is what I want to focus on because it modifies the PS1 variable. As you can see, it sets it here, and then we add stuff to it. So this is how we make the prompt. The prompt is this string. I modify this file? Okay. The prompt is this string, Dave@ysap with the $ at it with all the colors. So how we do that is I pick all my colors that I like here. So I have the reset character, I have the bold one, and then I have colors that I like. These were arbitrarily picked. I just happen to like these colors. And then we make the prompt. I like to put a comment that shows what we're trying to make. So this part just adds the username. So as you can see, we print color1 and then Dave and then reset. Now this is very important. Do you see this extra escaped opening square bracket and this extra escaped closing square bracket that shows up here? It shows up here. It even shows up down here. You wrap the color codes in this, okay? When you are making a prompt for bash or whatever shell, you want to put your color codes in this because this tells bash that whatever's in here does not count as the length of the prompt. This is very important. You really want to have these here. If you don't put these here, your prompt will still work. You may have seen this where the prompt works, but then when your cursor's like going over here, and then suddenly it gets here, like it gets like 80% of the way to the terminal, and then it goes to the next line, but the line's kind of overwriting itself and your cursor gets all messed up and you're like, why is my shell messed up? Why am I typing over commands? It says I'm typing here, but I'm not actually typing there. Most likely there's probably something escaped improperly in your prompt. You want to put this here, which basically says, hey, don't count the next set of characters towards the length of the string, which I use the color codes here. They're not printable. They're not going to count towards length. And then you put this here to say, hey, now start counting them all to length. So anytime you see color in my prompt in bash, I'm wrapping them in these square bracket notation. It's very important. Then No different here. When it comes time for the @ sign, we turn on the bold, we turn on color 2, and we put a literal @ sign there. That is what we do that. Get down here and we put the host name in here. I'm lying about the host name. I literally just hard coded the string ysap because that's what this course is all about. So this is just a lie. It's not actually the host name. I could put the host name in there and I will show you how to do that. And then we put the prompt character, which is the $sign. Now notice that I escape the $sign. This is actually key. Bash respects this. If you escape the $sign, it will use a $sign if you are a normal user, and it will use a £sign if you are the root user. So you'll see this. You'll see $signs when you're a normal user. Root will have that little £sign, or the hash mark or the octothorpe, whatever you want to call it. ZSH or any sort of C shell variant will have a %sign for normal users, but it will also probably have the £sign for root users. This is how you get that. So I don't have to manually write code to check if I'm root or not. No, I just do this and Bash knows how to expand this, which is super cool. So in this example, we have our ysap hostname here. We've manually turned it into ysap. What if we wanted to get our actual hostname? Well, we have the $hostname variable, and that's great, but is there an easier way to tell Bash to do this? Well, actually, yes, there is. We could do \h. So if we do that and we reload Bash, exec bash, meaning tell this shell to re-become the Bash process, we can see that we have Dave at studio because my hostname is studio.local. So that is a truncated version of my hostname. If you wanted the full hostname, you can give it a /H and you will get the full hostname. So let's reload the shell, and now we have studio.local there. So that's how you do that. Let's go ahead and rechange this to ysap. There are a bunch of other things here. I'm going to pull up a website for that. In the official Bash manual, as you can see, we're on gnu.org here. It actually shows there's a bunch of things you can use for all the different prompts here. So here are some of the backslash you have. So we have the hostname up to the first dot, the H is the hostname, and there's all sorts of stuff. The number of jobs, the base name of the shell's terminal device. You can put carriage returns. I don't even know why you'd want to do that. We can put the time in the prompt, which is kind of nice. You can see exactly like when a command started, and you can have all sorts of stuff here. Like there's a ton of stuff you can put here. Begin a sequence of non-printing characters. This could be useful to embed a terminal control sequence into the prompt. That's what we did. That's where we put our color codes, and then we escape the non-printing characters. This is so Bash can correctly calculate the length. Again, I'll link this in the references, but there's a ton of stuff you can do to customize your PS1 prompt. And of course, it mentions the other one, PS4. There's PS2, which is select, and PS0. I don't even know what PS0 is. So I mean, like, I love Bash, and I don't even know which one that is. So that's really funny. Cool. So now that you know how to customize your prompt if you wanted to, let's go back up and let's talk about some of the stuff we have in our Bash RC, because I did kind of gloss over some stuff. I talked about the basic stuff, but let's go down here to my shell options. CD spell, check win size, and ext glob. We've already talked about ext glob. Ext glob is super useful for extended globbing. I haven't talked about CD spell, and I haven't talked about auto CD. I'm going to talk about these. Notice that these are wrapped in a way where they hide the error messages if they fail. That's because on older versions of Bash, these aren't supported, but I still really like them. So we have CD spell, we have dir spell, and we have auto CD. When you combine a bunch of this stuff, it's really nice. So CD spell is, let's say I misspell a directory, EMTPY. That's not how you spell empty. It still works. It prints the fixed version of it, and it CDs me in there, which is super nice. This only works interactively. You wouldn't ever want this in a script, so please don't put this in scripts. But yeah, this only works when you're interactive, but this is super nice when I just like misspell something, when I'm like, oh, CD into foo. Oh, whoops, I typed it wrong. Okay. Auto CD allows me to CD in directories even if I don't give the CD command. There's some ambiguity around this, but it does kind of work out pretty nice. Say I'm like trying to go somewhere, I'm like, what is it? Files, I think there's something in there. Let me just hit that. It runs CD and brings me there. Now, that's super nice, but don't think you can combine the two. If you have a misspelling, if I spell done like this and I don't actually put CD in front of it, it doesn't know what to do. So it'll correct your spelling with CD, or it will auto CD if you spelled it correctly. Don't assume the two can ever really mix. So those are those options. I really like those options. I think they're super nice. Dot dot is another example. I abuse dot dot if you've seen me in this. I love using the dot dot command just to go up one directory. So now I don't even know where I am. There we go. Now we're back in foo. So yeah, I love dot dot. I think it's super great. But again, this is interactive only. This is when I'm on the shell that I want this. In a script, I don't want things to be doing typo detection. That is, oh my God, I can't even imagine the issues that would crop up because of that. So yeah, don't want that there. Let's talk about some of my aliases, because I use a lot. As you can see, I alias dot dot to be that way. Now, auto CD should handle this, but I have used Bash on versions that don't have auto CD. So I just put this here. So even if auto CD fails, I have my own alias of dot dot doing it for me. So I like it. I used to use the Silver Searcher. Now I use grep, and I'm sorry, but it's easier for me to type AG than it is to type RG just because of the Dvorak keyboard layout that I type in. So I alias one command over another command. I feel really bad about that, but you know, hey, it is what it is. Chommed because I misspell chmod a lot. I have one called external IP. This curls my own website. I'm not going to run this because I don't want to give out my external IP, but you can run this on your own machine and it will give you your external IP. Don't trust my server to be up 100% of the time. I just use it for my own little way of finding out what my IP address is. Super nice. You don't need the HTTPS if you don't want it. I prefer it. I alias grep to grep because I make spelling mistakes. HL is really cool. This uses grep. This is a Rust tool you can install, RG. It uses the pass-through flag. I want to show you why I like this because it's that awesome. Let's go ahead and look at our done file and let's look at what do we have in file.txt. We have foo, bar, and baz. Let's go ahead and highlight bar. Look how nice it is. It shows you the same file, but it highlights exactly what you're looking for. Let's go ahead and highlight B. There's every B in the file. Let's go ahead and highlight A and B. There we go. There's every A and B in the file. Highlight is stupidly useful. I love it. Thank you, grep. Grep is a super great program. Oh, man. L is ls. LL is a long listing of ls, so I do sometimes LL if I want to do this. It's the same as ls des LHA. L for long, H for human readable, A for all files. Let's go back into it. And sudo for sudo, because again, I really like to make typos. Here's where things get a little bit gnarly, but I want to at least equip you guys to be able to deal with some of this stuff. Let's take a look at what's happening here. There's two separate commands. Grep -- color auto, read in from dev null and write to dev null. Now this ampersand greater than dev null means both standard error and standard out go to dev null. And if that's successful, then we set an alias. So what is that actually doing? Here's what I'm doing. I'm reading in from nothing, I'm writing to nothing, so that should be successful. This is a way of checking to see, does grep support the -- color equals auto, or am I on a machine with GNU grep? So I literally do feature detection to see if this flag is available, and if that flag is available, then I alias my grep to use that flag. This is super useful. Sometimes I'm on a machine where grep doesn't support that flag, so I don't want to have an alias to grep that's broken. I only alias grep if that flag is supported. That's what that line does here. xdg open is like a Linux command to open files directly from the terminal. I check -- version. I check if I'm able to run xdg open with the -- version flag. If that works, if that's successful, then I alias open to xdg open. Otherwise, I'm on my Mac, which has an open command. So this way, I only ever have to run the open command, and it kind of works on most systems that I'm on, which is super nice. ls is another weird one. ls has the GNU variant, but then I've been using a version of like Solaris or Illumos ls, so things can be a little bit wild here. If we do a little check, if the color auto flag is supported, we just ls dev null, so that'll be pretty fast. If the color equals auto is supported, then we set the alias to this. Otherwise, we set the alias to that. The difference is the -g flag, I just assume is going to give me color output. Otherwise, I do the -- color equals auto. P is nice because if I wanted to, here, I'll show you something. If I run ls, it's technically running this for me. If I wanted to run ls without those flags, I could run command ls, and now it runs ls without using my alias. There's another trick I've seen people do where they do \ls. That's another way to do it. You just \ the command and that will avoid the aliases for you, which is kind of nice. But as you can see, this is what ls would look like normally. Let's go ahead and add the color equals auto flag. Now we have color, and then, let's put the \ here. There we go. And then do you see what's missing? Let me give -p. Now directories have a / at the end of them, so I can easily identify that they are directories. That's what that does. That's what those are. So we've in this, we have our make prompt. We've already talked about this. We have prompt command. I haven't talked about this, but this is really cool. This is built into bash prompt command, and this is code that will run every time a new prompt is generated. So basically every time I hit enter, that code is running. Now what that code actually does is it runs this function prompt command, and this function gets my username, it gets the host name, it trims off anything to the right of the host name, so it's a very small host name. We get the present working directory, and we swap out if it looks like my home directory with the literal tilde character because it's easier to see. And then we check if there was an SSH client, meaning are we SSH somewhere? Then we append this string to it, and then we run this. It's a pretty gnarly printf command, but look at this. We've already seen this. This is the escape sequence. Why I chose to use 033, I don't really know. I could have just put the escape character there. But we run this gnarly thing, which prints this SSH string if it was set, the user, the host, and the PWD, but then it puts it where? We have this weird like escape sequence of 0, semicolon, and then we close it with a 7. So what's going on here? I will show you. look up here, follow my mouse all the way at the top. You see that terminal, Dave at Studio, and then it has my directory up there. That's how I set that. That is what's going on here. That is how to set the actual title bar of your terminal. So I could do something like copy and paste all that stuff here. Let's get rid of all the %s's here. And let's just say, hello world. And we run that. And it doesn't work because the prompt command immediately overrode it. So if we unset prompt command, now it won't change it. If we run this, look at the top of my terminal, hello world. So if I wanted to, I could like put an animation up there or something crazy. Maybe I'll do it in the future video. It'll be a lot of fun. That's what that's doing. Let's go ahead and re-exec bash. So now it will update that title bar for us. But that's what the prompt command's doing. It is updating my title bar. So if you ever wondered how title bars are updated, that's how. I won't go into all this. This is a little wrapper function that I really like. I didn't get to use it at all during this course, but when you diff two files, which is to see the difference between two files. Actually, let me show you a quick example of that. If I go into the done directory, remember how we had simple CSV and complex? I can do a diff of simple to complex and it will show me the differences between them. That's well and good, but I like my little wrapper that runs color diff and then shows it like this. I wrote this maybe like 15 years ago, so I mean, there's probably better tools that do it now, but I find it a lot easier to read it with color and a red and green. It makes it so much easier to see. Probably won't go through the rest of these because there's a couple other functions you guys can feel free to look at. There's that color function, which we actually ended up writing ourselves. There's a nice little copy wrapper, so I can paste things to copy and it puts it in my clipboard with whatever tool is available to put it in my clipboard. And then we have, we have this one. This one's really fun, the True Color Rainbow. You remember that 24-bit color thing I was talking about? We could technically run this, and you can see what 24-bit color rainbow looks like on that. So again, I would encourage you all to check out this code, go take a look at it, and kind of look through it yourself and mess around with it. Have fun. Make your own bash RC, make your own .file repos on GitHub, and go ahead and start customizing your environment. It's a ton of fun. All right, the last thing I want to show you when it comes to like interactive use is how I've been navigating so quickly. Like, yes, I know how to use Vim. I can navigate Vim pretty quickly. But what if I had something like, I don't know, I want an ls done and ls empty and ls files. Okay, I can run that. That's all good. I can press up and down to bring back the commands from my history. I can also press Control P, which is the same as up for previous, and Control N, which is the same as down for next. That's how I think of it in my head. This is super nice because I don't have to take my hands off the actual like keyboard. I don't have to move over to the arrow keys. I can keep my hand in the same space and just move around, which is super nice. So let's go ahead. Let's pull that command back up. And then some of the things you can do, these are called Readline Shortcuts. It's called Readline. This is what Bash uses. Other programs use it too, like if you're using Node.js. If you were to open up Node.js, it's technically using Readline here. So I could jump around the same thing. If I said like console.log, I know this is a Bash course. Hi, I could press up and it brings up the previous command. I could press Control N, Control P, and it all works. It's because it's using Readline. It's the same library that's going on for Bash. And by default, we are in the Emacs style mode, and this is what I've gotten pretty good at. So let's go ahead and pull back open that ls command. Get ready for this. Press the Alt key or the Super key or your Meta key, whatever that is. By default for me on my Mac, it's Option. If I hold the Option key, I can do Option B to jump backward and Option F to jump forward. So convenient. Absolutely so convenient. Cannot live without it. If I go between two words and do Option T, I can swap them. I can swap full words. So I'm doing B to go back, T to swap. How cool is that? It is super useful. It's awesome. If you use Control instead of Option, I can do B to go back one character and F to go forward one character. It's the same as right and left arrow, but you don't have to take your hands off of the actual keyboard and jump to little arrows to find them. Super useful, super awesome. Just like you had Alt T, I can do Control T, and I can swap two letters and move my cursor forward. Very confusing, very specific, very niche when you would need it, but sometimes it's super useful. If you have like a, all right, let's say I were to have suad, which you can see I messed up sudo there. Now on my system, this would work because I have the alias. Put the cursor on the D, hit Control T. Now we have sudo. So it's very situational, but it is kind of useful to know about. The other ones I really like, Control W, delete back a word. Control W, delete back a word. Alt backspace is very similar, but it has a smaller word boundary. So if I were to curl ysap, let's say like, let's do https://ysap.sh/help. There we go. I can do Option B and Option F to jump around this, and I can do Option Delete to just delete up to like a word marker like that. Whereas Control W trashes the whole argument, which again, super nice, super useful. And let's say you're really far over here and you're like, oh man, I need to get to the beginning of the command. Control A to get to the beginning, Control E to get to the end. And one thing I really like, Control U. Delete everything up until the left. So Control U is super useful. Obviously, you could also just Control C and get out of what you were doing. So yeah, if you want to learn more about this stuff, these are called Readline Shortcuts. We are in Emacs mode in Bash to get this. I'll put some references at the end of this, but I am scratching the surface. I hope this is giving you a jump off point to go learn more if you want to. Now, before I get too deep into this, I want to give a shout out, of course, to the Wooledge Wiki. I mean, this is huge. They are one of the best references I have for this stuff. This is how I learned Bash. I learned Bash by going into the IRC Bash channel on Freenode back in like 2010. And this wiki back then was like invaluable to me. So I can't give them enough of a shout out here. Like, I just love it. There's so many great things. So some of the pitfalls I'm talking about are going to be mentioned here because they're common. People who learned or do Bash, they run into this stuff. So I just want to talk about some of them that I've seen. And one of them I'm really interested to talk about is ls, and I want to talk about this one because it's actually kind of fun to me. This is the first video I ever made for You Suck at Programming, was talking about this specific pitfall. The first episode of my You Suck at Programming series back in 2022 was about this topic, so we're going full circle here now that I'm making this Bash course. I have some files here ready for us. We have files directory and we have bad and good, so you can tell one script's good and one script's bad. All right, very simple. Let's go ahead and ls files and see what we have. We have 5 files, A, B, C, D, and E. That's awesome. Let's look at our bad script. For F in ls files, file is $F. Now look at this. We know better. We could do this. We could swap out the notation for this. That's good. But like I said, remember, if we're not quoting our expansion here and it works because of that, then we're probably doing something wrong. I want to showcase that. So let's go ahead. Let's look at our bad script. And let's run our bad script. File is A, file is B, file is C, file is D, file is E. Well, I mean, that kind of looks right? Like, that makes sense to me. Like, yeah, so let's pull up our good script. What's happening here? For F in /file star. Okay, we're using a wildcard now. We're using a glob operator. Okay, what's better about that? Well, this paints a different picture, doesn't it? This is totally different. Look at this. File is A, file is B, file is C, file is D, space, E. So this looks like there's 5 files here. But this one says there's only 4 files here. How many files are here exactly? ls minus l files. We can see that there are 4 files, A, B, C, and D with a bunch of white space in it. So because of that white space, remember I taught this before, because of that white space, it was broken apart as a separate argument to the for loop. In certain cases, that might be what you want, but in this case, it's almost certainly not what you want. And let's not even talk about another way I could mess this up for you. We have files here. Let's touch a new file. We know how to do this with special strings. Let's touch F, new line, G. So the next letter is the alphabet. If we ls this, oh, we get a nice little question mark character. That's very nice. What if we ls and pipe to cat? Okay, well, we can see that D clearly has a problem because it has E here, but F and G look like separate files, right? So wait, what does that mean? If I ls and then pipe it to, was it word count minus L, it says there are 6 files here. Well, are there 6 files? Let's run the bad script. The bad script seems to think there are 7 files here, so that's not 6. Let's run the good script. The good script thinks there are 1, 2, 3, 4, 5. So you see how confusing this can get? This one has a new line in it. This one has space in it. They're both totally valid. You can have files like this. And in reality, there are only 5 files in this directory. If we do a long listing, we can also see it. Let me actually type it correctly. If we do a long listing, we can see the individual 5 files here. But yeah, so be mindful of this. The bad syntax, you will see this a lot. A lot of programmers write this, and here's the thing, for the most part, it probably works. If you don't have spaces or new lines or any sort of tabs in your files, it'll work. And then when it breaks, people are like, well, maybe you shouldn't put space in your files. Like, dude, just write better code, man. So yeah, this is just a common pitfall. I see it so often. It's pitfall number 1 in the Wooledge wiki, and it's pitfall number 1 for a reason, man. I just see it everywhere. It's so prevalent. Don't rely on the output of ls, okay? Just use the built-in operators to list files, and you'll be safe. You'll eliminate these issues. Okay, here's another pitfall or gotcha I see. So many times people ask, how do I give my aliases arguments? So if you remember, we could make an alias like greet equals echo, let's put this in quotes, echo hello. We can do this. And now we can greet Dave, and it will say hello, Dave, because it swaps out greet with what is here. But what if you wanted to say hello, $1, nice to meet you. People will do this, and they'll run this, and they'll be like, hello, nice to meet you, Dave. Well, I mean, that's a nice sentence, but that's not what I wanted. I wanted, hello, Dave, nice to meet you. I didn't want Dave at the end of it, but that's how aliases work. Aliases swap out the term greet with everything here. So everything here got swapped down here, and then Dave got appended to the end of this. That's how that worked. So a lot of people will scratch their head. They'll be like, how do I do this? How do I get arguments into my aliases? You don't. What you need is a mini program. And do you remember what mini programs are? Let's unalias greet, because we don't want an alias to be messing with us here, because aliases take precedence. And let's make a function. So we can define a function here interactively where we could say echo hello, $1, nice to meet you. And you are free to then, oh, did I just called this function alias. This is not at all what I wanted. Wow, I love that it let me do that. Let's go ahead and do that, and let's just pretend I didn't do that. That's gonna mess things up. We can go ahead and unset -f alias, which will unset that as a function. Let's not cause any problems, okay? Let's pretend I didn't do that. Let's go back. All right, so now we have this greet function and nothing else. So we can run greet Dave, and there we go. Hello, Dave, nice to meet you. So if you want an alias with arguments, you don't want an alias with arguments. You actually want a function if you're in Bash. I think other shells supported ZSH might actually support that, but you don't really want that. Because if you were to do something like alias foo equals echo $1, $2, you were to do something like that, you run foo, $1 and $2 aren't set in my current shell. But they could be. We could use the set built in to do that. We could say set, go ahead and give it this, what tells it to stop processing arguments, and then we could put, I don't know, A, B, C here. Now, if we echo $1 and $2, we get A and B, because $1 is that, $2 is that, and $3 is that. That is how you can set the positional parameters in your program. You can technically overwrite them. So, cool little thing, just to be aware of that. You'll probably see that syntax out in the wild. People will do things like that. So, yeah, just definitely a gotcha to be mindful of. Okay, so here's another gotcha, and this is something I've hinted at before, but we're going to talk about it more in depth here. Let's go ahead and make a special string with an escape sequence. We'll make it yellow, and it will say hello world, and then we will close that escape sequence, so 0M, and close that. Notice that it doesn't quite work. We want to use the single quotes here, not the double quotes. The double quotes are valid, but the single quotes will actually interpret those characters properly because they're escaped properly. So now we have this, we have hello world, and it's yellow. That's great. We can also store this as a variable. So we could do s equals that, and now we have a variable with s in it. And we can also use this notation to get the length of that string. And we can see that it's length 20. Shouldn't really be length 20, right? Hello is 5 characters, this is 5 characters, this is 1 character, what's going on here? Well, it's 11 printable characters, but then there are 9 unprintable characters. That's what's happening. The ANSI escape sequences count towards the character count. So be mindful of that. Just be aware that that is the case. Some languages strip those out. Some languages keep that. I think most languages, this would be the case, but just be aware of this. Because if I were to echo this without the trailing new line and pipe it to word count minus C, you can see that it is 20 bytes. So there are 20 bytes of data there, which lines up with the length that Bash thinks it is. Be careful with this because it does get even more confusing. You ready for this? We're going to override that string to not be that color code anymore. Let's go ahead and make it this first emoji that showed up there. There we go. So now S is equal to that emoji. Totally valid. We can echo S and we get that. Echo the length of S and it is 1. But be careful because the actual byte count of S is slightly different because it takes 4 bytes to print this emoji, whereas Bash says, oh yeah, that's only 1 character. So there's all sorts of like locale stuff going on there. You need to know about like code points, Unicode, UTF-8 and stuff. It is a rabbit hole. I don't have enough time in this course to teach it. Also, I don't even know it that well. If you've ever tried to learn this stuff, it is very, very confusing. So just be aware of this. The length of strings can be an absolute gotcha in Bash. So just be aware that this is the case here. Okay, and finally, here's one last thing, one last gotcha, one last way to have a fun time, okay? Here is a command that is very scary. I'm not lying to you, it actually legitimately is a scary command. It can cause problems. You've probably seen it. It's sort of a meme on the internet. Probably more so a while back than it is now. I haven't seen it too much recently, but this is like a known thing. So be careful about this. If you notice, I am logged into Void, the Linux machine that I have. We are running Linux over here. It is in a virtual machine. There's a reason for that. Let's ls what I have. I have bomb.txt and diagram.txt. So let's take a look at bomb.txt. Don't run this. Don't run this. This is very important. Look at this code. Study this code. Don't run this code. If you run this code, it will probably lock up your machine. I'm not lying. More modern machines have ways of dealing with this, so it probably won't lock up your machine, but be mindful, this can cause some serious problem. This little code right here, and it is very esoteric. How do we even understand what's going on here? Well, we just took a whole bash course. So let's unminify the bomb, okay? We're gonna go ahead and we're gonna put this in a script. We are not going to run it, okay? We're gonna be very safe. Do not run this. Let me handle it because I am an expert here. We go down here, we paste it in. So what's going on here? Well, look, we have colon, which again, colon is built into bash, but we can override it. It's the null command. We're going to override it to be a function. So let's put some spaces here, and this is a function definition. So let's put a new line here. Let's tab this out, and let's put a new line here. Hey, look, it's already starting to make sense. This semicolon separates these two commands, so let's put a new line here. So now we have that. And now we have colon, pipe, colon, ampersand. So let's change the word colon to something we could understand. My func. So we're going to change colon to my func and every version of it. There we go. Does this make more sense now? We make a function called myfunc. Myfunc calls itself, pipes itself to itself, and then puts itself in the background. This is a Forkbomb. This is a recursive Forkbomb. This will have devastating effects to your computer if you don't have proper limits in place. So this is dangerous. And this final myfunc at the bottom, the final colon, is the trigger. This is what actually runs this. So we're not going to run this. In fact, we're not going to, I already chmod plus exit. We're going to minus exit. So we don't even accidentally run it. We don't want that to be runnable. Okay. Now, let's go ahead and explain what actually happens, because you can kind of understand what's happening here. But if you look at this little diagram I made, not the best, not my best work, but you can see that function forks off function and function. They fork off function, function, and function. So as you can see, it's recursive. It's recursive in nature. It's exponential growth. The first function will create 2, 2 will create 4, 4 will create 8, 8 will create 16, 32, 64, 128, 256, etc. So not great. Please do not run this, but we can show how to safely run this, okay? Let's cp unminify bomb, and we're gonna call it step bomb. Why are we calling it step bomb? Because we are going to step through the bomb. So let's go ahead and change this myfunc to bomb. Let's just change it everywhere, right? Myfunc to bomb. So we still know what it is. It's a bomb function. That's not great. Let's go ahead and add some accounting to this. So let's take some variables. Let's take a number as $1 and a name as $2. So, okay, we have that. Now we want to print the actual name and number. So we could do this. We could say num name is running. There we go. Okay, very simple. Okay, now we're gonna increment num plus plus, and then we're gonna call bomb with the number and a name. Now, what name are we going to give it? Because we have the two numbers here. We haven't taken our numbers yet. Let's give it the name left and the name right. So this might be kind of confusing, but let's go down here and give it the number 0. So we're going to start at 0, and we're going to give it the name init for initial. So the bomb function takes a number and a name, and the number increments every layer deep we get. So we're going to start at layer 0, which is 1 bomb function. Then we're going to go to layer 1, which will have 2 bomb functions. Then we're going to go to layer 2, which will have 4 bomb functions. Yada, yada, yada. This is still a dangerous command. We don't want to run this, okay? So let's go ahead and do this. If num equal 2, then we will return 0. We will return success. We won't keep running. So this is our safety. All right, now one last thing before we run this. As you can see, this is echoing to standard out, which means the bomb function will actually output that into the input of the other bomb function. We don't want that. We want this to go directly to the terminal. So let's go ahead and output that to standard error. This way, no data will get transferred between the two. And let's go ahead and run this. Step bomb. Okay, a lot going on here. 0 init is running, 1 left is running, 1 right is running, 2 left is running, 2 right is running, 2 left is running. So as you can see, on the left side, we had 1 here, but on the left side here, we have 2 here. So it'll get big very fast. If we set the number to, let's say, 5, this is going to get very big. Very, very big. In fact, you can see it even return before some of the output was actually done running. Now, here's the cool thing we could do. We could process this output, okay? So we could take the standard error and write it to standard out, so it'll all go to the same place, and then we could pipe this to sort. Now we've sorted the output, which is really neat. We can see that there are 2 1s, there are 4 2s, there are 8 3s, 16 4s, and 32 5s. Is that right? Maybe if I counted those right. There's a lot going on here. But here's the fun part. Let's go ahead and use all our tools that we know. Let's get just the first field, because the first field is just the number, right? If we awk, we can do this little thing to print $1, and we will get the first field separated by white space. You could also use cut to get this, and now we get that, and we can pipe it to unique -c, which is our frequency count. This is very confusing, but what that means is there is one process running at layer 0 with number 0. There are 2 processes running at layer 1. There are 4 processes running at layer 2. There are 8 processes running at layer 3. It's exponential growth. There are 16 running at layer 4, and there are 32 running at layer 5. So, of course, we could increment this trigger if we wanted to. We could make it like 8. This will get large, but we could still run it. There were 256 processes running at layer 8. So if we don't put a stop on this, if we don't bind it somewhere, it'll just keep running forever. And that can be very dangerous. So that's why this is scary. This little minified syntax makes a function called colon. Colon calls itself, pipes itself to itself, runs it in the background, defines that function with a semicolon, and then runs itself. This final trigger is what actually runs the Forkbomb. So don't run a Forkbomb on your system. It's incredibly dangerous. Thank you all for watching my bash course. I appreciate it so much. If you have made it this far, congratulations. Here we go. This is for you. There's the Forkbomb running on my system. Look at that. There you go. How beautiful is that? Thank you so much for watching. Honestly, this has been a long course. There's so much that has gone into it. I appreciate every single one of you who has made it this far. Thank you so much. This course is completely free. It's on YouTube for free. Course.ysap.sh is the permalink for it. It's free. You can pay if you want the DRM free MP4 download. Sign up for my Patreon if you want to give me money. If you don't want to, that's fine. I understand. I don't believe in paywalling educational content. Just hit like and subscribe on YouTube. Really, just hit subscribe. I want to try and hit 100,000 subscribers. At the time of this recording, I have about 62,000 subscribers. So we'll see what this can do. Hopefully me fork-bombing my machine directly in front of you has given you the motivation you need. So, yeah, I can't do anything here. What I can do is I could open up another terminal and I could SSH into void, and it fails. Wait, oh, we almost got in. We almost got in. So like I said, be really careful with this, okay? Just be really careful. Hopefully I've given you the tools to understand what's going on here. Again, I will have references and stuff. There's probably some topics that I've skipped, not because I wanted to skip, just because there's so much in this course. It took so long to actually work up all the materials. I know there are things that I have missed. So I will put as many references as I can with educational content from me and other people to help you get going with this. But hopefully I've given you enough to get going and to really hit the ground running, because we've talked about some advanced topics here. This has been a Dave Eddy production. You suck at programming. This machine is still messed up. So this is probably bonus content for the super fans here. Let's go ahead and log into the hypervisor of that machine. And let's do a z80 list grep void, because it is a virtual machine. I'm running on Illumos, which is the fork of OpenSolaris. And void is a beehive instance, so it is a Illumos zone, and inside that zone, which is an OS level virtualization, is a beehive instance, which is originally FreeBSD's hardware virtualization like software that they write. So it is a hardware virtualized instance inside a zone running on my machine. It says it's running. It's not really. Wow, it's completely unresponsive. This is hilarious. So you're welcome for that. Z80M, reboot, void. Go ahead, put sudo in front of it. And there we go. Now it should reboot. If you're ever in the situation and you're hitting enter and nothing's showing up and you know SSH is borked, shift tilde dot and it will pull you out of it. You might have to hit enter after it, but yeah, tilde dot and it pulls you out of SSH. That's the SSH escape hatch. So let's go ahead and SSH back into void. And maybe it's back up, maybe it's not. It might take some time to come back up. Let's do a nice little list on that. And it says it's running. I didn't actually know if it said it was, I didn't actually see if it went down for a reboot or not. But yeah, hopefully it's working. Sudo z80m console. Let's console into void and see if there's anything even on the console for us. Out of memory. Yeah, so the killer in Linux is going on here. So it tried to give it a soft reboot. That's not going to work. I have to remember my escape sequence. I remember my escape sequence. Let's go ahead and hard reboot that with Z80M. I don't remember how to do it off the top of my head because it has been such a long time. We'll probably have to do a sudo Z80M power off on void. So let's give it a hard power off. And yeah, so now it should just be completely down. If I ping void, maybe it'll just hang. Yeah, it'll actually just not work. That's great. Perfect. Sudo z80m boot void. And this should bring it up. Oh, it's already running. Huh. Okay, I'm getting void login here. That seems better. So if I go here, can I SSH into void? Hey, look at that. It works. So yeah, on my system, I had to recover from a Forkbomb that way. That's probably not good. I think you can set U limits on your machine to limit the amount of like stack size and stuff. I should probably look into this. I should probably add some sane U limits to my bash RC. What have I been doing this whole time? So yeah, there's a Forkbomb on my machine. That's it. That's my bash course. Thank you so much for watching. I've already said all this. Thank you guys. Thank you so much for watching. I honestly appreciate it. And I know it's been a long time coming, but it's out now. So yeah, go check out the channel. Go subscribe. It's called You Suck at Programming. I have been Dave Eddy. Thank you.